My name is Rod, and this is our course Advanced Spark for developers. And what we're going to be doing is kind of kicking off with sort of a general introduction, a couple of housekeeping points. We're going for the next 4 hours. So we'll take about a 10-minute break about 2 hours in, 10, 15 minutes, just so people can get up and get some activity in and something like that. We need that cognitive break. We are going to be, I'll go through these slides in just a moment, but just to kind of keep some other things in mind. We're going to be doing this for 6 days, 4 hours a day. So it's a little bit different than just blasting our way through it. We're really and we'll kind of tune this as we go along, but the general plan I'm getting is to sort of spend the first little while delving into the architecture and a lot of the conceptual ideas that form the foundation of Spark and related concepts. And then next week, we'll really delve deeply into the tuning aspects of it. And once we have a foundation on which to build. So this is kind of, this is assuming a kind of a 3 full day approach. So we will focus on Scala in the beginning, and this is an important concept because since Spark is written in Scala, many of the ideas of Scala are inherited into Spark. So sometimes understanding what Scala does from a conceptual point of view helps understand why Spark is doing the things that it's doing. That takes us into our core Spark architecture and data structures. We'll probably cover most of this in the next day or a day or two. So we'll probably get to the end of day 1, maybe into day 2 by the end of tomorrow, and we're into day 2 by the end of tomorrow. And then the topic that we're really probably going to focus on for most of next week is this part here with the Spark tuning and the production, since there are some topics we want to kind of add into there. That's the general plan. Like I said, this plan is modifiable as we go along and tuning things up. There we go. Prerequisites and expectations. The request was made specifically that we focus on Scala. This general programming model allows you to actually work in a number of languages, but we are going to focus conceptually on Scala and some of the other things as well. We will do a quick Scala primer. I am going to go a little bit beyond that because I want to get to the conceptual part of Scala. And we're going to assume that you all have some basic familiarity with Java or equivalent object-oriented programming, since those concepts will start to come up in various points in the course. You should be able to work in a Linux environment, and we will be using some virtual machines. I'll be assigning those out later today for you to experiment with. And you will have a full environment in there. So one of the things that I do want to caution you about is that if you're going to be experimental about things, you should experiment in the virtual machines that we give you, not in any of your own machines, because the virtual machines are no consequences environment. What that means, if something goes terribly wrong, we'll just restart the instance and get you back into a clean environment. We are not assuming any knowledge of Spark, although you may have some. So I'll find out what everybody's skill levels in these areas are in just a moment. But we are going to focus, I said, particularly Monday, Tuesday, Wednesday next week, we're going to be focusing really on advanced optimization and optimization techniques and the underlying optimization technology. And we will adjust the class as we go along. A couple of things I'll just mention here. This is kind of standard stock slides. But first of all, this is the first time I'm teaching from this set of materials. So I sometimes might have to fumble around a little bit to figure out where things are, but do bear with me. We'll get that sorted out. I've just gotten a hold of all the production materials a little while ago, so was still sort of going through it, then matching up what I wanted to teach with what was in the various slides and various labs. So I'm still making that matching here. So uh, keep that in mind. The labs are we're going to be doing lots of labs. Again, I'm going to encourage you, be experimental if you want. If you break something, it doesn't really matter. We'll just start it up again. But please don't be experimental in your own environment, because you don't want to screw up any of your own internal settings or any of your environments. So we're going to assume that we know all of this idea that we're going to learn the theory, which is what we're going to be talking about, and then you're going to go and practice out a number of different exercises to reinforce the particular theory. That's the overall concept here. These are kind of cool images. There we go. Somebody's done some nice photoshopping there. So we're going to get to the actual start of the course now. To kind of done that housekeeping. The other bit of housekeeping that I would like to do is with regards to the Zoom. I haven't used Zoom to teach a course. I've only used it for conferences. So I do believe I'm trying to figure out if there is I got to share, and there is a chat. So if you do feel you want to chat me, I will try and keep the chat window open while I'm lecturing so I can respond to those. If you're chatting and I'm not responding, you may want to just give me a verbal heads up that you're chatting. Let me see, is there anything else that we want to mention? I think that's probably the important thing. You can just speak up as we go along. So I'm going to ask you all to give me a little bit of feedback on this, more or less aligned with this template. I'm the purple or violet thing down here, something non-technical about you, not mandatory. If I'm going to replace that actually with something else. So we'll start with your name, your background, and I'm also curious what your current role is, because sometimes that's not the same as your background. Very often, technical people wind up as managers or team leads. Technologies that you are familiar with, again, technologies that are related to your work with Spark. So if you are very good at the piano, that's not something that's really quite relevant. Interesting, but not relevant. And also, I want to know about your familiarity with Spark. And also, I'm going to add Scala in there as well. I'm particularly interested in the programming languages that you're familiar with. I'm also going to replace number 4. Oh, you can give me an answer to the last one if you want. But the point that I would like to get from you is, and this is just kind of going to get me oriented, is any specific things that are on your mind that you want to try and address during the course. So particular issues, particular questions, things that annoy you, in that you're saying, well, if I could figure something out, then I could get rid of this annoyance. So I want you to think about that. And if you can't think of anything in that category right now, that's fine. You're always welcome to add to that last item at any point during the course. It helps me too, because as I'm presenting the material, if I know that material is of interest to you or important to you, then it serves as a reminder to me to focus appropriately on the concepts that are relevant. So I'll start to give you an idea of what's sort of expected here. My name is Rod, and my background is quite eclectic. I started back in the 1970s as a theoretical mathematician, which is one of the reasons I love Spark, not Spark, but Scala. I also worked studied as a cognitive psychologist and anthropologist, studying linguistics and looking at cognitive structures, which got me into artificial intelligence in the early 1980s, in that first, or I should say the second big boom of AI. I wound up doing development work and scientific consultant, and eventually became project managers for several AI startup companies funded by several of the computer companies. I'd spent most of my time up to that in the mainframe world, working in developing things like language dictionaries, automated language dictionaries, and that sort of environment, working with large corpuses of text. I wound up doing project management work for a number of research projects and development projects for a number of years, but I always continued to teach because I was an early adopter of a number of technologies, including object-oriented technology in the early mid-'80s, when everybody thought it was just going to be a passing fad. And I wound up doing a lot of teaching as I had to share these things that I was adopting with my colleagues and my coworkers and my teams. So in the late 1980s, early 1990s, I got out of project management. I decided that I wasn't a good bureaucrat, and I was a really bad employee in that sense. And I started doing consulting and teaching. I had an opportunity to go around a number of different organizations in a variety of industries, Wall Street, defense contractors. And I got to see what a lot of, and I've always tell people, I was never really the smartest guy in the room, but I did get a chance to see what the smartest guys in the room were doing. And that was of interest to me as an anthropologist. So I tried to focus on what are these people doing that is really a best practice that I can take back and share with other people. I have been always interested in, of course, machine learning, working with data representation, how we manipulate data, what's the reality of data in terms of what it tells us, what are the effective tools for analyzing data, and all of these sorts of related issues that go around with data. So this is an area of interest to me. I got interested in the whole big data analytics world as it came out. I've had my fingers in a number of pies. I'm particularly fascinated with Spark because Spark employs a number of what I think are brilliant and innovative approaches to the problem, and I hope I can share some of the kind of admiration that I feel for the product with you as we go through the course. So that's basically, I'm all over the map in terms of technologies as well, programming in a number of languages, working from everything from developing executable requirements for business analysis to software testing, quality assurance, data modeling, domain modeling, all that kind of general technology. So hopefully I'm bringing a somewhat unified approach to the class, and we'll be able to relate to all of you from different backgrounds. My particular goal for the course is to try to give you something that you can take back and use on a very practical sense. So that's generally me. So I'm going to kind of go through my list here, and I've got a list of people on the chat window. So I'm hoping that that's a complete list. If not, somebody's going to have to shout out. So we'll go alphabetically. Michael, how about you? Let's hear from you.
Yeah, so I can start. So my current role at, let's say, Cryolytics is officially engineering specialist. What that translates into is somebody who's been doing technology for, let's say, way too long and still wants to keep doing it. So we found a way for me found a way to make it interesting for me. So like I've been with the company for a little over 5 years at this point. So which is way past the norm. So we have to find something. So I'm sort of looking at more at the, let's say, architectural implications of what the individual teams are doing. So the rest of the guys, what they're producing, I'm sort of looking at whether or not it fits within what we want to do, whether or not we can sort of challenge it to make it better. So more on a high level. Now that said, I'm still involved in some projects, so I still want to like to keep my hands dirty. As for, let's say, programming languages, I'm also, let's say, not sticking to only one. Way back when, I used to do Java and C. Then at some point, I transitioned into Ruby, spent a bunch of time there. And most recently, I was doing some projects in Golang, and right now I'm starting to learn Scala so that I can be effective with Spark, let's say. So on that scale of 1 to 4, I would say still maybe somewhere between 1 and 2, still trying to sort of figure out stuff that is you could consider basic, but That said, I can read code, so Scala is not really an issue. The most interesting thing for me is actually Spark.
Great. So yeah, you already say my name. It's Gregory. My title, what I'm doing here, I'm a senior data engineer. So basically, in the data team, like we are responsible of ingesting, transforming, making the data available for the other team services, stakeholders, so that can have like detailed reporting or insights, KPIs, metrics, hot water, cold water, whatever they want. Basically, we try to kind of make it real. About my background, I started as a C++ developer for a real-time bidding system. So it's basically advertising system that you connect. It's like Wall Street, but for advertising. So you basically do bids in real time for an advertising spot, and in a matter of seconds, you fill these spots, you run an auction, and the guy who is willing to pay the most basically fill the spots with his advertising. Yeah, so I was basically working on the technology that allows to make the auction and also enrich the ability to make the bid for the people who are willing to make these bids, so give more information and context about the ad spots. Yeah, I've done this for roughly 5 years. Then I moved to data engineering, which is kind of closely related to this, because to provide information to be able to do a proper bid, you need to know what kind of information you have and run some analysis on top of it. I switched from C++ to Scala and yeah, functional programming thingy, and then naturally I kind of came into Spark. So yeah, in terms of familiarity with Spark, I know it's really hard for me to scale. I would say 2 or 3 out of 4 maybe. And yeah, I'm familiar with Scala now since I think around 4 years, and yeah, so C++, Python, all the let's say usual suspects. I do a bit of Ruby, although I hate it, so I wouldn't even consider that I'm really familiar with. It's like the mother-in-law, you know, you have to see her, but really like her, but it's okay, you have to do it. Something non-technical, that's a good question. I like climbing, rock climbing in general. Cycling as well. Yeah.
I've always remembered. Interesting about Ruby is that Ruby has that effect. People either love Ruby or they hate Ruby. I've done a lot of Ruby, and I'm not sure if I like it or not, but I do it. I respect it. So we've got some good programming languages here: C++, Scala, Ruby, Golang. One of my personal favorites right now. So very good. Okay, thank you. So we've done Gregory and Michael. Robert, you're up next.
Yeah, my name is Robert. My background, so I left Hungary. I'm originally from Hungary and started studying in Germany as computer scientist. I finished too soon and I got the offer to do a PhD. So I stayed for a PhD at the data management chair. And after that, I wanted to see the world, world meaning Germany. So I joined consulting companies, and there I was able to work with many different people in many different companies, and exactly as you mentioned, pick up the best practices, and always try to get to the next place where I'm not the smartest in the room, but there are other smarter people to learn from.
Absolutely.
So I did that for roughly 5 years. And worked in anything that's data related. So from backend ETL processes up to front end, and even building a reporting tool that some clients even use today. So yeah, and after that I decided to not travel anymore, also because of private reasons. And then I joined Credityx as a data engineer. Soon I became a senior, and recently I became the team lead in the data team. So our goal is to provide the data as soon as possible to all our users, and make sure that we scale for more customers. Technologies I'm familiar with, well, during my phase as a consultant, I worked with basically any database system that's available in the market. So just name it. Most likely I did some work with it. And I really like to write SQL. That's one of my favorite. And from programming side, I started with C++, built actually a database management system in C++ back at university, and then jumped into Java technologies due to this consultancy work. And at Creditix, I had to learn Ruby then, which actually I like. And there are also other languages that I had to pick up at Creditix, like Go and some Python. And recently we moved into Scala and Spark for revamping our data pipeline. So familiarity with Spark and Scala is more in this 2 and 3 section. I would guess more in the 2 area. Since we had to develop our knowledge ourselves within the company. That's also why we are asking now for a training, so we get a better overview. And some non-technical about me. Yeah, I mentioned it at the beginning. I really like to eat. That's the thing I did while I was a PhD student. I also learned to cook because the food was simply not good enough in the town I was living. And I even brought it to the level that I worked in Michelin-starred restaurants. But then I decided to continue on the computer science path because it's more family-friendly. So that's also the reason why I moved into Berlin, where Creditix is operating its IT department, because it has just the best variety of really good food in Germany.
Oh, really?
Yep.
I'll have to remember that if I come to Germany to, if I want food, to go to Berlin.
You have to go to Berlin, yes. But there are other cities as well with good food. So.
Yes. Well, I'll keep that in mind. Okay. Yeah. Okay. Good. Thank you very much. And I think now I do not know how to pronounce the next name here properly. Evgeny, or can you pronounce?
Hello. The closest you can pronounce is fine, but the proper would be Yevgeny. It's not that easy.
Okay.
Yevgeny. Yeah.
Yeah. I never know how the G's come out and stuff. So Evgeny. Okay.
Yeah. So I started doing some basic web pages with PHP like 15 years ago. Found after some time Ruby, loved it. After that, spent a lot of time with different technologies, trying new things, experimenting. Some years ago, joined a company who was developing mobile video games, and it was a lot of fun to be responsible for backends of these games, especially involving some game mechanics like calculations and other stuff. 2 years ago, joined Creditix, learned Scala somehow a bit. And currently I'm in a situation where I'm exploring the possibilities, so exploring new fields like data fields. Maybe it could be interesting for me. And in past few months also completed Scala, functional and Spark stuff on Coursera, which I found very interesting for me.
Oh, good. Was that the David Odetsky's course?
Yeah, I think so. It's from the creator of Scala, at least first 2 parts. Yeah, it was amazing, especially his explanations of how language is designed and how it's
Yes, and that's
work.
one of the things we're going to be getting into, so that should be familiar ground for you.
Yeah, and so if my familiarity with Spark would be around 1, I say, and non-technical stuff is I really into ping pong these days. I never suspected that this is possible, but it's amazing.
I'm sorry, what was that?
Ping pong, table tennis.
Pong.
Yeah.
Really? Okay.
It sounds silly, but it is. It is fun.
Okay, I know that it has a wide fan base in Asia. You know, ping pong stars over there are like rock stars. So
Yeah, I guess so.
So if you ever want to go professional, go to Asia on that one. Okay, thank you, Gerald, how about you?
Yeah, hi, I'm Gerald. How I started, I was going to university in Potsdam, so pretty close to Berlin. In this time, probably I did more data engineering or kind of information handling and so on than in my whole professional time, I would even say. So got first contact with Hadoop and these kind of things, things that were kind of the basis for stuff like Spark and so on. And during that time and also after university, I was mostly doing web-based applications, not so much, let's say, rocket science, rather the basic stuff.
Mm-hmm.
And I joined kind of Cryolytics 6 years ago. Basically, I joined a company that was acquired by Cryolytics more than 3 years ago. And I'm still working on this application that was brought into Cryolytics. Then we also have some Spark component written partially in Scala, partially Java. It's a little bit of a black box, so editing and changing things there is a little bit difficult, and sometimes the results are surprising. So that workshop should help in this direction to understand it in a better way. The general application is more, again, web-based application based on Java, Postgres, Elasticsearch, these kind of things. And what else? In between, I also got into contact with Ruby, Scala as well a bit, and my familiarization with Spark is probably at 2, I would say. And non-technical. I guess the reason why we start the workshop today is because of me, because I just returned from vacation.
So you're the cause. All right. Well, I'll have to. So you're the guy I have to make happy. All right. Good.
I'm pretty sure that will.
Okay, Roman, how about you? You get the last one here.
Okay, we have a couple more people.
Okay, they're not on my list, so you can introduce them as we go along too here. I'll have them introduce themselves.
I think they're pretty capable of introducing themselves. So let us just start with me, and then we proceed with these people. So my name is Roman, and I started off as a developer like more than 12 years ago. It has started off with supporting of a web-based application, mostly PHP. So this is the kind of experience I'm not proud of. Then at some point I decided to switch to Ruby because I'm in the love Ruby party here. So I kind of love this language. I'm impressed by its simplicity and yet powerfulness. I joined Cryolytics this year, actually beginning of this year, and my title sounds like well, it's complicated. It's engineering team leads, application development, something. Anyway, what my team is doing is we're developing one of the tools that is intended for our digital marketing to automate their some of the stuff they're doing. And right now the focus of the company changes a little bit, and we have to change our focus as well. And one of the opportunities that we're exploring is moving more towards, from application development, more towards the data processing. So as far as I'm aware, all team members are, Evgeny is actually one of my team members. And actually, all of my team members, as far as I'm aware, are particularly interested in the data processing topics. So we started to explore these opportunities. I have also started going over the Coursera courses on Spark and Scala. And unfortunately, I haven't finished, but I also share the same feedback as Evgeny had. So I really find them useful and pretty much clear to understand. On the scale of 1 to 4 of my familiarity with Spark, it's between 0 and 1. So I have just only started, I haven't completed it yet. And yeah, it's actually a nice thing to me that we're going to touch upon some Spark basics on this course. So yeah, this is really awesome. Fun fact about me, well, my favorite ice cream flavor is stracciatella, if anyone is interested. And I live in Germany for almost 5 years and haven't managed to learn German yet.
Oh, that's an impressive feat.
Depends where you live in Germany. You don't need to.
Well, you see, I live in Canada in a bilingual part of the country, and I moved here from an English-speaking part of the country, and I have learned French to the point where I can sit quite comfortably in conversations and could contribute if I want, but I find it's more to my advantage to make the people think that I don't understand French. Particularly when I'm in meetings. I learn a lot of information that way when they talk in French thinking I can't understand. So I understand that. Okay, so now there's other people there who I haven't hit on, so maybe we could have somebody introduce himself who I haven't mentioned so far, because I'm making notes here.
There's two more of us. So
okay.
I'm a data engineer at Analytics. I've been in this role for the last 3 years.
I'm sorry, what was your name?
Manu.
Manu, okay.
And yeah, so I'm working with Gregory and Robert on the data team. So I recently joined the efforts of building this data pipeline and data warehouse in the cloud using Scala, Spark, and so on. In that sense, my familiarity with both technologies, Spark and Scala, is not super good yet. I'm catching up. I would say 1.5 at best. Mm-hmm. And besides that, well, I had contact with C and Java in ancient times. More recently, Python, Ruby, a little bit of Go. But yeah, so I would say I'm mostly a Python developer, and again, trying to become a Scala developer as well. So yeah, and ice cream, well, I would say pistachio.
All right. Fair enough. All right, thank you. Next person? The other person?
Okay. I'm the last one. I'm Yorgos. I'm coming from Greece. I've been in Analytics for the last 2 years. The project I'm working on is relatively new. We're doing Java mainly. I completed a course in Coursera regarding Scala back in 2013. Yeah, my familiarity with Spark is 0. I just saw some YouTube videos and I started reading this online book. And some non-technical about me is that, yeah, I also like biking, I like swimming, and I'm gonna try to complete my first triathlon next year.
Okay, excellent. Sounds good. All right, thank you all. I appreciate that, and we can get down to it. By the way, that marathon's interesting. My brother-in-law is a triathlete, and his son, my nephew, actually just set the Canadian record for the, or actually set the Canadian record for the, a number of years ago for the under 18 triathlon in Canada. So they're always off doing Ironman and all that kind of stuff. So I can really appreciate how hard that is for people to do. Okay, there's a couple of reference books here, and I will actually be referring to some of the high performance Spark material next week to give you a bit of a reference there as well. So you can follow up with the class with that. And a couple of other just final points, and then we'll get right into it. I'll give you my contact information. Best way to get a hold of me is by email. I'll type that into the chat window right now. That's generally the best way to get a hold of me. If there's any kind of issues, I generally tend to monitor my email fairly regularly. The slides will be emailed out or delivered. I will probably see about just putting them into a GitHub repository or something and letting you just pull them down. The labs for the same things will be on the nodes that you'll get. You'll also be able to get all of the lab material as well. And a little bit later this morning, we're going to set up your nodes that you'll be able to work on, and that'll be just a bit of an administrative overhead. I think we don't have enough, so I may have to spin up a couple more instances, but we'll sort that out as we get there, and we'll do some walkthrough on how to actually use that material. And I think that's about it for logistics. Typographic conventions, fairly standard boilerplate stuff. Basically, we're going to have examples of code as we go through. So there's different fonts that we use on there. And so we'll end up that session and we'll carry on and we'll do questions as we proceed. Let me see here. Now I'm going to start off actually with the Spark intro and then go back to Scala. Simply because a number of people we want to sort of understand where Spark fits into this ecosystem first. So I'll just take a moment here to load up. I have this Windows computer I do this on for presentations. I don't normally use Windows, but Zoom and other things only run under Windows. So it's sometimes a little bit frustrating for me. I really hate Windows. Okay, so what we're really going to do, and we won't install Spark, I just want to go over the first part of this to give us a conceptual overview as to where Spark fits into the whole technology ecosystem. So let's jump into that. The particular thing we want to focus on is what Spark is actually intended to do and what its capabilities are, and then we're going to go back and look at Scala, because then we can see how Scala and Spark are related conceptually. I think if we just jump right into Scala, it's a little bit, it's not as conducive to learning when you're not making those connections between Spark and Scala right off. So I think it's useful for us to take a little look at Spark as we go before we start. The Spark comes out of the big data world, and it is built on some gaps in the needs that existed in the big data world. Big data, of course, just to clarify for the purposes of this course, is data that's characterized by the 4 or 5 V's, depending on who you're listening to. The most important ones from our point of view are large volumes of data from different sources and variety that we need to manipulate in some way. The whole notion of Hadoop comes out of a number of different projects that coalesced, merged with each other, and borrowed from each other about how do you manage these large volumes of data in a close to real-time way. Hadoop was the standard HDFS Hadoop file system, evolved as a way to manage that data. The original goal of these things was not to do a lot of real-time processing. It was to do analytics on large data sets. And the initial approach was to focus on how do we store the data, first of all, and then how do we distribute out our processing and do queries on this big data, get analytics out of this big data. The initial problem was very challenging. So the problems that weren't addressed at the time were often problems of how fast can we do this? It was more, can we do this? So MapReduce engine came up as the way of doing this distributed query analytics approach. It worked and everybody was very happy with that, but it was originally developed from a batch processing perspective. Then that had a couple of advantages and disadvantages. So while we were now able to process large amounts of data, we had the MapReduce bottlenecks, and a couple of problems that emerged with that where the batch processing model that was used did not fit all of the needs that we wanted to apply this kind of approach to. In particular, we had high latencies for small to medium data sets. In other words, it didn't scale down and give us a comparable improvement in performance that we would expect to see. So there was a bit of a problem there with it was designed for high volume, large amounts of data. It didn't tune well when we wanted to look in other environments. So it's not a solution that matched every volume use case for data. The other problem was that it was processing data at rest using batch processing. So it was not really applicable to some of the needs where we're wanting to process streaming data in real time. And because everything was done in terms of disk writes, the bottleneck in performance was often the disk access, disk speed, and there was a difficulty to optimize the performance because of this bottleneck that existed with this reliance on reading and writing to disk. It also had a programming model that was somewhat user unfriendly. It was very difficult and verbose, but again, in all honesty, this was the first attempt to solve this problem, and it actually solved it in a fairly elegant way, given that there was nothing before that that did that. But it also showed there were certain deficiencies that needed to be addressed. Spark is a tool that was not intended to replace this approach, but was rather intended to sit on top of it and rectify a number of these deficiencies, more to fill in the gaps than to do any sort of replacement of what was there. So Spark is not saying this is the wrong tool, or we need a new tool. Spark says this is a great tool, but you know what? It's not addressing certain issues, and we're going to address those particular issues. I have no idea about this cartoon, where it came from or anything. So, but it's in the slides. But Spark comes out of a number of different approaches. Again, in the industry, so Microsoft and Hadoop and Microsoft Labs, and everybody's trying to solve this problem. And we do know that there was something called Dryad. Dryad was, again, as you see there, the Hadoop killer, the original approach to say, well, let's get rid of Hadoop and put something else out that works. And I believe this was at Microsoft. So it was better in software, but I think what happened was Microsoft in their wisdom realized that trying to replace something that was getting a large amount of attention and focus in the marketplace was probably not a good idea. There's probably other reasons, so they killed the project. But a lot of the ideas that were developed were recycled into Spark, and that became an Apache project and took off and refocused itself from being a Hadoop killer to being a Hadoop colleague that worked along with Hadoop. So I think in the class, we will be working with Spark in a Hadoop and a non-Hadoop environment. Spark is intended to be a computing engine. It's not intended to be a big data storage system or anything like that. It focuses on the computing option. And the way it does that is with an architecture that focuses on using memory. Now, next week, we're going to be talking about things like Tungsten, which was where Spark has a number of subsidiary projects which are optimizing the in-memory operations of Spark in order to make it even better, in order to make it even more powerful. The disk operations are then optimized because there is a better relationship between what's going on in memory and what needs to go out to disk. So whereas MapReduce is entirely, or not entirely, but primarily focused on reading and writing the data, the Spark it takes a different approach and talks about how do we maintain data in memory in a way that we can get much better performance. Also, Spark tried to address the issue of streaming data, and this is very important for real-time analytics, machine learning, particularly when you're responding in real-time environments. If you're doing security analysis, trend analysis, there's a number of things you want to do in real time. You don't want to wait till tomorrow to get responses from that. The other approach that Spark took was to say, we don't want to create a new ecosystem. So what we're going to do is not replicate what's already there. So we're going to be compatible with Hadoop, and the cluster managers like Mesos and Yarn work and run in a standalone mode. So we're going to work with a number of other types of storage and data processing engines. So rather than try to force people to choose between Spark and these other things, let's focus on what Spark is actually going to do and where it can contribute into this ecosystem. So the idea here is that Spark is intended to be a tool that enhances the use of all of these other products. It's also based on Scala, and when we come back and look at Scala, we'll see some of the ideas of Scala translate very nicely into a processing engine, which give us a very, very elegant way to think about how to process the data. So now Scala, of course, comes out of Berkeley, officially after borrowing some of the concepts from Dryad, now a top-level Apache framework or project, and is now achieving a high degree of popularity because it fits those specific needs. A couple of people in the ecosystem is, of course, Apache, where it's got a lot of open source support. Databricks is a number of Spark creators. So there is actually a professional group or a corporate group committed also to supporting and developing Spark. So there's that interesting fusion between the open source community and a corporate community. The Hadoop vendors like Cloudera are also realizing that by bundling Spark, it enhances the value of their product so that Spark now goes along with a number of those distributions. And like Ruby and its gems, or Python and its packages, or R and its packages, there is a large community index of Spark add-ons, and I think that's... I think I had that linked. We'll take a look at that a little bit later. So the idea too is that once you get a large community of contributors involved in bringing various kinds of packages that solve certain kinds of problems, you increase the overvalue of the platform. So this is that open architecture. That means that adopting Spark allows you to have access to a number of packages that do things so that you don't have to build things from the ground up. As we know in Python, and especially if you've done any machine learning or data analysis in Python, you know that because there exist packages like pandas and other very specialized packages, you don't have to invent things from the ground up. So this makes this whole thing very, very attractive. So why is Spark popular? Well, it's again, it's not an attempt to create an entire ecosystem. So it is a relatively a compact package. It's elegant in the sense it's easy to get up and running. You can deploy it in a number of different environments. It doesn't depend on a particular technology. A couple of other nice things about it is that it has a number of programming interfaces so that it can interface with a number of different development environments. And they've divided it down into developers and data scientists here by language. But generally, we're going to focus on Scala in the course. And my personal opinion is that you really are able to get more performance out of Spark. You're able to use it more effectively with Scala because you're thinking using the same paradigm that when you're programming in Scala that was used to design and encode Spark. So there's a natural relationship there. High performance plays nice with big data ecosystems, and you can pretty much use it out of the box. And the thing we're going to focus on a little bit more this morning are these functional programming constructs and concepts. We're not going to be so much interested in the other kind of applications. The job trends from Spark just give you an idea of its adoption rates. So as of 2015, you can see there was a bit, by the way, that big spike, I think, is because there was that new release of Spark around that time. But there is obviously a trending up, good measures. One of the most active big data projects, again, the spike, I think, is around one of the major releases of Spark. But you can see it's a pretty significant community. This is where things really get interesting. And one of the reasons why Spark is working is when we're actually looking at benchmarking in terms of median response times. You'll notice that Spark, because of its architecture, is outperforming most of the other kinds of products that are doing this. Now, other kind of products have advantages, but where Spark is really focused is on speed of performance in performing various kinds of queries and various kinds of data manipulations. So we are seeing this sort of high performance turnaround, which is what makes it really, really interesting. You'll also notice the difference between Spark, where we're using a lot of disk access, and Spark, where we're emphasizing memory. Even with the disk access, the architecture of Spark is producing significantly better performance than the other products. And once we move to a more of an in-memory model and emphasize the in-memory model, then our performance improves even beyond that. So this is the kind of performance issue that makes Spark so popular. The other sort of thing we look at is the usability portion in terms of code size. So we have large amounts of code for other products, but we, again, partly because of the functional emphasis, have a small amount of code that performs the equivalent function in Spark. That, again, comes from the idea that most functional programming languages actually do more in fewer lines of code. The challenge we're going to look at today is how do you think in a functional programming paradigm. And for those of you who've done Odetsky's course and other things, you notice that it does require you to think differently about how programs work. All right, so there's some noteworthy features here. So again, we got that initial release in the Apache project. There was 2.14, there was that big bump up. And there have been a number of incremental improvements in Spark. The original version of Spark uses something called a resilient dataset, was a really interesting innovation, but it still wasn't as good as Spark could be. So subsequent releases of Spark introduced something called data frames, which improved performance even more. And then we moved into something called data sets in version 2, which provided an even better model for working with data. And so the evolution of Spark has been along the lines of improving the ability to structure and manipulate data and get improvements on that basis. Here's the Spark architecture in terms of how it fits on with other environments. Down at the bottom is the data storage layer. And again, one of the questions I hear people saying, well, should I do Hadoop or should I do Spark? And the answer is, well, that's an irrelevant question because they are designed to work together. The Spark itself is intended to cooperate with a cluster manager, which is of course, the type of application that manages the distribution of work and other tasks on the various clusters. It also has a standalone manager as well. So it can actually work directly with HDFS and other environments. The idea is that the Spark core delegates or does not try to duplicate any kind of the work that's already being done in this at this layer. It is intended instead more to sit on top of it. Once we have the Spark core, there's a number of packages that get plugged in on the top of Spark that now are able to do various kinds of tasks or adapt the Spark engine to tasks. So Spark SQL involves us being able to use SQL in Spark. Spark streaming allows us to be able to work with streaming data. Machine learning library, again, gives us a machine learning component that sits on top of Spark. So rather than have Spark do all of those things at its core level, those are broken out into individual modules, similar to the way that you can think of Python as having packages or Ruby as having gems that encapsulate various chunks of functionality that have certain applications or are applicable in certain ways. So in terms of its overall architecture, what we're really going to be focusing on this course is this Spark core piece, with maybe some reference later on in the week to a couple of these other modules. And we'll also be interacting with a number of these other components as well. So the idea behind the unpluggable storage is that you want to have Spark freely able to use all these different kinds of storage mechanisms. You also want to be able to integrate with various cluster managers. In the absence of a cluster manager, it does have its own standalone manager. Cluster managers meaning the thing that coordinates the various clusters in our data storage environment. And the thing that, again, we're really coming back to here is the distributed computing engine, which is the focus of this course. And then the Spark components, which are the modularization. So that's the idea of the Spark, excuse me, of the Spark architecture. Spark has a couple of features that are important to emphasize. The one is that it has things called task schedulers and memory management, where tasks are units of work that can be done on a particular node without having to reference other nodes. And part of the optimization is going to be looking at how task schedulers work and how we do things called shuffles, which is where we have to reorganize data on the nodes in order to do an appropriate sort of computation. We're also has this memory management model, which again we'll get into with Tungsten, to look at how memory management is being optimized through the use of some innovative ideas. Fault recovery, this is an important thing. So we want to have a complete failover, transparent failover ability, so that if we do have a failure of a node or we have a failure of a partition of data, we're able to fully recover that without any kind of downtime. So we're going to talk about fault recovery and the interfaces to the storage system. So we're going to get into each of those kinds of ideas as well. Spark uses a couple of representations of data, and these have evolved over the years. So each one sort of builds on the other or complements the other. We'll look at each of these. RDD, resilient distributed data sets, that's RDD, data frame and data set, and each one of them introduces innovations which allows Spark to process even faster. So the idea is that the data model and how it is being distributed on parallel is going to be opaque to you, more or less. That's going to be all delegated out to how we take one of these resilient data sets, distributed data sets, and how it is getting distributed out there should not be of a concern necessarily to you when you're focused on the processing of the data, although there will be considerations that you have to take into account. This gets us the parallelism. And the other idea is that we can create these RDDs, data frames and data sets, from various kinds of data sources, just not an HDFS input source, but we can create it from text files, from in-memory data. We can do, the idea is that Spark doesn't really care where the data comes from. What it's interested in is putting it into a form where we can get this high degree of performance. And we'll interact, of course, with the APIs on that. So the components that we're looking at are structured data, where we can support SQL types of operations. And for that, we can take any kind of data that's structured in basically an underlying key value pair kind of model. So you can argue that tables and SQL tables are sort of the idea of a highly structured key value pair. So Hive tables, SQL tables, JSON data fits into the same category, CSV files, anything that would be representable in the spreadsheet, Parquet, which is another data format. So the Spark SQL is a module that works with data which has a particular kind of structure to it that's familiar to us in the QL language worlds. Spark streaming is manages a different kind of data. So you're looking at things like the example, sensor data, in particular, Internet of Things. So there's another general application area. I do believe that's not something we're going to really touch on much in this class. Machine learning at scale, again, requires massive amounts of data processing often. And we might mention some of the applications, but we're not going to get into the machine learning at scale. But again, notice that these are very different application areas, so we don't want to put them into the Spark core. We want to keep these as add-ons. And GraphX and graph manipulation is again another big area that's out there, using graph data sets and looking at associative relationships and other sorts of things. So there are a number of different components that get built on top of Spark. Okay, so you should get basically an idea here that what Spark is this core, which we're going to look at, which is this model of how you process data quickly in real time and manipulate data. And that is going to talk at the lower end to the various data storage systems, data availability systems. And then on top of that, you've got these other modules which are going to add functionality for particular application domains or particular kinds of data processing that we're doing. Okay, so that's the first really big takeaway, is just get a sense of this architecture. The modules are also what we call tightly integrated, so that they work in a very, very seamless fashion. Now, I'm not going to claim that Spark is the only stack you need, but because it runs as standalone, it could be the only stack that you have. But I will leave that as a debate to purists as they want to go through that. This is a table I'm not going to spend a lot of time on. Just basically, somebody's divided this down into the two kinds of approaches that people take looking at data. The data scientist versus the data engineer. The data scientist is focused on the data. The data engineer is more focused on the infrastructure that surrounds the data. I think that's how they've kind of broken this down. So again, building a data infrastructure versus ad hoc exploration. So a couple of the ideas here is that they're probably using different kinds of shells. Data engineers often use things like R. And the other thing we want to be able to do is to leverage existing libraries and work that are there. Interactive development, again, short turnarounds for data scientists when we're doing ad hoc exploration, and again, the reuse of being able to use programming languages. A couple of the use cases where it's actually being used. I'm not familiar with the details of some of these, although I do know I have heard wonderful reports of what people are doing with Spark. So Teralytics, telco data. This is an example of using more large amounts of data. This is really important for phone companies because what they have to do is telco resources at a hardware level are actually very expensive. And being able to actually predict usage patterns enables them to be able to do very, very effective cost planning. So, for example, estimating usage patterns to enhance coverage. One of the things that they know in North America, for example, is that all telcos know that the largest number of long-distance phone calls are placed on Mother's Day. So on Mother's Day, you have to make sure that you can handle the stress of all those extra calls. And they also know that the largest number of collect long-distance calls are placed on Father's Day. So having historical data to enable them to know that enables them to be able to respond to those effects. And we get various kinds of peaks. So for example, we also know that on an average day, the two peak times for making phone calls are generally right after the start of business when people return calls, and just before the start of business when people start calling home. So we know that by analyzing data. So now with Spark, you can analyze these 180 billion events per day in a much more effective pattern and get your patterns to become much more accurate with better levels of tolerance. Yahoo is another example. And this is actually a fairly impressive number, 15,000 lines of C++. Now, somebody said they had built originally a database in C++. I actually did the same thing too with my team back in the 1980s. Relational databases were incredibly expensive. And we got some stuff from MIT AI labs that enabled us to write a really sort of primitive relational database in C++ because we couldn't afford the $15,000 a license everybody was charging at the time. So I understand how difficult it is to write some of these things in C++. I do love the language, but yeah, 15,000 lines being reduced to 120-line Scala program, that is a real performance booster. Spark took 30 minutes to run 100 million samples. That, again, is pretty important. News personalization is, again, looking for, this is probably going to be a machine learning system doing some kind of recommendation system. Genomics, we've really gotten a lot of stuff done in the biology world because we have the computing power to actually analyze very, very complex sets of biological data. So millions of genomes, billions of combinations, it's only through the use of high performance computing in Spark enables us to actually do this kind, I shouldn't say us because I'm not doing it, but enables people to do this kind of genomics. What people can do with genomics now is absolutely astounding. And that is really built on the ability to be able to process these large amounts of data. Netflix, this is where Spark is sitting on top of Cassandra, analyzing streaming events and doing recommendations. When I do have time to go on Netflix, the recommendations are always wrong, but that's because I'm probably not using Netflix right. But again, these recommendation systems in various cases are not just the ability to collect the data, but also to analyze the data very, very quickly and not having to write massive amounts of code to do it. So the key leverage around here is not, oh, here's some really interesting cases. What we really want to take away from this is a lot of these cases are possible to be able to deliver the results simply because we have something like Spark that allows us to be able to do this in a really effective and elegant manner. Example, the Chinese social network, 8,000 nodes, 400 terabytes of data. I think that's just mind-blowing. Alibaba has a 1 petabyte job doing a single job of 1 petabyte. This medical images at Genelia Farm, again, massive amounts of data. And while the storage systems at scale can manage this data, it's the idea of the Spark model gives us the power to do that. There's one other architectural thing we'll look at here just before we get into a little bit and do a little bit more, and then we'll switch back over to Scala. And this is called the Lambda architecture pattern, which is an interesting approach which tries to leverage the strengths of these systems in multiple environments. It is a pattern that Spark works really well with, and it's a pattern that's becoming increasingly important. And this is where we're trying to work with and this is a problem we found in but in data warehouses as well historically, where you would have all this data go into the data warehouse, but you were only able to query the stuff that was there and not the things that had happened since the data was loaded into the data warehouse. You had this real-time component or this accumulated margin of data that you had to wanted to get access to. So the Lambda architecture works where we have split down our data into two kinds of storage streams. One goes into a batch layer, which is our master data set, which can be considered to be the accumulated repository of the data. And that can go through various kinds of processing models to produce a serving layer with different batch views that can be queried. And that would be a typical historical kind of data warehouse approach, or a more ETL type of approach. And then on parallel with that, you've got the speed layer where new data is also, in addition to going to the master data set, is also being put into a very fast real-time view of the data, which you can also query. So your queries can now incorporate both real-time views of the data and batch views of the data to give an integrated, up-to-date model. So the idea is to split the data into two, so we call them holding areas, and then being able to run an integrated query on the two holding areas. This is called the Lambda architecture, although I gotta tell you, I'm not exactly sure why it's called the Lambda architecture. That's just the name somebody came up with. But I'm sure there's a good reason for it that I just haven't found it yet.
I can give you an explanation, because you basically have two branches, and the lambda letters has two branches actually.
That is a good That's a good explanation as any. Okay, so that I will go with that. That's a good. I'll go with that one. Okay, but as you can see, this is an architecture that solves a number of sort of problems we have in trying to deal with both historical and real-time data at the same time. Thank you for that. I appreciate that insight. Okay, so this is the challenge that we've got here. In that kind of architecture is, again, how do you integrate these two disparate kinds of data holding areas, and what Spark does is, because Spark is basically has this kind of unique data representation model, it is able to actually process the data by integrating both the streaming view and the batch view. And if we get a chance, I'd like to maybe see if we can come back and touch on a little bit more about the Lambda architecture next week, because I think there's some interesting ideas here about how data actually can work in terms of designing data applications. And so here's where Spark actually is able to fit in all of the different bits and pieces where it's creating views of the data that it can work with. So we'll come back and revisit this at a particular point. So here's, again, where we wind up looking at a real-time architecture. So we've got Kafka, which is pulling a lot of real-time events in. It's going to the Spark streaming module, which is able to then work with the data in a couple of different representations in both the persistent world, or I should say the batch world, again, typical HDFS type of application, and also create this immediate representation using something like a NoSQL database with the data, and able to actually do the queries in real time and batch queries. And we'll come, like I said, I'd like to come back and take a look at that a little bit later on. Okay, so the last thing we'll do in this is just look at the Spark versus Hadoop. There's our Spark timeline again. This is I couldn't figure out what this thing was until somebody pointed me back to those old commercials where they had those two actors going, "Hi, I'm a PC. Hi, I'm a Mac." And I'm not particularly thrilled with this representation, but this is the part that's really interesting here, and I think is important, is that if we look at the amount of coding required to actually do various kinds of processing in a Hadoop system, and again, I have to go back to say, this was Hadoop. We can't underestimate the innovation of the innovation that Hadoop made. So it was the first one really that made this available. So it obviously had some areas that needed a little bit of work, and this is one of those example of the areas. So we've got this, I believe, yeah, this is a Java implementation of a Hadoop performance, and down there in Spark, we've got the same equivalent code being represented as a couple of lines of code. Actually, if you put it out, it's actually one long line of code. So we're not saying here that Spark is a better programming model than Hadoop. What we're saying is that because of the tools available in Spark and because of the way Spark is structuring the data, we can take advantage of more elegant programming models. And I don't know about you, but I kind of like the Spark implementation here a little bit better than the Hadoop. Comparison side by side, and this is something that people often want to be clear about, because again, if you're new to Spark, the question is, well, Hadoop versus Spark. I think we made at this point clear that they do two different jobs. Even though Hadoop does some of the stuff Spark does, it was never intended to be a Spark kind of engine. It was really focused on how do I actually distribute and work with data in a large scale environment. So it's really focused on distributed storage and then adding computing on top of that, whereas Spark doesn't care about the computing, so it doesn't have storage. It doesn't have to worry about that whole layer. It delegates that off to Hadoop. So it's riding on top of Hadoop and other storage engines. It uses a MapReduce framework. That's the model that came up with it. So you're locked into that model. And again, that's not intended as a criticism. That's just the reality of the situation. Spark is looking at more of a generalized computation, so it's not locked into that model. Hadoop, again, is focused on the disk. So it's the HDFS, again, a very significant innovation. But Spark, because they're not having to worry about building that model, can actually use a different kind of model that focuses on in-memory and its relationship to on-disk. And we'll mention Tachyon as one of the projects that is associated with that later on. We get into optimization. It's not, Hadoop doesn't work for iterative work because it's primarily a batch processing, which was how it was originally intended to work. So it works great for that particular objective. But Spark is designed for the general purpose, so it looks at the iterative workloads, and again, because of its memory model and how it's structuring data, it just works faster. The Java is the core programming on Hadoop, and Java is a great programming language for what it does, but again, as you can see, it can be very verbose. What Hadoop does is, because it employs a lot of the functional programming concepts and model, it winds up being a lot more elegant to program in. And Hadoop doesn't really have a shell, so we have to have things that build on top of Hadoop, whereas I keep wanting to say Scala instead of Spark. I have to keep watching myself. Where Spark has various kinds of shells, so and we're going to work in the Spark shell as we go along. And I think there's just the arguments we've been made. I don't think we need to beat that to death. Compared to MapReduce, though, Spark is a better fit for small gigabytes to medium gigabytes of data, simply because it manages the data in a more effective manner than MapReduce. Here's a couple of benchmarks. So Spark won the, world record large scale sort. So versus Hadoop and Spark, and we've got elapsed time 72 minutes versus 23 minutes. And we've got a sort rate here of 0.67 gigabytes per minute per node, and here's 20 gigabytes overall. It's terabytes per minute, so you can see we get performance enhancements. So it's not just theoretical. We actually see this model, and where that performance is coming in is this gap here, where we're actually, instead of doing a chunk writing to disk, doing a chunk writing to disk, we're doing a computation, and then we're caching the computation in memory if possible, sometimes spilling into disk, and then doing a computation again, so that we wind up being able to streamline the approach with options to be able to save to disk at various points. And we also have the stack support. So we can work with a variety of these particular technologies. And again, we're not going to get too much into it at this point. These slides are basically kind of driving the same point home over and over again. This is the big thing that you want to take away from this: is Spark is complementary to Hadoop. It doesn't replace Hadoop. It does replace some of the things that Hadoop tried to do with it, that were kind of not add-ons, but kind of ancillary to the storage model, which in terms of that is particularly the programming stack that's on top of it. So Spark sits on top of the HDFS, manages it, and can operate through a number of the various distributed operating system cluster managers that are out there. So the idea is Spark only does what it has to do. There's a number of different ways we can actually run in different environments. Spark can query Hive tables directly, for example. It can run Pig using the Spork project. It can work on Yarn. So it does a number of things. So that's basically kind of an idea of the kind of overall idea of Spark. We're going to come back and install Spark a little bit later today. Let me see. Let's check on my times and things. So at this point, I'll ask any questions. Everybody doing okay on this?
Do people still use Hadoop, and why?
Yeah, people still use Hadoop because it got a wide distribution there, and I'm not sure how how much of the market share Hadoop has got, but basically the Hadoop model is extensively used. And again, I'm sometimes I find it, I'm in so many areas I find it difficult to keep up with what the current market leaders are in some of these things. But generally, yeah, when I'm talking to a lot of clients, I do see a lot of Hadoop installations because it kind of went with it, and now they're just kind of sticking with it at this point. And there's talk about doing other things, but yeah, I am seeing a lot of Hadoop out there. What's your take on that?
Well, Spark is like tens of hundreds times faster, better, cheaper, whatever. So Hadoop should die from.
Well, basically, I think again, this is the point: is where Hadoop is primarily being used is as a way to store data in a distributed environment. And so Hadoop is, I think what we're actually seeing in the marketplace is where Hadoop used to be sort of the complete solution. When it was the only one in the marketplace, it is now more of a storage solution. While there are other competitors out there for other large-scale data storage solutions, but I think where we're really seeing the transition is people, instead of doing the actual analytics using Hadoop and the tools that are tightly coupled to Hadoop, they're starting to use Spark on top of Hadoop to get, as you said, the speed of processing. So I would say that Hadoop is out there a lot. People are committed to it for a couple of reasons. Number one, it's their storage solution, but in those cases, they're often bringing Spark in as a processing engine on top of Hadoop in order to replace the Hadoop MapReduce component and get better processing in that sense. And I do know that there are other large storage solutions that are sort of out there that people are switching to. But yeah, I would say that Hadoop is probably going to be around for a while as a storage solution as opposed to a processing solution. Does that help answer your question?
Yeah, sure. Thanks.
Yeah. And remember, Spark isn't really focused on trying to build a storage solution. It's focused on building a processing solution. All right?
Yep.
Okay. So we're going to talk a little bit about Scala and functional programming. And I think I'm going to actually use a little bit different material here. Web services, Azure. I'll give you the URL for this. I'll put it in here if anybody wants to just grab a copy of it. This should be this is the Scala by example. Martin Odersky is the guy who invented Scala. I think a couple people here have taken a look at his course on Coursera. Excellent course. He always looks a bit mad to me, but angry, but I really love his approach. He always looks like he's a bit annoyed with whoever's filming him. But the big important thing we want to, screen sharing is paused. That's not good. There we go. Resume share. Can you guys, I'm sorry. This is my problem here. Let me, I want to share my whole screen here. There we go. I think that'll probably be a bit better. Okay, can you see my screen?
Yep.
Okay, good. I am fumbling around a little bit with the tools here. Okay, so the big important thing about Scala, now we've got people with a variety of programming languages. We've got people coming from Java, people coming from C++, Ruby, Golang. There's a lovely range of programming languages there. Scala is intended to implement a functional programming paradigm, which involves a substantial change in the way that we think about doing code. And this comes from the idea that in mathematics, we have these functions, and we are able to describe an entire programming environment and computational environment using something called a lambda calculus, which is a way of being able to implement programming languages, provided that the functions have no side effects. In other words, they are basically stateless. The fundamental idea in a Scala environment and a functional programming environment is that you want to keep things as immutable as possible. And in a certain sense, well, you don't change data so much as you create a new copy of the data that has changes from the original version. So I've put up a little Scala here in my environment simply because I think it's easier to see on the screen. So one of the things that functional programming does and Scala does is it really blurs the distinction, and I'm going to mention this up first because I think this is an important point, between function and data. It basically thinks of them all as objects, and this is what we often call first-class object. And it really becomes clear when we look at the difference between a simple function that we might have. So we have def, we'll say x int, and that's going to be equal to, hold on here, x plus 1. Okay, and we'll do that. And now we've got a function, and of course we can apply the function to 2, and we get 3. And we can actually do this and we get an error. So it looks fairly standard, but there's a lot of things that are going on under the hood. And we can see this when we actually use that same keyword to define what appears to be a variable. Okay, and this is and if I do x, we get 3 again. But I'm also can describe a variable by using this notation as well. So it seems like I have the ability to do things, and in my shell to do something like that. So this is just a simple example to illustrate that things are not exactly what they appear if you're thinking about this from a more traditional programming language. So let's figure out what actually is going on here. And this is, I think, Martin in his course actually does a lovely, elegant explanation of this, is that these are basically called rewriting rules. And we have to, instead of thinking in terms of computation, we think in terms of evaluating things as you go along in kinds of rewriting rules. So in functional programming, we tend to blur the distinction between functions and data. They're all just things that we can manipulate in some way. In particular, functions are basically things that can be assigned to variables. And we'll notice up here that you start to see this in the notation here. And what we're really doing is saying there's an equal sign here, just like we've got down here. And this is really saying I'm defining this function f, or this symbol f, and I'm going to rewrite it. And whenever you see f, this function, so for example, when you see f, where do we have it here, f2, I want you to rewrite this statement as x plus 1 and then evaluate it. And that's what we're getting here. So there's a rewrite rule. So instead of thinking of this as being as creating some kind of object code somewhere off in memory, and then we're doing a call to that object code and pulling it and then executing it, what we're really doing here is we think in terms of this. It's almost like a macro expansion to think of it. Now, obviously, there's a lot more going on under the hood, but the idea here is that this equal sign kind of give you a clue that what we're doing here is we're working with this rewrite rule. And similarly here, we're saying whenever you see x, for example, when I use it here, rewrite it as 3, and in this particular case, I get 3. So this def is basically defining the stuff on the left-hand side of the equal sign as the stuff on the right-hand side, and it's saying whenever you see the stuff on the left-hand side, rewrite it as the stuff on the right-hand side. Now, the val is a little bit different because it's not getting a rewrite rule. And this, by the way, is something we often term call by name, in which we're doing this rewriting. Then when we get to a point, once we do the rewriting, then we do the evaluation. In this form here, we're saying evaluate what's on the right, and then then take the results of that evaluation and assign it to the variable x. So there's two different processes going on here, although initially they kind of look like the same thing. And we're going to see this as we go through in the code. So for example, let's take a look at let's define x to be 3, and so if we do f of x, we get the result 4. And if we now say, I think I can do it this way, f equals to 5. Okay, whoops, that's sorry there, the way I've defined it. So let's do a var x equal to 1. Let's do f of x. Okay, and x is equal to 2. And the point here is that if I were to go and change that value of x, it's going to affect the rewriting rule. We'll get more into that a little bit later. I'm sorry, I'm just going to skip over that example. But what I wanted to do, illustrate here initially, is that when we have a value, it's when we think in terms of traditional programming distinction between functions and data, it's not quite the same. So we're going to jump to our Scala primer. Let's do one more little thing here. Def, and we'll do function g, which takes no parameters, and we'll set this equal to, we'll just do a computation here, 7 plus 1. Let's see if that'll actually work. Now if I do g, notice it doesn't even look like a function call, it looks like a variable call, because now I've rewritten g as 7 plus 1, and because of the def, and I wind up with 8. Okay, why couldn't I have done that with f up here when I just put f? I got an error, and the reason why is because f basically has a rewriting rule. If I look at the definition of f, here we go. It has a rewriting rule that says substitute, whenever you see f, substitute, do this rewriting rule, but rewrite x as whatever value was passed into x. So we're getting so this works as a rewriting rule, but this one doesn't because I left something out. So in this, unapplied methods are only converted to functions when a function type is expected. So in other words, we're saying, oh, there's something fundamentally wrong here. I can't implement my rewriting rule. On the other hand, when we look at g, what g is saying is just rewrite, whenever you see g, rewrite it as 7 plus 1 and evaluate it. There is no need to rewrite any of the placeholders or parameters in here. So I can freely call g without an argument list, and the rewriting rule works. Now I'm making this point because the problem that people have when they're learning Scala is that last line g without the argument list looks really confusing, because doesn't the compiler expect to see the parentheses to know that this is a function? And again, that is a result of programming languages where we make a distinction between functions and between variables. All a function actually is a string that can be evaluated, where we rewrite some of the values before we evaluate it. And once we get that idea, and we'll see that idea occurring in how Spark actually manages some of the data. Okay, is that idea fairly clear to everybody? Is that we have to think about this in a completely different sort of way from what we might be used to? Make sense?
Yes.
Yeah, yep. Good. Okay, it's a simple idea, but it has great. It has a lot of implication for it. So let's take a look at our Scala primer here. And I will come back and look at some of these ideas as we go along. Okay, so first of all, a couple of things about Scala. Is that Scala is built to compile down to the Java Virtual Machine, or a JVM. What that means is that we can run our code in a JVM. Now that is important because the heart of all the processing that's being done in Spark is being done through JVMs. And when we get into looking at the memory models and sort of things, we'll see that Tungsten works with the JVM memory directly in order to improve efficiency and performance. So what we can do is basically embed Java within Scala because it compiles down to the same thing. So Scala itself is not just a functional programming language, but because it basically has object-oriented definitions, it also has an object-oriented component. And I believe Martin was kind of looked a bit grumpy when he said, well, you know, we have to do some processing because Java is a procedural language, so Scala does it as well. That's where Scala breaks from being a purely functional programming language and incorporates some of these ideas. So there's two different programming paradigms that are going on inside Scala, but the functional concepts are the important ones in understanding what's going on in Spark. So let's take a look at a couple of these ideas here, and then we'll get a chance to look at the functional languages. So Scala programs use Java libraries. It can be object-oriented, which is useful because if you're porting code in from Java, you don't have to completely rewrite the code. You can do staged kinds of whoops, sorry, my microphone slipped here. You can do staged kinds of transitions. Hold on here. There we go. Sorry, I have these cables running everywhere, and I move my chair and it gets wrapped up in the wheels. So we'll get into more about what the functional things are, the functional aspects of the language are as it relates to Spark. But at this point, we would call Scala a mixed paradigm language. It does support the object-oriented approach with Java. So anything you know about Java, knowledge about C++, object-oriented programming, generally applies into Scala as well. But Scala also has aspects of other programming languages, like its list structure comes right out of Lisp. So if anybody's ever worked on Lisp and its elegant list structure, that's really great. It's got pattern matching that is really fantastic. It's also got a lot of the really functional components that we want to use. The idea behind functional programming is that things should be immutable and stateless. And the more we introduce state into objects as side effects, the more likely things are going to break on us. The RDD model is built around this concept of immutable and stateless. When we create one of these resilient distributed data sets in Spark, they are immutable. They don't change. That's one of the reasons why it's able to do failover. Instead, what we do is if I have a piece of data, in the example that was once given to me is, suppose I have a form that has to go to 3 people and each person has to sign off on this form. So it goes to person number 1. Now, in a typical procedural approach, person number 1 would get the form, sign it, and give the form to person number 2 and sign it, and the form is changing as it goes through each step of the process. And we can never go back and see what the form was like when the first person got it after it's gone through the process because it's changed. We can't go backwards. But what if we did it in a functional approach? Now we have a form. It goes to the first person, say it's Martin. Martin doesn't sign the form. Instead, what he does is he photocopies it and then signs the photocopy and hands the photocopy on to Robert. And Robert now photocopies that, and then he signs the photocopy and with the 2 signatures now and passes that on to Evgeny or whoever else is there. And what happens is that every time somebody does something, they're really creating a new object that they pass on. And once they've photocopied and passed on, they can either keep the original form. So when it gets to the end, it could say, we can actually go back and say, well, what did the object look like when we first started? Well, we just go back and look at the original form. We can roll backwards. On the other and on the other hand, if we finally get to the end and we say, yep, that's good enough, and everybody can destroy their intermediate copies and throw them away. So this is the idea behind what we talk about immutable and stateless. It's not that anything doesn't change. Things, instead of changing an object, we create a new copy of the object that incorporates the changes. Now that new copy is immutable. And that is the principle behind these resilient data sets, these distributed data sets, is they follow exactly the same idea. So that we can always roll back to various points. And with the ability to do that, we're able to optimize the operations that are in Scala. So this is the functional programming concept that's really important in Spark. That's really important as it applies to Spark, is this notion of immutability and statelessness. So every object only has one state. It's created in a particular way, and it's got that particular state. In our Scala programming environment, we have a condescension to that, and this is the difference between a val, which is really the idea of a functional programming object, because once that's created, I cannot change it. It is now immutable. The var keyword is the incorporation of the Java type of programming paradigm, where now if I put var equal to 8, okay. Now, at this particular point, I should also point out a point about the syntax, is that I now have two different variables t. I have the original one, which is the val, and I have the new one I've just created, which is the var. I'm not getting an error here, because in functional programming, if I was doing this in a procedural environment, it would look like I'm trying to redefine a symbol to have a different meaning. The functional programming paradigm doesn't work that way. It says, okay, you created this object T, it's sitting out there. Now you're creating a new object T, and it's going to shadow that old object T. So that old object T is no longer accessible, that you created with val. You've now got a new object called T, which is var, and that kind of shadowing effect is very typical of what we find in functional programming. However, because this is a var, I am now able to make that assignment, because now I've created a mutable object. So my var is a mutable object. My val is an unmutable object. Val is very much like a resilient distributed data set in Spark. It follows that model. It doesn't follow the model of the var, which is a mutable variable. So we have mutable variables in Scala, not because Scala wants mutable variables, but because we want to be compatible with the Java code that's in there. So there's the distinction between the var and the val. Okay, Scala and Spark. There we go. So that's one of the kind of things that we're going to see when we talk about immutable. And again, I'm stressing that because that's a point that's important for Spark. It mentioned interoperates with Java, operates on a Java VBM, so it can operate on use all of the Java libraries, and it does create bytecode. And one of the keys is that it has this wonderful compatibility with Java that is leveraged by Spark. It also tends to be a little bit more compact in its notation. We'll get a chance to play around with it. I'll go to Martin's thing. We'll take a look at some specific examples that illustrate some of the things we're going to need to know for Spark. Functions are full class objects. In mathematics, we talk about first class object. We talk about functional objects. If you've done any functional analysis, we tend to manipulate functions in mathematics all the time. We can sum up a number of functions anytime we do an infinite series or something like that, or we're summing up sums or any kind of analytical analysis. We're very used to using functions as basically data objects. And what a functional language is where we have the same ability to do that in code that we can do in mathematics. So it's a natural expression of mathematics. So we're going to see a lot of that. And that, of course, is one of the strengths of it. And you notice that idea of passing functions as arguments is heavily adopted now by many programming languages. So for example, Go is built, with its Go routines, that's built right into the design of the language. And if you're working with Python, has aspects of a lot of functional programming in it as well. Those languages are not actually functional programming languages, but they do incorporate some of these ideas about what functions can do. Okay, so we go back to the Spark for a moment. 2 core goals: work within the Hadoop ecosystem, where we're basically using all this data that's sitting out there on these Hadoop clusters. And we also want to have a very, very elegant programming interface. And we also wanted to employ, I keep saying we, I'm not going to actually do it, I'm using the royal we here. We as a community, or I'm speaking on behalf of the developers, wanted also to get a elegant programming model, recognizing the fact that we don't want to spend a lot of our time writing and maintaining large chunks of code. So the Python is a possible candidate. The problem with Python is that it does not do strict typing. It's not to checking, which means that some of the efficiencies that Spark needs can't really be done in Python effectively. So Python is not really the optimal language for working with Spark because of its untyped nature. And we've got some Java functional programming that we can kind of leverage here as well. So Scala code and programs follow the same process of being compiled down to bytecode. Scala C is the compiler, where we can basically run it the same way we run a Java code. But we also have an interpreter, which is what I'm using with that REPL to give some examples. And that interpreter also then allows us to work in a Spark environment, in a Spark shell, to do similar kinds of queries. All operations are method calls, and that's going to be something that I'll demonstrate before we'll take a quick break. Again, this is another point that you have to get used to in Scala. So let's go back into my Scala language here, and let's take a look at a couple of things that look really odd to start with. Okay, so first of all, this doesn't look odd at all. That doesn't look odd because that looks like an operator defined in a standard programming language. The problem is that that's not an operator, that's a function. And I can rewrite that as in which being able to do that and get the same result shows me something that's actually going on in the language that's not immediately apparent. This infix operator notation in Scala is syntactic sugar, whereas this is actually defined in the grammar of most programming languages as an operator, and there's an argument on both sides. In Scala, it is really just another way of writing this piece, which says, I have this expression here, which just happens to be a literal, and I can call a function or a method on that literal, which is called a plus sign, and give that the argument 7. And this would be the same as if I had written a function called add, and for an integer class, and assigned this to an object in an integer class and called the add method on it. It's exactly the same idea. So there's a couple of deep concepts here that are important to understand. Is first of all, these literals are no different than anything else. So in Word Java, a literal is very different. Like in Java, you couldn't call a method on a literal. You have to put a literal inside of some kind of construct and then call that on the construct. Or even if you wanted to do, you'd have to call some static method and pass the literal as an argument. And we've got things like the int classes to give us that kind of programming construct. Scala takes a very different approach on this. What Scala says is that everything is an expression. So everything evaluates to something. The only difference is that a literal evaluates to itself. And what Scala realizes is that when I evaluate the literal and I get the same result back, I'm done my evaluation. So when I put X in here, what Scala is really doing is saying, ooh, I've got an expression. I'll evaluate the expression and I get a 1 back. Now I'll evaluate the 1, I get another 1 back. Okay, my evaluation sequence is terminated, so the final result I'm returning is going to be the 1. So we, again, have lost the distinction between literals and variables here. They're all just expressions. Everything returns a value in Scala. Well, that's actually pure Scala. So our if statement looks a little bit different. So I can say, there we go. So I can say this, except a string, but a literal is found. Thank you. I knew it was some ridiculous error like that. There we go, because I'd already defined f. Okay. So what's happening here is that if I looked at this from a procedural point of view, what I might think is happening is that I'm encountering a control structure in the language, and I'm encountering a Boolean condition which I evaluate, and then I would execute whatever code is here, or I would, if it's false, I'd execute whatever code is here. And I would think of this as being like a framework that holds these two alternative ways of executing code. In functional programming, we think about this really, really differently. In functional programming, we're basically saying, rewrite this. And if we have if, and if this first part is true, our rewrite rule says then basically rewrite it as this. If this is false, then rewrite this whole expression as this. And in this particular case, what Scala did was that, okay, this expression, if true, high, else, by. Okay, when I apply my rewrite rule, I get this string high, then I rewrite my high, I get high back again, so I'm finished my evaluation. So it's a different way of thinking about how these things work. And of course, what I can do is I can go and assign that the result of that computation into a variable, okay? All right, so what I wanted to point out in this initial kind of discussion is just a couple of little examples to show that as we go through the rest of the Scala is that what's going on under the hood, while it might look syntactically very similar to what you're used to in other programming languages, there's actually underlying ideas that are quite different in terms of how you read the code that's in Scala versus how you read the code that's in another programming language. The reason I'm making this distinction is that these concepts are the same concepts that show up in how Spark works with its data as well. Okay, so let me just take a quick moment here and say, how are we doing, everybody? Everybody, is this working for everybody so far? Is this, let's get some feedback on how we're coming along here. Guys, how are we doing?
I'm still here.
Pardon? You're still here.
Present. Yeah.
You're still present. Okay. Is you finding this useful?
Yeah, I was already introduced to Scala a bit, so maybe people who are new to Scala, I think for them it's useful.
Yeah. Okay. How about some of you guys who are new to Scala? Is this being useful for you so far?
Well, these are the kind of concepts that we have already learned because we happen to work with Scala in production. But it's always good to touch upon the basics.
Okay.
So yeah, that's we still constantly keep in mind that things are built in a certain way in Scala than in the language that we used to.
Okay. All right. Anybody else want to chime in? I'm always trying to adapt to what we're doing here. Anybody else have anything they want to add to it?
Do you guys want like with a faster pace, or do you want?
Nothing new so far.
It's good.
I'm sorry. Could you repeat that? There was an echo.
Sorry?
Could you repeat that? I got an echo.
I just said that nothing new so far.
Nothing new so far. So this is all familiar stuff to you guys?
Yeah.
Yeah, I would say even so. I would say that even people that aren't really native Scala people sort of know this by being exposed to other functional languages. So me,
Okay.
for example, I haven't really done any real Scala work. I did touch a little bit of one of the
Okay.
projects that we have, but I was exposed to other functional languages that sort of
Okay.
already covered these types of topics.
Okay. All right. Well, what we'll do is we will take a break for about say 15 minutes. Everybody a chance to go and get some stuff, and then we'll come back and we'll finish up with the slides, and we'll then start into getting up some virtual machines and signing them out to you. All right.
Super.
Perfect. Thank you.
Thank you.
Okay. Okay, guys. How are we doing? Are we back?
I'm back.
Almost.
All right. I'll give everybody a chance to settle in. I've just been setting up the virtual machines here, and we'll spend some time just getting you guys logged in so you can play around with them before I go back into the presentation. It's just something we need to get done. On my screen, I think you should be able to see the instances I've set up in AWS. And I think I've got everybody accounted for. My count might be off. Is there anybody whose name is not on that?
I think Roman and me are missing, but we don't have a Richard.
I don't have a Richard. Okay, well, who is speaking there?
Robert.
Robert. Okay, that probably should have been you then. Unless you want to become Richard. And Roman? Okay. All right, so now is there anybody that's not accounted for at this particular point? I think we're good.
Should be everyone. Yeah.
I'm sorry?
I think everyone is on the list so
Good.
far.
All right, so this particular, I'll assign everybody a machine here with an IP address, and rather than you try to copy them off the screen, I'll just go through and chat them individually out to you, so you can just do a cut and paste. There's two pieces of information you need on each machine. One, of course, is the public IP address. So I'm going to start with Robert, and I might not get all this. So Robert, there's your IP address. And the other thing that you're going to need is a password. And generally, the password is going to be this instance ID. And if you do want to grab it yourself, so there's Robert, and I was trying to figure out a fast way to do this. So
Thank
that's
you.
Robert's.
Thanks.
Okay, and so then we'll go to Michael. Here's your IP. And Michael's instance ID is that. I ran up a few of these the other day and tested them. They should be fine. Gorios, here is your IP.
I opened it, so I have to.
And your instance ID. I think this will probably be the best way to do this. Gregory. This helps to avoid people trying to make copying errors, copying off the screen, particularly with these instance IDs. And you can kind of match up on the screen if you're with your IP address to make sure you've got the right one here. Okay, Manuel. Yeah, the instance ID is going to be your password, and I'll basically show you how to get onto the machine. This is actually a new environment for me too, so I had to play around with a little bit. Oops. I was dreading this part. I knew this was going to be tedious somehow. And Vigny.
In the chat.
And finally, Gerald. Okay. All right, so if you want to paste those away somewhere in a little text file, you're going to be able to use that information. If you just want to paste that away. And what I'll do is I'll introduce you to how we're getting onto this. It's fairly straightforward. So what you want to do is go to your IP address. And what you should see is this training sandbox environment. And there's a couple of things that we're doing. Nothing is actually set up in terms of Spark. You're going to do that setup as one of the labs. So there's a couple of places you're going to actually, we're going to do that a little bit later on this morning. We're actually going to set things up. There's a couple of things that are useful for you. This VNC is a remote X desktop. And you're going to be able to access that by, if we do access over the web, we're going to get this this no VNC. And okay. Okay, I just did this. Is anybody else getting that problem?
Yes. There was just
Ran this test last night and it worked fine. I think I tested on your machine, Robert. Worked fine.
I got too many authentication failures.
Really?
Same thing for me.
New connection has been rejected with reason too many authentication failures.
same here.
Yeah, same here.
All right. Because I was in there last night working with it on one of the machines and it seemed to work fine. So I'm getting an error on my machine too here. Okay, so what I might do is we'll have to maybe hold on to that. I'll try and resolve that issue. Tests work perfectly. Pardon?
But my machine is fine.
Who's that?
I just, it's Evgeny.
Okay.
And I just logged into his SSH.
Yeah.
And I'm right.
So you got in okay. Okay, so let's have a little poll. Who was able to get in successfully? Evgeny?
One.
I'm still trying.
Okay.
How do you enter the password? Just this?
Yeah.
The password is that instance ID that I gave you. So I gave you an IP address and an instance ID immediately following.
So Ron here speaking, I'm trying to do SSH, and when I enter the password, it asks for password again.
Yeah, same for me.
Okay, let's
Use the Ubuntu user. That's what the instructions say.
Yeah, here. What I'll do is I'll at least try that part.
So SSH works for me. This is Mike.
Yeah, I think the SSH is not a problem. So I do the SSH over the web.
That may be a problem, but I just SSH using a terminal and that was fine.
Yeah. Oops. Yeah. So this should be fine. The password should be that instance ID. Oops, that's the IP address, not the instance ID.
So I'm getting the wrong password, both in web SSH and normal SSH.
Really? Okay.
Looks like I got in.
So that's one more, the address
Okay.
and the...
All right. So I got in fine with my SSH, but I'm running into problems with the NC. Okay. All right. So if you are having no problems with your machine, send me your name and I will keep your machine up. If you are having problems, then what I'll do is I'll try to spin up another instance for you and see if that doesn't solve the problem. Okay.
Maybe also people could double check passwords.
So yeah, Roman speaking here. I confused the first line and the second line because they're all coming all together without any blank line.
Yeah.
Blank line.
Okay.
So I grabbed the wrong password actually.
Okay. So you're.
So if any other people run into the same issue, then the password is the one that goes after the URP and not before.
Right. Yeah, I should have probably done that a little bit differently.
So SSH
Okay.
directly to the machine works for me as
So-
well.
So Robert, can you get on the VNC?
VNC via browser doesn't work,
Uh-huh.
but SSHing to the machine works for me.
Okay.
None of them works really.
Gerald speaking, same as Robert.
Okay. Well, I'm going to have to ask Robert. Okay, Robert. Michael, how about you? I just want to get a little count here.
So SSH works for me, but VNC also fails.
Okay. Gregorios, how about you?
It worked for me. It's your
Okay. How about VNC?
The VLC I haven't tried.
Okay. All right. Gregory, are you okay with SSHing in?
None of them works like terminal or web.
Pardon?
None of them works like either from the web or the terminal. Can't get
Okay.
it working.
Okay, so Gregory is machine I may have to restart. Okay. Okay, Manuel, how about you?
Hi, Corinne, just fine on SSH, no VNC though.
Yeah,
So
it seems so.
SSH is okay, VNC is no, is that what you said?
Yes.
Okay, Roman, I think you already told me, so just remind me.
So I connected through the normal SSH, so through the console, and web I didn't try.
Okay. All right. Hey, Vigny, I've got yours already. SH client and Gerald. Did you send me a message? Gerald, what's your status?
VNC is also not working.
Okay. See, I went into the instructor machine and Robert machines last night and did VNC and it worked fine. So I'm going to have to figure out what's happened between now and then. So, so as it stands right now, Gregory, you're unable to get into your machine at all?
No.
Okay, so
either-
I'm going to spin up a new instance for you, Gregory, okay? And we'll give you a shot on that.
Can you access which one are you trying SSH over web or VNC?
This one actually.
Well, those for me.
I'm not sure how to access VNC because whenever I type the IP address, I go to this web login SSH. So there's no option for me. I've logged into SSH, but I'm not able to click on the VNC anymore. I don't see this screen.
Okay. All right.
And I've tried also both two browsers, and also the other browser is the same. Oh.
All right.
No, I can log in now from the web. I succeed from the web, but not from. Oh, I got it now from. It's okay. Yeah. Oh, okay. Well, too late. But I have access now from both web and terminal.
You're talking about SSH?
Yeah, both. Yeah, both from terminal and web.
Okay. I have a suspicion maybe killing that process and starting it again might be the process. I'll try and work on that after class. Okay. Well, at least we got. Okay, so Gregory, I have spun up another machine for you.
Well, you can maybe kill it because that the first one works. So I'm kind of.
Oh, okay. All right. Okay. Oh, all right. This is the nightmare. You test everything the night before, and then when you actually get into class, it doesn't work. You know. Oh. Okay. Well, at least if you're in the terminal, you are going to have access to you should have access to a Scala shell so that you can work in the Scala shell there for the various exercises. I do believe that there is also VI on the machine. So without the virtual desktop, we can at least do VI on there. All right, and we'll try and resolve that issue after class. And if I have it, and when I come up with a fix, not if, I will come up with a fix, and then we'll implement that tomorrow, so that you guys can work on the desktop the way you're supposed to. All right. So let's go back into Scala and pick this up again here, and we'll work on this. Here we go. Okay, so let me see where we are here in time-wise. We are 10:30. Okay. Okay, so a couple of things about Scala that are suggested here. So we're going to work on our environment. We can do a simple REPL loop. We've already seen that. :help gives you commands that help on the various commands. And you can also do a history using the history command, :history. So there's some good stuff. Well, this is what we've mentioned before. Var and val define variables, where var is a mutable variable and val is an immutable variable. Scala uses type inferencing so that the type of the variable is inferenced from the literal that's used to initialize it. And generally, as with Java, if you try to assign a value to a variable that's not typed correctly, then you're going to wind up getting a mismatch. So the first couple of lines of code there are demonstrating a var, and that in the val y equals x, and we already demonstrated that. The syntax on var d:double gives an example of typing, explicit type declarations. If you are from the Java world, the thing to notice is that the Scala types are capitalized, whereas the Java types are not. Attempting to assign variables to the wrong types produces an error. This is important because typing is one of the key things that Spark uses in some of its commands. I'd mentioned before that everything that takes place in the Scala environment is evaluated as an expression. Everything is an expression, with the proviso that we're not doing something like from the Java world or something that's not an expression. Again, everything is a rewrite rule. So basically, we're assigning a rewrite rule here for y. And when we actually reference it, we get a rewrite rule, just like this is a rewrite rule. So this is rewriting 1 + 1. 1 evaluates to 1, and then the +2 evaluates to a function call, and that gives us 3. So we, again, have both this immutability and the use of strong typing. The Scala numeric types are byte, char, short, int, long, what you would generally expect. They are objects. You can call methods on. We illustrated that with that functional call on a 3. So this comes back to the idea that everything is an object, which is a little bit more of an object oriented. Now, if you're in Ruby, that is also a concept that's shared in Ruby. Where everything is an object. So that's a very Ruby type way of approaching this. So the notion of distinction between primitive types and user-defined types is really blurred in Scala, just like it's blurred in Ruby. There are helper classes, which give us a wide variety of operations that we could perform. So string ops, for example, gives all kinds of great operations like intersect and a number of other operations. And again, you notice in the example is that the string is an object. We can call the method right on it with the appropriate arguments. And at the second point there is also, again, that syntactic sugar. Anytime that you have that kind of structure where you're calling an argument on, or you're calling a method on an object with a parameter, you can rewrite that as an infix notation to get hello intersect loop, exactly the same way we would with an arithmetic operator. The distinction between these kinds of monadic operators and actually they're technically dyadic operators, I guess, but operators that take one argument can be easily rewritten as an infix type of notation on two arguments. That often produces some readable code, but it also can be a little bit confusing for people who are not used to the fact that this notation takes place, that there's actually a method call going on in there. But again, that's consistent with the use of the operators in the language. Let me see, there is a couple of special types. Scala predef gives a bunch of easily defined convenience functions. And we have two very special types. One is the any, which is the root type of all numerical types, which is any val, which is the numeric type. Sorry, any is the root of all types. We'll have a little tree here at some point. And what Scala does is always tries to go to the lowest point in a tree in doing inferencing. And if it can't, it goes up one level in the tree to figure things out. Unit is equivalent to void. It's more of a place marker in notation to let us see what's going on there rather than any sort of actual computation or usable value. So there's that little thing. Arithmetic operators. Oh, okay. Actually, it's in here too as well. So this gets basically the idea of how we think about the operators and what's actually going on under the hood. So we can actually add different kinds of operators, and we can work with those sorts of things a little bit later on. Hold on here. I'm just making an adjustment. All right, with you. I'm just getting a little bit of feedback here. There we go. A couple of interesting things that can take place here. So for example, we'll go back into my thing here. And again, the notation, if you're not used to or functioning, hold on here, functional programming, this can be a bit odd at the beginning. So for example, 1 to 10, whoops. I've got a caps lock on there. Immutable range. Okay, so what I'm actually doing here is I'm actually creating an object. So I could actually say var x equal to 1 to 10. And I'm actually creating a range object. So now if I actually list x, I can see that it's a range object, and I can do things like actually get the second element out of x. Again, it's a rewrite rule in which we're actually calling a method to, but we're using it in a particular infix notation. So in Scala, that is an expression that can be evaluated, which we're actually seeing here. Okay, so we'll see this kind of notation now and then. Let me see, where are we here? We just did that one. There we go. Yeah, we did there. Okay, that's where we are. So generally the collections or ranges are going to be immutable, and we're going to see that we often want to change that. So here is again, the expression that this really is one dot on the operator 2, which produces a collection, an immutable collection. Normally things are immutable by default in Scala. Whereas if we want them to be mutable, we can declare them to be mutable. So there's a couple of different things that are mutable and immutable. One is the rewrite rules for variables, which is the val-var distinction. And the other one is whether or not the actual object itself can be mutated in terms of, for example, a collection is going to be mutable or immutable. Again, we keep that distinction in mind. Mapping here, this page is just mapping our Scala types with our Java types. And we wind up with kind of a nice little mapping there. The difference here in Scala is that, again, we notice that the literals are not primitives. That distinction doesn't exist. They are objects. Again, very Ruby kind of way of looking at it. There are a couple of implementations in the object-oriented side of Scala, which is a little bit different than the Java model. It actually goes back to an older form of object-oriented programming, which we call mix-in objects. And the mix-in objects are ability to package up functionality, which is not intended to be instantiated on its own, but it's intended to be incorporated into other definitions so that we can add functionality in nice packageable units. The idea here is that we often have clear chunks of functionality which are not necessarily representable by something as lean as a Java interface. So we want to use some kind of other mechanism to do that. And this goes back to an old technique. There are, again, the any is equivalent to the object root class in Java. Interesting little historical work. Note back in one of the first object-oriented languages called Zeta-Lisp, they didn't have classes, they had flavors, and the root object was a vanilla flavor, which was kind of interesting. That was the original work that came out of MIT AI Labs. There's standard syntax for and while. The primary difference you have to keep in mind with these control structures is that they are expressions, they evaluate, and they produce a result, which can make things work very nicely. So if we take a look at the examples, we get B is an immutable collection from 1 to 2, which is essentially an ordered pair. And we can also now iterate over a collection. So the syntax is in that second line. So we want to iterate over that collection B. We use something that looks very similar using that reverse arrow. So we're basically declaring a locally scoped variable I, which is running from 0 to the length of B minus 1. And for every point, for every iteration on that loop, we're just printing out the line. So it is similar to the normal kind of for loops, just a little bit of syntactic issues that we have to look at, and we can even do it shorter by implying the iteration loop. So in the second line, saying for current and then left assignment arrow B, since we've got a for loop and since we've got an iterable object in B, the implication here is that we're going to iterate over that iterable object, and in each iteration, the element that's the current element is going to be in cur, which makes it a lot easier to work with. And then what we can do is also assign the results of that for loop to an object. So we can assign the results of the various structures here. We have those kinds of operations that we can perform in looping, and we'll take a look at Martin's book just to get a little bit richer sense of the syntax a little bit later. Standard if-else statements, we kind of looked at that earlier. I mentioned that a point is that this is, again, an expression that evaluates, so you can see it in a variety of different formats. And we tend to use very compact notations here. So that last line gives you the idea that, again, we have an expression as a rewrite rule instead of a instead of just a flow of control like we have in Java. The thing that's sometimes confusing for people is that the rules themselves are for how these things work in control structures are a little bit different than Java, although the control structures themselves look very much like Java. So you have to be careful if you're new to Scala to not think in terms of Java when you're looking at some of these similar faux-ami kinds of structures. The other structure, which resembles in sort of a generic sense a switch case statement that we would find in a procedural language, is a match. And we'll see the use of match a lot, which basically has a something to be matched and then a series of patterns that you can match from. So if we, for example, take a look at the first one, we've got the month num is a match, and we're going to match on the values there. So we're going to set cases 1, case 2, case equal to 3, and we get the appropriate match. The underscore is sort of the else case on this one, and we can now also assign the result back to the as a variable. We'll take a look at these a little bit later on in more detail. Hold on here. I'm just going to mute one of these because I'm getting some strange feedback. No, I can't mute it. Okay. All right. All right. Okay. So now we've basically got you guys have already done this part. So we've got you logged into the cloud here. Everybody's logged in, at least on the terminal. And you can log into your node. Actually, there's something different than what I was told to do.
Sorry, this is Roman speaking. My SSH connection for some reason is now broken. Can you please restart the machine or something?
Which machine was that? Who was that just made that request? To restart the machine?
I think it was Roman, but it seems like Berlin is not responding anymore.
Maybe they don't have internet.
Yeah, so Mike and me are not in Berlin. And that's sometimes the case, that Berlin loses internet.
Really? Okay.
Yeah, that's the downside of Berlin. So good food, but no internet.
Okay, so Berlin, it might be dead.
Maybe that's the reason why his SSH is not working.
That's what I wanted to point out.
Maybe no action is required.
We'll give a point to see if we can get back to them there. Yeah, this is really frustrating because I went and I just got all of this information the other day about all the setup. So I spun up some machines and I tested them up and it all worked fine. And then it took me, we got this issue now. So
I just got the information that on the floor they are sitting, the virus LAN just went very, very slow. So I guess that's causing the issues.
Okay. We'll give them a little bit of time to get straightened out there, and I'll wait until I get a go ahead from them that they're actually up and running. Is that just with you guys, your Berlin office, or is that an issue that happens a lot in Berlin itself as the city with wonky internet connections?
And the joke was that Berlin doesn't really do internet well as a city.
So we moved from the previous office location to the new office location. We supposedly have a different cable there, obviously.
Yeah.
But also in the previous location, we had internet issues.
Yeah.
And that was fiber, mind you.
Okay. Oh, people are coming back now. and going away.
Yeah, not sure how they will solve this because in the room they don't have cables.
Well, you know, I'm not going anywhere. So, I mean, if I don't want to, you know, like bore you guys, but yeah, everybody's gone now except for us. So I guess that's an internet issue.
Hmm.
Maybe
They
not
may be
internet,
trying to
maybe just
they maybe were trying to reset their
Wi-Fi.
connections or something.
Yeah, it's completely down. So other floors are complaining.
Okay. So how are you guys finding it so far? Is it useful, informative? I may as well get some feedback while I'm talking to you.
Until now, it's quite basic.
Mhm.
And I think, except for Roman, everybody should already know these few introduction
Okay.
steps, at least for Scala. For Spark, I'm not sure. For Spark,
Yeah.
maybe it's good to start from scratch, but for Scala, I
Yeah.
think we could move on quicker
Yeah.
if
Okay.
we
Well,
get internet.
sure. If we get
Yeah.
internet, sure. All right. Well,
Actually,
that's
I
good
was
to know
okay.
because it's hard to judge coming into a class like this because often people say, "Oh yeah, we're comfortable with Scala, we're comfortable with this." When you get in there, it's kind of like, "No, you're not." So we have to kind of
Yeah. So
feel our
that's
way
true,
out a
of
little bit.
course. Whenever you have training with multiple people, you don't really know what to expect. So
Yeah, well, I'm training another class in the evenings. It's supposed to be for programmers, and I have 3 people who've never programmed in a class. So kind of like, oh gosh.
We are terribly sorry, but we're back.
Okay.
What did
Are you
guys
sorry
do?
that you're back?
Yeah, well, I hear the internet went out all over Southern Europe, so you know, you guys did something wrong there. All right, looks like people are slowly repopulating the environment.
I think our keyboard Zoom.
Let's do this again. No, I can. Right.
Oh,
Cool.
All right, are we missing anybody?
No, I just I don't the password. I don't install the password anywhere. Jesus.
Just ask Manu, he has all the passwords.
And Manu, can you just like share again all of them?
I can copy paste. Sorry.
Which
No, one mine.
I don't have it.
Because the chat, of course, the chat history is gone. Yeah.
All right, well,
So
we
I
will
just
do this.
pasted the information in our private
Yeah.
chat. So everybody is
Okay, well, we'll redo that part right now. Okay, but this time I'll try and chat it out to you individually, and then you guys can cut and paste it. Let me see. Robert, do you still have your information?
Yes, I already copy pasted all the IPs
Okay.
and passwords into our private chat. We
Okay.
have in the company, so everybody should have access to that.
All right. If anybody does need their information, just let me know again.
so these are anonymized.
Okay.
Just speak any, just don't kill my jobs.
All right.
Almost connected VPN or VNC.
Okay.
So, yeah. Berlin, are you fine now? Can we continue?
Yes, I think so.
Awesome.
Okay, good. All right. Okay, so we've got that done, and what we'll do is just quickly do a quick review of functions and other things, collections. Again, this might be a little bit basic, but just on the off chance, we'll just go through this very quickly. If anybody has any particular points they want to explore, then please raise the issue, but I will assume that this is more of a review now for you guys than anything else. So collection classes, sequences, basically the three standard types that we find: sequences, sets, and maps. We parameterize them with a type if we are parameterizing them. And we have a variety of different operations on this. The one thing I will mention as an addition is that these lists are structurally quite different than arrays, in that they represent more of the kinds of lists that you see in very highly recursive languages. So these are actually more like a linked list as opposed to something else. So the various kinds of head-tail operations are very much like the cons and catter operations that we see in other programming languages. They operate under the hood the same way. The collections have are basically traversable, and they have the various categories. Again, you'll be able to explore this on your own if it's not completely familiar to you, but again, similar standard boilerplate methodologies. We can create collections, instances using a collection name with so there's an example there of creating the various kinds of instances. Arrays are different in the sense that they store the data somewhat differently, and there's an underlying difference in how they're structured. We won't get into the details of that in this class, but just to notice that there are some underlying structural differences. Collections are immutable by definition, but we can use we have mutable collections which allow us to add and remove elements. But again, if we want to keep in the spirit of functional programming, we don't generally tend to use those unless we absolutely have to. So there's the example of mutable and immutable. Different kinds of capabilities naturally on the different kinds of collections. So the examples given there just show this standard kinds of list with a head and tail operation, a range operation, which I demonstrated earlier, a map operation, which allows you to go and access by key as well. So very standard operations, nothing that you'd expect that would be particularly different. The functional operations that we have are similar to what we find in other functional programming languages. Map operations, which basically take a collection, map a function to it, produce another map or another collection. Map generally tends to do a one-to-one operation, and flat map does a many-to-many operations in some sense. We can do a variety of different operations with those, and we'll see those particularly as we get more into as we get into the Spark portion of the course. Sub-retrieval collections are exactly what they sound like. Take, filter, slice. We get some kind of predicate for doing a extraction of some subset. So the comment here is kind of good. Filter implicitly loops over a list and takes a function as an argument. So it gets that. It creates an interesting cognitive view of it. Folds and reduce apply operations to successive elements. These are all fairly standard, so they're supported in Scala. There's the idea of a map function where we're using a syntax. And again, the point of this thing is that the point of this slide is that we're applying this as a single functional operation, whereas we're using a procedural language, we're coding through the how to do it, whereas Scala is telling us, we're telling Java how to do it, we're telling Scala what to do. Okay, so filter function. Again, as an extraction function, these are going to be fairly important later on when we start to think about how these functions interact with each other in processing a set of data. So everybody should be clear on this. Reduce function basically is a collector function or an aggregation function of some kind of aggregation operator. And the example being presented here is sum. And then we have reduction, a typical example of using a reduction operation through addition to do a reduction of a list. And so this is primarily the essence of the operations that we need to be concerned with. You should be familiar with all of these and the underlying conceptual concepts behind them. The mapping, the filtering, the reducing. And of course, at this point, I'm assuming everybody's familiar with the concepts of anonymous functions. Anybody not familiar with that? I think everybody should, given the programming languages that you've been in. So we'll take that and move this along. We can define tuples, which are ways of structuring data. So just by using the tuple notation, which is the parentheses, this is similar to other programming languages, like we'll see like you will see in something like Python as well. The only thing that you might want to note is the use of the underscore notation to reference the various members of the tuple. And of course, if we had a triple, we could underscore with 3 as well. So this is the notation for generating tuples. Notice that this tuple is a different data structure than a list. We can use this underscore placeholder for anonymous function parameters, which allow as long as the parameters are used once. So basically it's more of a positional assignment rather than a named assignment. So when we have 2 parameter positions, the order in which the underscores appear are the order in which the assignment takes place. So the first example shows replacing a named parameter with an unnamed parameter, so that since there is no named parameter, we don't really have to worry about it. Personally, I don't really like this notation, just as a personal preference, because I find that I prefer the readability of the other form just for other people reading my code, but that's just a matter of personal preference. I mean, I think from the point of view of elegance, I like it, but in the point of view of code maintenance, I don't like it, just simply because I got to think about other people reading my code. So I tend not to do that. But you can see for reduce function, again, we have the 2 placeholders, and they're assigned positionally, which means that the first underscore is A, the second underscore is B, and it's positional. Again, very effective, very, very quick. Once you're used to it, it's a lovely notation. But the problem is that I always find is other people reading our code. And also, I'm also the kind of person, though I should indicate that when I have a complex computation, I put the parentheses in to explicitly do the sequencing more for my benefit than for the compiler's benefit. I often find that it's important for me to have a very clear idea of exactly what the order of operations are in an expression. So I tend to do that a lot. So we just did that. There we go. So we can go and you guys can experiment with a couple of these. One of the things I should point out is that I'm sort of committed to at least going through the material. So we'll give you guys a couple of minutes to play. I'm not going to do this now. I'll get you guys, give you guys an opportunity to experiment a little on in the environment towards the end of this morning's session, but I'm not going to stop and have you type in val equal 1 to 10. You can go back and experiment with some of these things if you want. And if anybody wants me to go back to any of the slides, you can do that. If anybody is unfamiliar with Scala in working with the language syntactically, do take advantage of the opportunity. So does anybody want an opportunity just to kind of play around with Scala for a little bit before I move on? It doesn't sound like it.
The slides later?
Yeah, I can give you the slides later. I'll make them available to you.
All right. Yeah, that will do for me.
Okay, so we can do that later? Okay. You might want to play around with a couple of these things. And really the only reason I want you to play around with it is just to make sure that if you're new to Scala, you've kind of understood the concepts, okay? Okay, very quickly, functions. Again, we won't spend a lot of time on this because it's fairly standard. But again, we have to think in terms of the rewrite rules as opposed to more of a traditional approach. And again, there's no specific return values again because we're always thinking in terms of evaluating expressions. And we also notice again that the equal sign reminds us again that this is a rewrite rule. And if we do have a block, then the block here, which is the parentheses, always returns the value of the last expression in the block. An empty block returns unit, which means that it's returning the equivalent of a void. You normally do not have to indicate the return value of the function if it can be inferred from the expression. However, the one exception to this is if you're doing a recursive function, you do have to put the return value type there, otherwise the compiler can get confused. So let me see, anything else I want to do? Call the function by name. I think that's pretty much basic. Unnamed functions, of course, you all should be familiar with this, and the standard arrow notation, which we're going to see, of course, quite a bit. So if that, I don't think anybody should have any problem with that. So we'll leave that as it is. Again, standard with multiple arguments. You can use a variety of different approaches here, including that using the underscore notation. So the important thing to also remember is that we need a function signature. So what we're actually looking at here is the type of a function. So we're assigning, again, the distinction between defs and vals is somewhat different. What we're doing here is assigning a function to a variable as opposed to using a def. So when we actually do a def, we're actually doing a sort of a call by name. This is a call by value. And what this is actually returning is a function that takes two integers and returns an integer, return type being inferred from what is returned by the body of the expression. So we can do the similar kind of thing here. Again, inlining functions. So we use our anonymous functions wherever it's convenient. Again, nothing that's particularly out of the ordinary. Class objects and traits. Well, again, this is where we're getting a little bit more away from the functional programming side of things, and we're getting into the class definitions, which are similar to the Java definitions. And I'm going to ask one question if somebody might want to think about an answer, is why am I using def to define the instance variables in my class definition? Anybody got a thought about that? Why don't I put var in there? I mean, I could, but...
So in the end, they have to be evaluated when you're calling it. Otherwise, if it would be a wall, it would be evaluated too soon and the value would be fixed. Yeah, actually, and this is just reminding me that I want to evaluate these things actually when not when I'm defining the class, but when it's at the instantiation time. Exactly. So it's controlling when those things are evaluated. Thank you very much. Perfect. Okay, so I can create a new square object, and that's the point of when things are evaluated. There's some rewrite rules for that class definition when you get to evaluate it. Other than that, it looks very similar to the kinds of definitions that we see. Everything, I believe, is public by default. I think that's how it works. Again, so many different rules and languages. I'll have to check on that myself. Scoping rules of what the default is. In this particular case as well, we also have a special singleton class, which is object. So object is a class definition, but it instantiates a single instance of itself. So you can only have a singleton for that particular object.
So you'll see that in a variety of places where, for example, at the root of an application or something, you'll have an object as opposed to a class. Constructors, we also have this interesting notation here, which is a bit different for accessors. And we won't, let me see, got it here, there we go. So the data members, scoping rules are the same. Access rules are generally the same for Java. And whoops, there we go. And we can also define methods. So all that's the same as Java. Singleton objects, again, it's a class that instantiates a single object of itself. And again, this is this is a really much cleaner implementation of the notion of a global object, or a encapsulating some kind of top level global context. The notion of a trait is that it looks very much like a class, but it basically is used to provide what we call mix-in functionality, and it can represent a role played by an object. It does have to have an implementation, but it doesn't have to. If it doesn't have an implementation, then it's much like an interface on Java. But sometimes you want to include some functionality. So this would be a trait geometric, which basically defines an informational structure that is going to be shared. And then we can use class in the same way, and then we use the trait here in the same way that we use a Java interface. And we're extending the class here. And we also use abstract classes in a similar way. So we can create an abstract class in Scala, which also is a class definition we don't want to, we'll want to use as the basis for inheritance. So we can have a new square. New square implements all of the appropriate methodologies. So this is very much exactly the same as Java. We can also use with to get the equivalent of multiple inheritance. We generally have a rooted single inheritance model, and the mix-ins represent additional components that are added in to avoid the crossing inheritance hierarchy problem that we have in multiple inheritance languages. So generally, if we had other mix-ins, we could have extends geometric with, and then we could add other mix-ins in there. And there'd be examples in the Odetsky book if you want to take a look at it. Other things to notice, so traits are mix-in classes, a little bit more like interfaces in the sense of how they're used, but a little bit richer than interfaces. The packaging works basically the same as in Java, with the difference that we use the underscore character as the global wildcard to import everything from the package that we're being imported from. We use types in different packages. And I think, let's see what this one's about here. Yeah, so we're using time here. So again, fairly, it's the standard packaging and import system that we see in Java, because again, it's built on the Java platform. So if you understand how the Java packaging works, you pretty much got this thing down nailed. Okay. The compilation process is similar for Scala as it is for Java. We use the Scala compiler, just like Javac, and then we run it with the Scala command, just like we run with the Java command. And when we do this, we have a main method, which gets the program arguments. It is generally an example of where we use the object. So here we've got an object simple app. It's got a main method, which is the entry point, and it's got the execute that's executed. So we can execute the application simple app with a command line argument, which is picked up, command line arguments which are picked up and used. All right, so the idea here is, again, we're not deviating too far from Java, but we're kind of got some interesting variations on the methodology. Okay, so now we finally reached the end of this particular section. So key points, functional as well as object-oriented programming. running in a JVM. There's a REPL which is something you can use to play around with. We do have the option of loading code. Scala is strongly typed. Everything is a class, defined as a class. Even literals are all objects. There's no primitive types. There is, hold on here. Oops, my mouse is rebelling. No primitive types. Again, it's using the garbage collection. Something like tungsten overrides that garbage collection. We prefer the immutability, and then we have type inferencing. All of those things we've demonstrated or seen. Tuple, container of one or more data types, lists and arrays. No way to iterate through elements in a tuple because there's no internal iterative structure associated with it. They're just collections of things. Expressions, we've seen that. Evaluations of expressions are basically applying rewrite rules. There are some things that are statements that don't return a value, and that's just syntactically difficult to do. So mostly they're things that define things like val x. It doesn't. You can't assign that to something, but it does return an evaluation in a certain sense. It tells you it created something. Units the same as void. And objects, and that's, I think, what we really want to cover off. Okay, so I think you shouldn't have any problems with those. And if you don't know the answers to those, then you probably need to take a look at a couple of things. But I'm judging by the feedback, everybody shouldn't have any problem with those particular problems, those particular questions. Okay, so again, I'm going to suggest if anybody wants to do a little bit more reading of Scala on their own, that what we want to do is, I have it set up here. There we go. I put the link in the chat for the Scala by example. So you can take a look there for some of the more interesting elements about the Scala language in terms of details about structure and whatnot. All right, so that gives us to about 18 minutes past the hour. So we've done our Scala kind of preliminary, which was something that had been indicated to me was something we wanted to cover before we jumped into Spark itself when we had that call. So we've done that. Is there any aspect about Scala that anybody would like to ask about, or anybody has any concerns about? And if not, we'll, you've got your virtual machines. I'm going to see about fixing that VNC problem today, but I'll leave them up until I find the solution for it anyway.
From Berlin, right?
Yeah.
I can't, I'm getting an echo. I'm having a hard time understanding that.
Okay, like the Berlin team is like good for the Scala parts. So.
Yeah, I'll leave. I have a suspicion I know how to fix that problem, but I want to test it before I take up any class time doing it, and then you can do some of the other stuff on it as well. Okay. But I'll leave them up for now with those operations, and I'll work on one of the machines to see if I can resolve that particular issue.
So the issue with the VNC, are you talking about?
I'm sorry, could you repeat?
So are you talking about the issue with this VNC server?
Yeah.
So yeah, so I think restarting the machines already works, or just killing the VNC server and starting up again. So problem was the machines were up for one day, and I guess someone on the internet tried to log in 1,000 times.
That may have actually.
Yeah,
Excellent.
but my client is not connecting because it says the settings are incompatible or somehow wrong. I googled, and there are some host encryption settings which are set to true, and my client is just unable to.
Okay, I'll tell you what I'll tell you what I'll do, guys. Is that I will actually restart the machines. We'll have wind up with new IP addresses and things, but I'll restart them just before class, and we'll see if that doesn't solve the problem. Because now that you think of it, I started at the machines and I did my VNC test right when it started, after it started up, and I had no problems. So I think whoever did that analysis about attempted logins across the internet, I think you're probably quite right. It never even occurred to me. That was actually brilliant thinking. If you're looking for a job, talk to me.
I'm fine, thanks.
Okay. Oh, brilliant, brilliant. Okay. Yeah, that authentication failure, I think, is probably directly due to that. So thank you. Good point. And I will try and resolve that issue later. And once we get logged into it, hopefully you can just stay logged in. And we have problems, we can restart or something to that effect. Okay. Okay, thank you all very much. Okay, so we're good with Scala. And if you guys want to just play around in that environment or a Scala environment, I will leave the machines up for the rest of the day, so you can get, use the SSH and play around in there at some point if you want. And if that is the correct solution, I will just reconstitute the machines just before class and let you guys log in right away at the beginning of class so that we can basically get that authentication in place. All right, thank you very much. Okay, so now if there's no questions, we'll get into the real content of the course, which is our Spark. We've already talked a little bit about Spark. I'm not going to do the Spark installation today. I'm going to wait until we get into the machine tomorrow so that you can actually, not going to lose it if I if I have to reconstitute the machine. Plus, we'll just pick up with that first thing in the morning tomorrow, or first thing in the afternoon for you guys. So let's get rid of that one. We've done that one, and we want to spend today and tomorrow working on this notion of the data model. So we've talked about the intro to Spark. I think we've covered up most of that. Let me also double check to make sure we've done that point. All right, I think we've covered off what we want to do at this particular point. Yeah, okay, we'll come back and look at that one later after we, come on here. I'm gonna get this data model one going here. Okay. So now we're into the heart of Spark. So those of you with 0 Spark and 1 light on their Spark, this is where hopefully things will start to get fun. Okay, so one of the things that we also want to emphasize is that I'll refer back to some of the ideas in Scala that are showing up in Spark. We've seen Spark from an architectural point of view. We've seen where it kind of fits into the ecosystem, what its goals are, what it's intended to do, what it's not intended to do, which is to replace the data storage mechanisms or to be a node manager, although it can be if it has to be. So we'll start with the notion of the Spark data model, since Spark is all about data. And we're going to start with the idea that there are multiple data models in Spark, and these correspond to multiple versions of Spark. The original one was the resilient distributed data set. This was changed, or not exchanged, but this was complemented by the introduction of data frames. Now, the big difference between RDDs and data frames is that RDD sees data as basically opaque. So if you've got a bunch of data, you can see the rows and the records in the data, but it has no concept of the internal structure. And what that means is that certain optimizations that it could do based on data structure are unavailable to it. What data frames do is they introduce a schema into the data and allow data to be schematized so that now we can perform optimizations based on the actual structure of the data in the records. And this is where we also introduce the Catalyst query optimizer, which is the tool that once we have this catalog structure can make optimizations based on the internal structure of the data, which is something that RDD could not do. In 2016, we have data sets, which provides a unified interface to those so that we can have a more integrated environment, and we'll generally think mostly in terms of data sets. In fact, we generally do talk about data sets now instead of these two discrete categories. And we're going to find that most of the time we can pretty much treat data as either one of these things. Okay, so the three data models, again, summarized here. The RDD gives complete control to the developer, and again, a little bit low level. But we're going to look at the concepts behind it to see how Scala actually operates with the data. The data frame, again, schematized, organized as columns, supports SQL. And so it is a RDD, but with an associated metadata about the structure of what's going on in the rows. This is an important innovation because a lot of the data that we work with is structured data. It is schematized. So we want to be able to extract those schemas. So everything from CSV files to JSON files, in a certain sense, is schematizable because it has some kind of structure. Whereas raw text is generally something that's not schematizable. It's just text in lines. There's not a lot you can do about that. And a data set is really an attempt to provide a unified interface to the data, whether it's represented as an RDD or as a data frame. Not all data can become data frames. And again, if you've worked in Python with data analysis and notions of pandas, or if you've worked in R with data frames, the idea of a data frame is not unique to Spark. It is a common way of representing data. So the RDDs are still the building block. We access it through multiple languages, and it's really the tool of choice for the unstructured data. I just mentioned text, but again, images, videos, anything that does not have a schematizable structure, we generally are going to use as RDDs. It uses the heap memory. Even with the tungsten optimizing, there is still going to be some problems with memory, and we'll take a look at some of those memory management issues next week. Today and tomorrow we're really going to focus in on the data models and get a good understanding of that. It's because the RDDs are more or less opaque. We can't really optimize a lot of things, including caching. So we wind up caching perhaps large chunks of data that we could have cached more optimally if we knew something about its structure. But again, for some data, we can't do that. So this becomes this becomes what we wind up living with. But we can optimize some of these things in other ways. So this is the core of the model. Now, data frames are, again, like I said, an RDD with an associated schema. All right, guys, welcome back to the second half of the first day, basically. Let me switch over to my, and we're working yesterday with the data model. Proceed along. By the way, with regards to that labs repository, that is a repository that we can access out of the machine. But I think what I'll do today when I have a moment is I'll make a clonable repository so that you can actually work with them on your desktop as well, because there are some documents in there that you might need. So I will attend to that. I just didn't have a lot of time, and I'm converting the slides to PDFs. So I'll finish up some of those slides again as well and pop them in the repository and then give you an update so that you can do a pull and get the slides. And if there's any other administrative matters you'd like me to take care of, just shoot me a message in Slack and I'll take a look at it. All right, good. So we started talking about the data model yesterday. I want to close this off. And this is, I think we got through these concepts here of these interfaces. And I believe we got certainly to there. Okay. All right. So we did that first section, the data model overview, and I believe this is where we got into the, this is where we sort of left off. So first of all, we will ask, are there any questions from that, from yesterday? All right. Now, this resilient data set, distributed data set, is an abstraction that formed the core of the original Spark release. And the idea here was that you are not directly interacting with the distribution model. So it is distributed and across multiple nodes, but because Spark is not doing the management, it's delegating off the management of the data in the various partitions to whatever manager is there. So it doesn't have to have a multiple nodes to work. It's going to look transparent to you because what you're really doing here is saying what you want to have done on the data, not how it's going to be managed across the nodes. We get into tuning, then we can alter the parameters that will in fact work with that and enable us to tweak how that actually is working by supplying various tuning parameters. And we'll be taking a look. I think most of next week is going to be looking at the specific ways that we tune. Today, really, we're trying to get the big picture, especially for those guys who are new to what's going on with Spark. So the distributed collection, the distributed part means it's partitioned, usually across different nodes, depending on the manager. That's transparent to you. It's also read-only. And there is a reason why it's read-only. It's the influence of that is, of course, the notion of immutable in the underlying Scala, which is written in. But it gives us an opportunity to do optimizations. In fact, it's the fact that it is read-only is one of the reasons why this, in fact, works as well as it does. The operations are executed in parallel on the partitions, same as you would expect for this standard kind of big data partition, map reduce. That's all managed at the infrastructure level. It's fault tolerant, and that is where we get the read-only property being highly supported, because if you are having a read-only set and you lose part of it, you can reread part of that set. If you have a set that is mutable and you get a loss at some point in the mutation, then it's very difficult sometimes to go back. Maybe you can sometimes, but it's very difficult to go back and reconstruct the set before that mutation took place. And so that's more at the theoretical level, but the idea is that this ability to have an immutable a data frame or data set. I can't not use those. I'll call them RDDs, so I'm not going to confuse them with the Spark data sets. To have these RDDs being read-only gives us a lot of capabilities to do this failover, because we can recompute not stored. We can get to that back to that state that we were in before we had a failure, and we can do it fairly effectively. So this is done efficiently. So we're not going out and fetching stuff. We're basically just recomputing what we've got to replace the missing data. The key to the optimization at the RDD level is that we break down the things that we can do with an RDD into two kinds of operations. Transformations, which are not actually executed when we invoke them. In fact, they stack up in what's called an acyclic directed graph, and we don't do any mapping or filtering or things that transform data into some other form until we actually have to return a result, and that's called an action. So when we finally have to get the delivery, say now we're going to take the results, we're going to save the result. Then we go and we execute all of the transformations, and the reason for that will become apparent in just a moment. Now, the analogy that I heard from when I was kind of delving into Spark is to kind of crystallize the concept behind this algorithm is if you are running a kitchen in a fancy restaurant, and you have an order comes in for a particular meal. You're going to have a group of people coming in, and they're going to have a banquet, and they have a menu. So what you do is you don't cook the meal at that particular point. You basically sit down with your staff and you figure, okay, when it's time to cook, you're going to do this, you're going to do this, then you're going to do this. And you run out a whole action plan of what's going to happen. And each person will have their step written out. They'll know exactly what to do. But there's no point in doing it because nobody's ordered the meal yet. Then the people come in, they order the meal, then you put your plan into effect. And the thing about the plan is that you may, as you're developing it, say, oh, wait a minute, there's a more efficient way to do this. So this is kind of an analogous idea, is that when we're doing these transformations, we're just documenting what we're doing. And then we're going to actually go and execute them only when we actually need to produce a result. And that gap gives us the opportunity to do some optimization. So here's the example of what we might call the life cycle of a resilient data distributed data set. So we will usually create it in one of two ways. We'll either load it from an external data set, or we'll do something called distributing a collection. And that is where we take a collection of data and we basically allocate it out to the distribution manager to say, okay, distribute this, parallelize this, distribute it out for me, and we wind up with a collection that's being distributed. So the data is created. Now, we go through a series of steps which describe what we're going to do with the data. So the first step in the process, and you can see this already sort of looks like a directed graph, is the first step is we've got a log file and we only want to look at the errors. So we're filtering out all the lines starting with error and we're reducing the data set. Then we're only interested in MySQL errors. So we filter again and then we get the right result to storage. It's so the transformation in this case is doing a couple of filters to filter out only the data that we want based on a couple of criteria. Nothing is actually done until we say write the result to storage. Then Spark goes and executes the three RDDs that are the three steps in working with the RDD. Conceptually, we think of three RDDs being created. So we think that RDD1, we filter and we actually create RDD2, and then we filter and we create RDD3. That's not actually happening. That is done at a conceptual level as we think through the stages in the transformation. So there's not actually three data sets necessarily being created. What's happening behind the scenes is that we're executing a sequence of actions on a particular resilient data set, and we're not creating multiple data sets. So and that's what's one of the optimizations that's going on. So it looks initially like we're creating all these copies of the data set. We're not really creating copies of the data set. What we're really doing is specifying what we want to do on the output. We're visualizing the output of one of the transformations as an RDD at the logical level, and then we're going to think, well, what do I want to do with this? So each RDD represents the output of the previous transformation. Okay, so this can be kind of confusing for people as we start off. So this engine does not immediately compute the results. They're stored as an execution graph, which is our directed acyclic graph. And then they specify how to perform them. This specifies how to perform things in parallel. So the graph is executed as an execution plan when the action occurs. And this only happens when something needs to be done and returned as a result. So this allows Spark to do a couple of things, and one of the things that we're really interested here is how does this help us do an optimization, and we can also do an effective recovery. So we'll take a look at those things in turn. So here's the example again. Excuse me for a second. I apologize for that. I'm just getting over a cold. I don't want to cough into the microphone. It's just rude. So this is what I mentioned here again. It reads a log file, filters out all but the error lines. It doesn't even read the file at this particular point. It's just specifying something it's going to do. And if you actually go and read a non-existent file, you won't get an error. if you're doing this, say for example, in the REPL loop. So if you in the REPL loop you say get text and read a file in, but that file doesn't exist, you won't get an error because nothing's been executed at that point. And then you perform a transformation and everything looks good and everything looks good. And then you finally get to the end of the point where you say, okay, now give me the top element of this. Then it goes back and starts to execute the operation. And it's that point that you're going to get the error that that file doesn't exist. So this is the manifestation of what's going on behind the scenes with this lazy evaluation. And this is a key concept. So the no actual work is being done in either of those two steps. So there's no execution in either of the filters because it's just talking about transformation. As long as the operation is only transforming the data in some manner, there's no need to execute it. It's only when we actually get the action that we have to produce something that triggers the execution. So there's a lot of different optimizations that can be made on here. So we could, if you notice that look at the sequence of actions that we're doing here. So we've got a log file, maybe it's a couple of gigabytes, and we're going to filter out all the lines with error. So maybe now we're down to a couple 100 megabytes. And then we say we only want to find the first line of that filtered data set. Okay, so when you stop and think about it, well, then why am I applying a filter to everything in the log file? There's a better way to do this. Instead of reading an entire multi-gigabyte log file and then transforming the entire file and filtering the entire file, maybe I can re-optimize this and just say, read the file in until I encounter the first error record, and then just return that and avoid all of this kind of work. So these are the idea behind an optimization. By analyzing, and that optimization is not apparent until you look and see what the action is that's requested. So now, knowing that we're only going to be getting the first element back, now we have to go back and rethink what these transformations do, and we can get a much, much more efficient way of producing the result rather than blindly executing each step in turn. So this is the idea behind what this lazy evaluation does. So when we so the sequence of actions that's taking place is that all of the steps up to the first action are creating a work plan, and a list of tasks to be done, and then once we encounter the action, we can look at the work plan and say, is there a better way to organize the work other than what was specified by the client? And that's where the optimization takes place with the RDDs. Okay, so that's what we're talking about here. The data is partitioned around the cluster. So while we're doing this, we've got a bunch of partitions and they're distributed onto various nodes. The partitions are distributed. How that partitioning takes place, again, we saw from yesterday that Spark has its own manager, but it generally tends to sit on top of other node managers, and so that's fairly opaque to the actual Spark engine when we're building it. But when we come into the optimizations, these things are going to be taken into account. So we've got distributed partitions. We take our file, divide it up into partitions. This is a fairly standard model. I'm sure you're all familiar with it. And we distribute the various partitions onto the various nodes. The nodes execute the task in parallel on the partitions. So we'll basically co-locate the tasks with the nodes. So, and then we perform in parallel, which is what we would expect. This is the whole idea behind the distributed part of the resilient distributed data set, is that we now have an underlying mechanism that goes and does the parallel processing for us. Okay, so, and this will come to a point we'll look at later, is that this, when we're doing the processing, we may discover that the way the data is distributed after we do a particular set of operations is unbalanced, and we'll see an example of that later. And at various points, we'll execute something called a shuffle manager. And that shuffle manager will go and reorganize the data so that we get a more even balance of loads. So if we do some kind of filter and we wind up with no data on 3 of the nodes because we filtered it all out and all the data for some reason is filtered on this node, we may want to shuffle things around to take advantage of the parallelism. So the parallelism and the shuffling is intended to improve efficiency, but it can also be a drag because shuffling may involve a lot of disk reads, disk I/O, which again slows it down. So one of the things that will happen is that while we've got this lovely, everything going in memory, that model can be a little bit difficult to implement completely when we've got to do a bunch of shuffling. So we'll get into shuffling later, and we'll look into optimization on shuffling, and we'll see how we can optimize the various kinds of shuffling algorithms that are there. So we'll turn to shuffling. So Spark, again, is basically designed to sit on top of Hadoop file system, and Spark can take the hints from the HDFS and do local data processing. So the idea here is to optimize operations based on where the data is located. So if we take a look at that line of code, this is in Scala. We're using the SC. Now, what the SC is, we'll get back to that in just a moment, is something called a Spark context. And I'm sure you're used to using context objects in a number of different programming environments, where the context object basically is an interface into a set of operational subsystems. So, and we'll see that this actually SC has been replaced by an object called Spark, which implements this functionality, but also implements other functionality as a result of having moved from this model to the unified data set model. So there is a so that first line, logs SC text file, goes and is reading in a text file from the Hadoop file system, and that is not executed immediately. And then when you execute logs.count, which is going to give us a count of the number of lines in the log file, at that point, the text file command is actually executed. If you've given it the wrong URL at that point, if the file doesn't exist, in this particular case, we're reading a collection of log files into one big, so we've got a bunch of log files sitting on a node, and we're creating a single RDD. Logs, in this case, is a resilient distributed data set. So the logs, so reading the data in and assigning it to a variable creates the RDD. So logs is now an RDD, and we can execute actions and transformation on logs. So in this case, we're executing the action count, which is now has to return a numerical value, which is going to count the number of lines. So the so again, because Hadoop preceded Spark, Spark was able to leverage its interactions with Hadoop in order to take advantage of the information available from Hadoop in order to figure out optimal ways or better ways or efficient ways to distribute the data. So we'll come back into those optimizations later on. Okay, so this shows up here. I believe S3 probably refers to an Amazon blob container. And we got HDFS on the left. Okay, so what accounts for the difference in this? Well, what accounts for the difference is that as far as the S3 is concerned, Spark is just seeing a big chunk of data, and the read time is going to be considerably longer. On the other hand, HDFS has a lot of information that Spark can access to read these things in very efficiently, and as a result, you get a much, much better lower time. So one of the takeaways from this is that while Spark can operate pretty much from data, from any kind of data source, where we really, really see good performance is that if we are able to leverage some kind of distributed node cluster system like Hadoop in order to process our data, because Spark will be able to use that information to process reads and other kinds of actions much, much more efficiently. So there's sort of a first optimization. Pick a data storage that Spark's really going to be able to leverage, and you're going to see significant improvements in things like iData IO. A transformation on a partition creates a partition of the new data set, and then the transformations on it may be pipelined in a task. Now, a task is a job that is can be run only referencing the data that's in a particular partition. So when we look up when we execute the read, then we're basically doing the distribute. We basically got information about how that data is distributed, and that action that we're taking on counting or doing a filter is now broken down into tasks that run on a single within a single partition. So the idea is that once we can break down the tasks in an optimal way, we can improve our efficiency by then doing all of this in memory. So in other words, we're talking about the importance of staying in memory. Part of that has to do with how we organize the data on the partitions so that we don't have to do things like shuffling. So if we can optimize our operations so that they can be pipelined in a task, so that our two options here, the two filters, if we can get it so that those two filters can operate sequentially within a partition without having to refer to everything else as tasks, then we've got a really, really good optimization. So now we're seeing one of the challenges that we've got here. Okay, so we've covered a couple of concepts here, and we're starting to get a peek under the hood at what's going on with these RDDs. So conceptually, when we write the code, it looks like we're just creating all of these new RDDs and moving them around. What's going on behind the scenes is that acyclic graph, directed graph, has to think in terms of where the data is located and how can we organize these activities so that we can break a single transformation down into a bunch of tasks, each task running on a partition, and pipeline it so that we don't have to stop and reorganize the data. That is our objective in the optimization. And again, if you stop and you think about it, if we were to execute each step as it occurs, this kind of operation would not be possible. So we'll take a look at the example here. We're reading a log file, and it's split into 3 partitions, and each line has a severity, a component, and a message. So the severities here are info, error, warning. The component looks like Spark, MySQL, some nulls, and we have a message which can be null as well. So we've got this data, we read it in, and it's split into 3 partitions. So the first transformation would be applied. In this particular case, we have run 3 tasks. Each task applies that transformation to its partition. So as partition 1 goes, all right, so let's go back. So we've divided up the data. We've got this transformation taking place. We're going to filter for the lines containing errors. And that's broken down into 3 tasks. And each task, and we'll just assume it's running sequentially at this point. So each task at this point goes through and produces its output in our next phase. And we have what we call uneven partitions. The filtering, this is what I'd mentioned before. This is an unbalanced set here, which means that we're going to have performance bottlenecks because the work is unbalanced. And the model we're using here is if I've got 3 programmers working for me, and I assign them programming tasks, but I do it in an unbalanced manner, then the programmer that gets all the tasks is probably going to break down and quit and throw things at me because he's so mad he's doing all the work. And I've got 2 other programmers just sitting around drinking beer and watching a Netflix. So the obvious thing is not so much that I'm overloading one partition, but the question is, well, why can't I utilize all these other resources more effectively? So the real danger in unbalanced partitions is not that we're going to be bottlenecked because of partition 1A, but that bottleneck is unnecessary, because if we proceed on, we've got all of this extra capability sitting in 2A and 3A that we're not using. Now, this may wind up being a very significant unbalancing if we have a lot of data. So we generally want to try and avoid our unbalanced partitions. So if we continue on to what we're doing is looking at the individual tasks. We're looking for filtering for lines containing error. So that our first filter would result, our first filter statement would result in 3 tasks running in parallel. They produce the output that would be in that data set 2. And then we run the second filter, and that produces the outset in data 3. So we've got, as we're reducing the amount of data, we're freeing up a lot of additional capability and storage. Now, the important thing to remember is that we're kind of cheating a bit here and saying that, okay, we apply this filter and we get this, we apply this filter and we get this. We're not really applying these filters. What we're saying here is, if we apply this filter, this is how the data would look. So we have this operation here. Now, this is going to be helpful if we have some sense of what the data is like. So what we want to do is do a couple of different things. And so we filter for the line containing error, and then we can go through what we call a coalesce operation. What a coalesce operation does is rebalance partitions. And this, depending on a number of factors, for example, how unbalanced our partitions are, this can improve our performance considerably. But the problem is we're going to have to move data around. Since each of the partitions generally is working in its own memory space, the way that we often will do this is with some kind of disk I/O in sort of our shuffling, like how do we get data from one partition to another. And so that'll become a topic of some of our optimizations as to how do we make this part really improve in performance, because it can be, in fact, quite expensive depending on the data in our underlying system. So the idea here is that we've got a couple of different things, though. So we can repartition, we can create more partitions or decrease partitions, and coalescing, which is just decreasing partitions and is more efficient. So repartition reshuffles the data randomly to create more and fewer partitions and balance them. And so the idea here is that let's go back. Whoops. Let's go back a slide here. Oh, there we are. Okay, so now we can even think in terms of, well, what are the costs of these two things? So we repartition. We reshuffle the data randomly to create more or fewer partitions and to balance it across them. So we shuffle data all over the network. So we could just reshuffle data, or what we could do is coalesce, which is an optimization on that because it decreases the number of partitions to these partitions. So rather than just changing and resorting all the data out across the partitions, we're just saying, okay, so we've run a couple of filters and now we've got a whole bunch of partitions really that are kind of empty. So what we'll do is coalesce them and just make those partitions available for something else. So the idea here is that we can rebalance the partitions we've got, and we'll get more into how these kind of mechanisms work. But the underlying difference between these is that we are looking at repartitioning as the possibility of increasing or decreasing, and has to take that into account in its algorithm. Where coalescing is only going to be used to decrease, so we can have a much better algorithm for actually doing that, and it's more efficient. So we're just decreasing the number of partitions. So generally, as we're filtering, the data sets are hopefully going to get smaller. As they get smaller, we don't need as much processing nodes, so we can coalesce and release some of the partitions that we no longer need. So again, this is a useful way to kind of return resources we no longer have available, that we no longer need, back to our resource pool. So what Spark does is is it tracks it, tracks the transformations. As mentioned that before. That's at the acyclic directed graph. And the lineage that we've got is this set of transformations that produce the data set, and the loss partition can be reproduced from this lineage. So the example down here, if partition 4 is lost, Spark can go back and reread the the block again, apply the transformations, and recover the partition. Excuse me. Now, because we're just reading the partition again and reapplying the transitions, and we pipeline the tasks as much as possible, it becomes very, very efficient. So the underlying mechanism that this works by is able to do fault recovery because of the way the data is managed in the partitions. So it's very efficient. It has little overheads. And we can because again we have kept track of how the data got to this point through our lineage. We're able to basically back up a few steps and say, okay, how did we get here? And of course, you know that this is so this sense of knowing the history of what got the data into this spot gives us this capability to look backwards in this lineage and say, okay, let's just restart back from over here. Okay, so let's take a look at what a Spark job does. So here's an example of Spark. Now, this is using the older interface, which has got the Spark context. So let's step through what the code looks like. We initially, using the text file, we read in a server log, and that creates an initial RDD, which is called logs. We then filter using our filter function for all of the lines that contain error, and the result of that filter is assigned to an RDD called error. Again, remember, this isn't actually happening. And then we filter that line on that RDD dataset errors. We filter out all of the Spark lines, and we assign that to a new RDD called Spark error. So we have two RDDs that have been built out of this operation. We've filtered the original line in two ways. So we have a graph here where nothing actually happens until we actually encounter the save as text file, and we specify the RDD that's going to be saved. So and I'm sure everybody here is familiar with the concepts of graphs and things like that, acyclic graphs, directed graphs, and all of those sorts of things. So if you aren't, just let me know. Okay, so once the action completes, the data sets disappear, and if you need one again, it's recomputed. And again, that's a little bit of a higher level point of view. Again, we do optimization here. And it's easy to conceptualize that these errors data set is transient. So basically, as it's executing it, it throws away the RDD, which is an intermediate result. So the way it's actually executing is a little bit different than we conceptualize, but it maps very nicely, and we can use that conceptual model. So in this particular case, we are going to if we didn't have the two filter operations out of the errors, we would probably get a different sequence of operations if we only had one filter. But now we realize the fact that we're going to have to branch at that errors process. So the operations are going to be implemented a little bit differently. Again, this is the optimization on the acyclic graph. In this particular point, though, that we're making, we can conceptualize it as this graph is running. Once we pass through a node, the data, the RDD that we used in that node to create the new nodes is no longer available. It's gone. So it's transient. And what we can do is actually suggest to Spark that it not be transient. We just want to keep it in memory. And again, the idea here is that sometimes this initial operation, whatever it might be extremely expensive. So to have to recreate this RDD might be prohibitive in terms of utilization of resources. So we can say, okay, when you get to this step, just hold on to a copy of that, and then we're going to use that in our further computations. So here's our notion of what we're going to be doing here when we do a distributed execution. So we have RDD count. So we're going to count stuff in the data set. And this is a fairly standard distributed model, like a MapReduce model. So what we're going to do is take our operation and delegate it out in terms of tasks. And again, the thing to notice about tasks is that the tasks themselves are operating pipeline within a particular worker node. So and operate on a particular partition. So so this is a fairly standard MapReduce type of idea here, but it's far more efficient than a standard MapReduce by the way it's organized. So the count is parallelized, and we get used to this notion of the task. So each worker runs a task, which is a subset, or the not a subset, which is the actual operation applied to that partition. So it would seem to be that if we can make these tasks work all within memory, we then get a much more efficient step at this point. And then the final coalescence is the results is the summary the total of the individual counts. Okay, so this is the notion of the parallelization. So here's a question. How would we find min, max in a distributed fashion? Just, I guess, as a general thought.
Well, we can find max or min in each of the nodes or in each of the partitions, and then find max or min in all the results that we've got from the nodes.
I think that's probably quite right. So yeah, and I think that's fairly obvious. How can we find an average value in a distributed fashion?
Cross all the nodes, sum up and count elements, and in the end divide sum by the number of elements.
Yeah, I mean, there's a couple of different ways you could think of decomposing the problem. Is you could return an average and then account for each partition, and then do a combined average, or you can do exactly what you say, do a sum of whatever you're averaging for each node, and then do a master sum and do the same thing with the count. So yeah, I think these are fairly obvious questions. So we're going to take a look now at the notion of the applications, jobs, and a so we have a Spark section and a hold on here. And the job can be executed in one or many stages, and the stages can have one or more tasks. So what we do is we decompose down the action, like save and collect, and we decompose those down into stages or steps, and each step then maps out to a set of tasks on a particular partition. Remember, tasks when we're talking about local partitions. So a stage is a collection of tasks that can be executed in one executor without talking to another executor. In other words, a stage is a sequence of operations. Let's go back over here. So when we look at this action, we'll say, well, what are the sequence of actions that we can do to get there that can be executed within a single partition? And that stage then breaks down to the series of tasks that we can execute on each partition. The collection. So the idea is that if we can execute all of this without having to do any reshuffling, we basically you can think of it as having one task. But if we have to do some kind of moving of data around or communicating of data, then we have to have another stage. So we have to think about as long as the data remains consistent and can work in isolation, we're generally going to be working within the same stage. But as soon as we need some kind of interaction, network communication, then we have to start a new stage. So what are the kinds of things that cause these? Well, sorts, groups, joins. So the idea is that when we are doing some operation on the data set as a whole that does some kind of transformation like this, like sorting, we can't just sort necessarily an individual a node because we're only going to be sorted on that node. And so to get an overall sort, we may have to do some kind of other operation to sort across the groups. And similarly, group by key, we can group on each node, but we still need to group in terms of the entire data set. And joins, of course, are a similar kind of operation. So what we want to do is try to pipeline and stream our stages into tasks, but we also want to try and break down the job into the individual stages that can be executed in sequence. So again, we're looking at going back to a really functional model here, where we're looking at applying a job, and you could almost think of this as currying the job, where you're taking a data set and a sequence of operations, and you're breaking them down into a sequence of operations, each one feeding on the output of the other. So there's a way to conceptualize that. Okay, working with RDDs. And by the way, we'll get into sort of the underlying mechanics after we cover all the basics. So don't worry, we shall get there. So the couple of ways to create data: we can load files from local or distributed systems, parallelize a collection, and this is often where we are wanting to work with small to medium-sized data sets. We're not going to get any significant advantages from parallelization of the data or maintaining a distributed file system. The idea is that there are some applications where you don't need a massive amount of storage, but you still want to do the same kind of analytics that we're doing here. So if you're going to parallelize a collection, this goes back to kind of our workflow model. So for example, if I am going to be developing some kind of algorithm to do some kind of analytics on a massively large data set, I'm probably going to take some sample of that data set and use that as a test data set with a relatively small number of elements that are representative of the underlying population, and I want to go and experiment with my Scala algorithms Spark algorithms on that data set. Because the data set's small enough, I don't need to put it into a distributed environment. So I'm really looking to see, is this algorithm going to give me the right result? Once you get the right algorithm, then you can start thinking about how I'm going to work with the larger data set in the data, but I know my algorithm is going to work. So the parallelize gives me the emulation of being in a distributed system. So I'm going to see how it's working and how it works. And I can work with small data that fits into memory. And we can create from a local file. There's an example that we read it in. We can create from multiple files. We can create from files in HDFS. And as we get into other ways of doing it, I think we get into the more recent versions of things like data frames. We also are able to read JSON files and CSV files and other things that have structure into it. The one disadvantage to the optimization routines for RDDs is that the data is fairly opaque to the optimization routines. There's no real sense of the underlying structure of the data. So it's not necessarily able sometimes to figure out what an optimal strategy is. That's what the data frames give us, is the ability to do a little bit more prediction as to what an optimal strategy is going to be. This is how we would do it in Python. Again, Python works here because we're working with RDDs. Pretty much the same as the Scala, and of course we could do a number of different operations using different, or we can implement that in a number of different programming languages. Now, transformation and action examples, and again, it's almost like we're beating a dead horse here. But we have input RDDs, and so we do a map to get squares. And then that one, if we want to filter, we get filter on even numbers, and distinct, we get 3, and those are all transformations. And the last one is a take, which is an action. Generally, the rule of thumb is if you're returning a result to as a return value from your Spark job, that is going to be an action. So there always should be an action, obviously, because what's the point of doing all this transformation if you don't get any results from it? So we're counting on the fact that there's always an action. The workflow, again, here is our RDD, and we again go through our filtering, do a couple of transformations, RDD3, and we find the errors. And then when we do a save, then we have an action, and we can collect on that and also do the client. Warning here is collect returns all of the results of the transformations. And there's other operations, particularly if you're testing that, like first and top, and is it top? There's certain, you can specify a certain number of records to be read, and just to make sure that you're doing things correctly. Yeah, if you're doing collect, it's generally not something you're going to do for a large data set. So the map transformation, this is going to be fairly obvious. Returns a mapped value, and there may be a transformation of type as well, but a simple map generally has the same amount of output records as inputs. And now what we can do is look at that code down there. We parallelize a list of numbers, we apply the map function, and then we collect it into and we get out the result of the result. So it's when that collect is actually executed, we wind up getting the result. We're going to do the same thing in Python. We're not really doing Python so much in this class, so I'll just put it up there to say you can see exactly the same operations taking place. We're just using a different programming interface. So what's happening in here is that when we parallelize the logical view, and this is now we're going to get the difference between the operational view and the logical view. So the idea is that every operational view of the data can produce multiple strategies. In fact, we call this a logical strategy. At the top, the logical view is a logical strategy. It makes sense. I've got all this data, and I'm going to multiply each element by 2. That's the logical view. In the operational view, or the implementation view, I'm thinking in terms of how that operation breaks down into tasks. So from my logical point of view, from my analytics point of view, I create RDD2 out of RDD1, and I can imagine that's in memory. Now, what happens is that that operation has only got one stage, is then at the physical view turned into tasks. So I've got this map task that's going to operate on each particular partition. So so where we're going to get optimizations is often in how that operational view is implemented from the logical view. So the idea is that one logical view can have multiple possible implementations. Each one of them has an associated cost, and our optimization routine is going to try and minimize the cost of that, implementing that logical operation in a particular physical environment. Okay, so there's the idea behind that. So filter reduces the size of an RDD, and it has does not do any type changing, and we have the same operation here. Again, fairly straightforward and simple. We're not going to get too deep into it. It's fairly obvious. You parallelize, you filter. I think everybody's familiar with that idea. And you can standard way actually is to use anonymous functions. So I think in Python we use the lambda keyword to get it in there. So it's exactly the same as the slide before. And we have a couple of common actions. Its take was the action I was trying to think. I work in so many different environments. I get aphasia between the commands in different environments. I've actually sat down in a programming language and written if, and I have no idea what comes next because I can't remember which way it's implemented in that programming language. So that's kind of embarrassing. So if you take a look here at an action, count returns the number of counts. And as you can see here, by the way, could anybody suggest what an optimization might be on this? What are some of the different ways that we could do this?
Persist odds collection.
Pardon?
Persist odds collection between, so count and take are both executing, right? So if we could persist the collection before doing count, then we wouldn't do it second time.
Yeah. So in other words, when you stop and you think about it, if you can think there's a couple of different ways that I can actually implement those two lines of code, some of which would produce results. So if I, excuse me. So if I just executed this all sequentially, I would have to have both RDDs around. I would have to have both numbers and odds in order for me to go and get a count of each. So it would seem really inefficient, even though the code says do these transformations and do these two actions. When I analyze what the actions are doing, I can reorder it so that when I first create the numbers, I can do a count of numbers and stash that, and then do the transformation, get the odds and count that. And I don't have to keep numbers around. I can, otherwise I might have to have it persisting. So the idea here is that what we're really doing is doing a count, and not only that, but if I do the count on odds, I don't even have to keep if I'm only going to take the first two after I get the count, I don't have to maintain the whole thing. So the idea here is, if you stop and you think about it, the question you're always asking is, what can I throw away? Where can if I reorganize my steps when I'm actually executing them, am I going to get efficiencies? Am I going to be able to throw away data that I'd otherwise have to keep? Or am I going to be able to do a couple of operations early, save the results, and then not have to do certain kinds of transformations? So these are the kinds of ideas that we have between this. Now, this I think is that's Python. We'll skip over that. Reduce is a standard functional reduce operation. Returns a single element. So standard examples of reduce are multiplication, factorials, and additions. And again, we do the parallelization and we operate it this way. The excuse me. Okay, so there's the reduction. We also have a flat map. And this flat map, the difference between a map and a flat map is that maps, always the number of records in the output set is always the same as the number of records in the input set. The flat map is, the output is going to may have more or less records. For example, if I take a long string of text and I break it into words and return that, that's a flat map because I've got more records than I had before. And so if I also have a text and let's see, well, if I take let me see. I'm just trying to think of another example of map. Another map might be that I have a string of words, and I decide that I'm going to join all of the words that precede a punctuation mark to create a sentence. That also is a flat map because I've got fewer objects coming out. So I always have a consistent size, and it's important to distinguish these because that's going to factor into our optimization. So here we've got, let me see, reduce flat map. So I've got my number of, I've got a parallelizing list of numbers, and I'm going to create a list of 3 numbers out of each number. So I'm going to wind up from 1, 2, 3, do 0, 1, 2, 1, 2, and I wind up getting my list of numbers. So this is a flat map because my original order 3 turns into an order 9 list as a result of applying the map operation. Okay, so where do we actually find flat maps? Flat maps often come when we want to break something down into finer structure, or we want to coalesce structure into larger conceptual objects. That's generally, that's why I use the example of the sentence and the words. It's generally a fairly straightforward kind of example, accessible. Union works the same way that a union does in something like SQL, in the sense it returns 2 RDDs and creates a union of them. And again, you can see that there's probably a couple of ways to actually optimize that as well. And now we're going to do a collect on that and do a sort, and we can use distinct to remove duplicates. So this is what we might call just like an SQL union as opposed to a set theoretic union. We can also return a union of this RDD with another RDD. So we're going to create a union of a particular RDD with another one, a different, in Python, slightly different, so it's about the same. So here's our operations. Mapping applies a function to each element in an RDD, and you get out the same number of elements. Each element may be changed to a different type. So for example, an example of that is where I get a RDD containing string representations of dates, and my map function turns them into ISO standard date objects, or a date object of a particular type. Or I get a string representing a numerical value that's been read in from somewhere, and my map turns it into an integer. So the map functions are not going to guarantee that the type of the object produced is the same as the object that went in, but it does guarantee that the number of objects is the same. The filter throws away data, always a useful operation to have. So the filter, the number of records in the filtered set is always less than or equal to the number of records in the previous set. And you're guaranteed that all of the data types are preserved because you're not doing any transformation of the underlying data. You can remove the duplicates of a set using distinct. And flat map is like map. Again, no guarantee that the output records are going to be the same type as the input records, and there's no guarantee that the data types are the same or the number of records are the same. All right, then we have map partitions, which is like map but runs on the whole partition, not on each element. And I think we'll see an example of that later on. So it's more of a group transformation. A couple of other things we've got: union, we saw that. Intersection, we didn't mention that, but it's fairly obvious what that does. Subtract, those are basically the set theoretic idea. Except for union, we have to remember we have to remove distincts because it is more of an SQL union. And sample is a very useful one. We can take a small sample from the RDD. So if I want to know if my RDD is going right, I just might want to grab a couple of quick samples out of it to say, did that transformation work properly? So we'll often sample as we go through as part of our data quality process. As the RDD actions, these return values that are not RDDs, and the ones that we've seen here are count, first, which are fairly obvious, takes the first n lines, collect gathers all the records, which basically says, which basically takes all of the resulting RDD and gives it back to you. And then save as a text file, saves to storage, and there's a whole bunch of others, but those are some of the more common ones. But again, notice that what we're getting back here is not an RDD. Even with collect, we are not getting back an RDD. We are getting back a vector, a list, or some other kind of construct that is not an RDD. So the RDDs are only things that happen in the actual operations of the data sets. All the RDDs disappear after the last action has been executed. They do not exist. They're ephemeral. Let me see. RDD documentation. I'm not even sure if this is still valid. So we'll come back and take a look at that a little bit later, and we'll maybe browse on that. And now we've come to our first lab, and we are going to do some 30 to 40 minutes. This is just going to be an opportunity for you guys to look at, and there are solutions to all of these things as well. And in order to do that, we have to get you into that lab environment. So I have to go and find those, and I'm going to be putting some things up here. Again, I'm still trying to work my way through all of this stuff. So I'm going to go into my. Okay, so first of all, any questions about the theory that we've done up to this point? I think it's fairly straightforward, but you never know.
Geralt here, different thing. So I tried to connect. It feels like my IP is not reachable. I mean, the IP I had yesterday.
Oh, yes, I gave you new machines. So there's a spreadsheet in the Slack channel. You should get a new IP, and it should. There's a.
ITSP external Spark training external.
IT Spark training external.
I think you missed to invite me.
Okay.
I'm gonna add you just now.
Yeah. So there it is. It's in the Slack channel. I tested my machine. It works fine. I think somebody else tested their machine. It works fine. So we should be good on that.
Yeah.
All right.
Thanks.
Okay. Now I'll go over a couple of these files here. These will be available to you in the machine, and I'm going to try to make them available to you all. I'm going to try to put them into an accessible repository so that you can also work on your machine with them as well. So there's some instructions here, and okay, that's where's our. There's a setup here I want to take a look at. Read me. Okay, so here's setup. And this will give you this information. I am going to put this into the Slack channel so that you can have the instructions, and that'll be useful. So I'm going to the Slack channel. I'm going to do setup. This Slack, whoever came up with this idea of the Slack channel, you're brilliant. Okay, and I'll just add that HTML. I'll give you the markdown. It might be a little bit easier to work with. So there's the setup. I'll put up some of the so this is the setup file. Hopefully you can open that into an appropriate editor that will give you a nice little markup. I'll put a couple of these setup files here so that you'll have them. Let me see. I don't think we're going to need Hadoop at this particular point, but if you do, I'll add the setup for Hadoop and for Scala and some of the edit files that are there. So we should have all of the setups that are there. And I'll let you guys see if you can actually get into that environment. So the edit files, we'll add that one. A couple of these files, we'll just dump them all into here. Setup local, setup Hadoop. I think that should be everything that you need. So I will dump those into there. Now, I will also, now in the setup, you'll also notice that you are going to be able to, you're going to be setting up your environment. So you're going to do a pull on the Spark Labs. They are on your machine. And you should be able to to use. And this is what I think one of the reasons why they wanted to have that desktop was because you're going to want to read the documents in the machine. So there is that as well. All right, so I'll let you guys see if you can manage the machines. Like I said, I did. Like I said, I was able to get in and get the VNC started. So you should be able to get the various tools that you need here, including the shell. You should be able to get it. You've got a shell here that you should be able to manipulate with, or you can just SH into the shell until you need to edit something. All right, so you should be able to browse the various files that are in there. I've given you copies so that you can look at them on your local machine as well, in case there's any issues. All right, so I will let you guys go to it, and we'll see if there's any issues. And I hope there's not. I ran through this setup once before, and I didn't have any issues, so we'll make sure that everything works. All right, sound good? Okay. Pardon?
How do we start? I mean, you send a couple of files, so.
Yeah, just read through the setup, and actually, that's a good question. I just wanted to give those to you. So the lab 241, lab 3. Oh yeah, we want to also go and pull this slide up here. Okay, and this is the one I said we will come to today. Okay, we ran out of time, so I will put this slide up on the screen for this lab 2. There we go. So you want to look for your run Spark instructions that should be in your setup. So I think that should be here. And so you'll find the instructions in that folder 02 to install Spark and the other things. All right. So that should be in your. Once you do the setup and you do a pull on that labs, you should have access to all of these things, and you should be able to look at. We'll do lab. That's Python. Scala. First look at, there we go. That's the one we're using here. And again, you don't necessarily have to use Hadoop at this point. You may want to use it later, but we want to basically set up a Spark cluster. So there we go. It's 2.1 install Spark file. That will give you the instructions to install. All right. Is anybody confused? Did I confuse it? Yes.
So there's supposed to be a folder in the home directory of the user that we log into the machine, or
there should be.
Because I don't see it. So it's referring to a Spark-lab folder, the instructions you send us, and I don't see it.
Okay. I think we may have to actually do a setup on that here. All right, let's take a look on that. Good point. Setup. So let's take a look at setup. Okay, so we log into Spark VM. We should see terminal to update the labs. Okay, so the two things that you want to do, I know I find it a little bit confusing as well too here. Okay, so there is the setup. So the lab prep. So I've given you the zip bundle. You can markdown. Now we're not using Python, so we're not going to be working with that. So the instruction is in lab 2 intro installs Spark file. That's the file that turns in the instructions for this lab. Okay. So this lab is about installing Spark. All right.
I cannot clone the elephant scale dataset.git. I have permission denied, so it's the data step.
If you just pull in the folder.
Yeah, yeah, exactly. I'm in the folder.
Well, is that for the labs?
No, the labs is okay. It's after the dataset.
Okay.
So you're supposed to do this git clone elephant lab datasets, but
Okay. Hold on for
I
just a
can't.
second.
No, the instruction actually says if the data directory is missing. For me, the
Yeah,
data
but even
directory is present.
Yeah, but but first I went to the data directory. I tried to pull, it didn't work, so I just deleted it and tried to pull directly from the home, which doesn't work as well. So both didn't work.
Yeah, I think
Yeah,
I
but
think that I'm sorry. I think the data directory pull is just done in case there's been an update in the data directory. I think the data is already there on the machine that you can use.
I have a question. So this data folder, is that the same that is located on the s3.amazon.aws.com/elephant-scale-public/data/datasets.zip? Is that the same thing? Because I downloaded it from there and it was just fine.
Yeah, I don't know. Again, I just was given these kinds of lab materials just the other day, so I haven't gone through all of it. So let me take a look and see if I can figure something out. Just give me a moment, okay? Okay, if you go into the files directory, you'll see the archives, the file archives in there. Looks like. Well, on the hand, I want to make sure those actually are there. Yeah, so it looks like those are already in your files directory. A little easier to see it this way, I think. So you should be able to find it in that directory, okay?
Which one?
We're looking for, let me find out. We are looking for, so we are looking for Spark 2.4.3 bin Hadoop 2.7. So that should be there.
Yeah, but it's not this. I want the data that data.
Spark 2.
I think he deleted the data folder.
Yeah. Thanks, Norman.
So not the Spark line is the problem, but the data folder.
Yeah, it's the last line of the installation thing.
So data was present. We wouldn't need to delete it, but he deleted it and wanted to clone it again. And
okay. Who was that had the problem with the data?
It's me, Gregory, because like the GitHub in the documents.
Yeah. Okay. I don't know if we're going. I don't know if you're going. We can actually get that back down. But what I'll do, Gregory, is I'll spin you up another machine. Okay. It'll just take a moment. You can go back to. So I'll just do a quick one.
Oh no, but I mean I can sort it out with the link.
Oh, okay. Because like I said, these are no consequences environments. If you completely destroy the environment, don't worry about it. We'll just spin up another environment.
No, but like I'll just get back noise.
Okay. Let me know if you want me to do something like that for you. Okay.
Just see if I can access the file that Roman sent. So be okay.
So yeah, I just wanted to confirm the link that I've sent in Slack, is that the correct one?
I'm sorry?
The link that I've sent in Slack, could you please take a look at that? Is that the correct one for the data?
Let me take a look in Slack. Hold on. I believe it should be.
I've got it from some other file, not from the same one, but it seems like looking at the structure, it seems like it's the same one as the one from Git, but I'm not sure.
Yeah, I suspect it probably is. Okay, I think there's okay. I think that elephant scale uses a fairly standard set of data sets, so they're probably located in multiple places.
I believe everyone is done, no? Is anyone not done?
I am done.
Okay. Everyone else? Anyone else done?
Done.
Or
Yes.
Okay, good. I
Yeah,
think we're. Is anybody having issues aside from deleting data sets? So I wasn't trying to be snarky there. It's actually a real issue. I have done far worse. I've actually even done that RM minus RF slash by mistake because I've left a space out of a path name. It took me 2 days to fix it. Okay. Okay. Okay, so we've done the general setup. So the next smart solutions RDD3. Okay, I'll see about updating the solution here too. So, but again, once we've done that, it's 1:45. So what we'll do is we'll let you guys move on to lab 3.1 and 3.1b. Actually, we do 3.1, I think. Maybe we can do 3.1b as well. Well, let's do 3.1 and 3.1b, and we'll come back and we're going to talk about data set basics as well. All right. So we can get us started on that, and we'll take a break at 10 for 15 minutes, and we'll come back and resume this, and then we'll get on with the rest of the theory. Okay? Sound like a good plan?
Yep.
Awesome. Okay. I will be here with my headphones on, but I will be muted. So if you do ask me something, give me a moment to unmute myself.
Gregory?
Yeah.
What's the reason why this, say, Spark job is implemented as two different tasks, even though this is one single text file? I have 4 cores.
Why?
So if I look at the amount of tasks, look at
Yeah, there is 2 tasks.
Exactly. So the amount of partitions for this text file, why is it 2?
Probably because. Good question. Can I just have a look at what is the file big? What's the size of the file? So it's usually if the file takes like more than 2 blocks, then I mean the file the partition usually in the GFS would be depending on the amount of nodes you have, but like if it's 2 blocks, might be loaded as 2 partitions.
So this is just 134 bytes, and this is a file on the local file system, not in HDFS. So at some point, Spark decides that if we create 2.
Yeah, but like check the Spark. Yeah, but the Spark shell basically uses local star, so it should basically. And you say it's 4 core? I haven't checked the machine, to be honest.
So 4 cores, yes, and that's also what I see on the worker. So on the executor summary, it claims to have 4 cores. Yeah. So you understand?
But the thing is, it depends like the configuration also of the Spark shell itself, because you have this mean, like the parallelism, which is usually 200 by default, which means that it doesn't really care about the amount of core that you have. It will use 200 if possible. And here, for example, like maybe that could be changed to 2, or I don't know. You have to check the Spark shell, the Spark conf that is used by Spark shell. Otherwise, you cannot be sure. Because the default parallelism should be 200, but again, since appeared to be a kind of a custom homemade bundle with Spark, and there might be something else here. You're just talking about the simple word count, right? The first task, the count.
Yes, so there's a filter and a count list, and that's with a sample file with.
Yeah, but you have two tasks, but you have none of it is different. You have two tasks, 4 stages. So you have
one stage?
Yes, but two tasks. Yes, sure.
Two partitions.
Yes.
For a file of 100
Yes.
bytes. Now the question is why two partitions? Why not one and why not 4?
Because you basically just leave the Spark, you put a star, so it chooses whatever is available, and you just basically assume that 2 is a proper number.
Okay, so 4 cores are available, then it assumes 2 is a proper number, and what I'm asking is what sort of mechanism is behind this?
Because maybe that the partition keys it's choosing doesn't have 4, you can't have 4 partitions. So you have only the possibility to have just 2 partitions.
Well, there are 4 lines, so I could imagine.
And there are 4 lines, and I guess 2 are the same. 2 contains the.
Well, but at the time you execute the count, the Spark doesn't know, right?
No. But when you load, no, that's the thing. When you load the file, you load the file because of the count at that moment. That's the thing. It doesn't do anything. Have you tried to check the UI before? If you load the file, you refer to UI, nothing happens. The thing happens only when you do the count.
I understand that. Let me just do this.
Yeah.
There's something like partition.
Yeah, you will have to like.
I haven't executed any count or any shit, and already I am seeing 2 partitions here. And if I execute the count, then I will see.
Where do you do? I don't see 2 partitions.
So there's this one, and there's this one.
You can say get numbers partitions.
Yeah, get num partition. Yeah.
Okay.
Interestingly, what you do is 500 megabytes, you get immediately 16. Only with loading the file.
Exactly. So to me, this is unexpected. I would either expect 1 partition because this is 1 file, or 4 partitions because I have 4 cores.
4 cores.
Exactly. So the question is why 2 partitions?
We have to. Why Spark is doing that?
No, but I think
when you're running count, for example, will it create 4 partitions per core, or will it
stick with 2? So what I saw is just by defining the RDV from the input file, and for executing any action, you have already assigned before running any action. And then when I actually run the action and see the outcome in the Spark UI, I actually see 2 tasks being executed, right?
Mm-hmm. Rob, hello, are you here?
Yes, I am.
Good. My question is there what is free1b file? Because I'm looking at it and it looks a lot like free1 without b.
Oh, I think. Yeah, I think there might be some differences there in just the interface. Again, I haven't had a chance to go through all of these files. I've been trying to struggle with that. So I think without even looking at it, the probable difference is that there's a Spark context, probably like an SC in 3.1 and an actual thing called Spark in 3.1b. Do you see that? I'll have to take a look.
Yep.
Yeah, okay. So what that is that that's the difference between the older version of Spark and the unified version. So almost everything is the same except that Spark object that's created in the B file, because that's the new unified interface to both datasets and RDDs. So SC is just the interface to a context. It just gives you an interface to RDDs. Spark gives you a unified interface. Does that answer your question?
Our goal, we go through 3.1 or 3.1b.
And so the difference, I believe the two of them is just that they're different in the, and I haven't taken a good look at them. I'm still trying to sort all this stuff out. The difference is probably just that you're using a different interface. And other than that, there should be a lot of similar things.
Okay, so it's not a continuation, it's not a...
No, I don't, I think it's, again, just a matter of using the different interface.
Okay, got it, fine.
All right. I have put an inquiry as to where the solutions are so I can share those with you. Now, how did the labs go? Is everybody doing okay? I said I'd check in on that. Okay.
Are doing fine, yes.
Okay. Do you need some more time or do you want to carry on with this? It's up to you guys. You're the ones that are taking the course.
I would like to ask a question, if that's okay.
Yes, of course.
So, when processing a text file and just doing some simple filters and counts, so there is this 100 megabyte file and there is a 1 gigabyte file, right? So, as examples, so we have this 10x difference. Now, when executing the same job, the same filter and count, I see that there is not 10x difference in runtime, but there is a much higher difference. So the 1 gigabyte file takes much, much longer. And I was wondering why is this happening.
Which is the file that takes longer?
So there's the 100 megabyte one and the 1 gigabyte one. So right. I'm just comparing the runtime on both of them. And even though the difference in size is 10x, the difference in runtime is closer to 100x. So why this difference?
It's probably because you are running it you're not running it on a cluster. So there's a lot of memory issues going on there. Okay, so I suspect that there's probably a lot of disk reads and writings going on there. Okay, that's my suspicion at this point.
So then, because the file is much bigger, like the second one, it does not fit fully in memory, and therefore there's a lot of read-write.
Yeah, there's a lot of spillage onto disk.
Okay, that makes sense.
And the problem with RDDs, as wonderful as they are, is that again a lot of that data is opaque. So it's not optimized when it's being spilled onto disk, and we'll talk a little bit about that. Yeah. So so while Spark does have a great in-memory model, a processing model, if we're generally running it in a relatively small environment like we're doing here, when we start to get into really significantly large files, we're starting to really tax the resources, and that's where we often find that layer of clustering. Or the clustering that we use really starts to help, because now we're spreading out the actual computational load into multiple processors with their own sets of memory. So that one file, so for example, if that 1 gigabyte file would partition up in a cluster, for example, if we partition up that 1 gigabyte file on your machine right now, I think these are all 4-core machines. So, there's sort of a physical limit there. But if we had a big cluster and we sent it out, that would maybe go down into, like 100 megabyte chunks onto different processors. And then each one of those individual nodes would have the same performance characteristics as you would have with that 100 megabyte file on your machine. So this is an issue with scaling up in terms of exceeding your physical resources. Does that make sense?
Yes, thanks.
Okay, good. Do you believe me?
So far I do. I will check later.
Yeah. The other thing too is remember is that the bottleneck for a lot of these things is just your computational horsepower and the memory that goes along that we have available to us, which is why we see increasingly movements towards GPUs and TPUs and things like that, as well as really significantly large memory models. So, but we all have certain limitations. So there are some things that work better from an architectural point of view. So yeah, you are going to see that kind of thing, and I'm going to suggest that most of that is doing to disk swapping on these instances. I think if you ran up a larger AWS instance with maybe 16 cores and put a Hadoop cluster on there, you'd see a significant drop in time. Really significant if you were able to use that cluster. But once you don't on Hadoop, you probably will see a similar the drop in processing time. All right. So I just do have one announcement. I have been informed that I have to do something right at noon. So I am going to today only have to leave at quarter to the hour. So our class will finish about 15 minutes early, but I will make that time up by just kind of adding extra time as we go through the next few classes here and there, and I won't be, I'll try and make up that time. Unfortunately, somebody sent me the wrong information. I'm supposed to give a lecture, and they got the time wrong, so I just was informed. So that's just for today only. All of the other days, I'm prepared to stay as long as we need to stay. Okay, so we're going to move and talk a little bit about caching, and this is the ability to save intermediate results, because normally they are not, intermediate results are not saved. Now, we looked at the acyclic graphs, and we said that the graph is built up as a work plan, a logical work plan, and then that's modified into an actual operational work plan, and then as soon as an action takes place, only then do we actually execute the plan. And there actually are no intermediate RDDs. So that is all a fiction that we use to think, to conceptualize what's going on. Instead, the data is just processed in one big long chunk as a series of tasks. So there is no intermediate RDD. There's a very efficient way to do the mapping. However, sometimes at certain stage in the processing, we may want to save or checkpoint that results. So we are able to actually create an RDD at that point that is actually going to be there and persist. It's not just a theoretical construct at that point. We're actually able to grab it and snapshot the RDD at that point in the transformation. And using that caching also is going to affect the optimization decisions that are being made by Spark, because it knows at this particular point it's going to be caching out data. And I couldn't tell you off the top of my head exactly what those are, but there are some there. We'll get into that a little bit later on in the class. So what is the use case for this is that we may have a particularly problematic RDD, in the sense that it requires a great deal of computational power to get it into a form, the raw data into a form we want, and we don't want to keep repeating that computation, because we're then going to use that digested data in a number of different ways, and we don't have to want to recompute it every time we want to use it. So we can basically put a checkpoint and say, okay, no, save it at this point in this structure, save the logical structure here, so that I can pick up and use it again. So because this is not the default behavior, those RDDs don't actually exist during computation, this checkpoints Spark to make Spark actually create the RDD in the form that can actually be persisted. And we'll take a look on that. Okay. So the RDD can persist across operations, because we're basically, like I said, putting a checkpoint in there, and we may want to go back and refer to that work over and over again. So those are the two use cases that we generally put out there. I'm going to use this intermediate result in a number of different computations going forward. I don't want to have to keep recomputing back to this point. So I'll just sort of preach it. It's almost like an ETL transformation. Getting it up to this point, I want to start from this point for a lot of other work, or getting to this point is really, really expensive. So I don't want to have to do it again. This is the one of the use cases illustrated. I have an RDD1. I do a very expensive transformation, and now I'm going to basically do two transformations to get two different RDDs off of this one. I don't want to go through this initial step twice. So what I want to do is basically say, we've done this computation, cache this result, and then proceed from there, so that we can optimize and not have to do this again. So it is a trade-off. There's going to be a cost to this. And so we may have to make an analysis. Is it worth the cost of caching versus the work versus the resources that we have in the RDD? Okay, so let's take a look at what the caching is actually doing. So we have several ways of caching: disk, memory, or a combination. And the caching is done by the executors that are working on the worker nodes. Now, remember, these are all working in JVMs. So there's a JVM running there on the node. It's got a couple of RDDs that it's working on. And so we do have some limits of what we can actually put into memory. So we've got about a 40 gigabyte memory there, larger, if you've actually got that memory, I suppose. So there are memory limits. So once you exceed those memory limits, obviously you're going to have to go onto disk. Obviously, we don't have 40 gigabytes of memory, I think, on these machines. I think we've got only 8 or 4. So what we can do is specify that we want a persistence in memory only, and so we can actually cache into memory. And so we can create a cache. And again, most CPU efficient. Now, it's most CPU efficient because it's not intended for storage, so it's stored in a form to allow low latency of access. And so this is the raw form. So we're not performing any serialization on it. And when we're storing it in the raw form, that the 1 gigabyte of data might use 3 to 5 gigabytes of memory, because again, we're caching for low latency here. So this is just something to keep in mind. The second type of caching we do is memory only serialization. So now we're serializing to memory. Everybody's familiar with serializing operations, writing data out in serializing operations. It is a trade-off between performance and memory again. So now we're saving on memory, but again, we've got computational costs because we're serializing and deserializing. Java serializer is okay, but we have another Creo serializer, which is high fast performance, more compact than Java. And later on in the class, I think we come back, we'll take a look at the Creo serializer. So already we're seeing that in caching in memory, the two options we've got are to cache in a raw form, which gives us a pretty good latency. And but if we want to save on memory, we're going to serialize, but that's going to require a latency time as we do the serialization and deserialization. So there's some CPU intensive. Hold on here. Then we have a raw form, which is called memory and disk. Okay, we'll talk about what memory eviction is. Memory eviction is where, for some reason, the memory that's been allocated to the storing the RVM is revoked, and something else is going to take place. We're going to look at that when we get into tungsten and how this kind of revocation and eviction takes place. But let's just say that there is the possibility, if we're doing memory only, that we could suddenly find ourselves being booted out of memory and our serialized RDD will not be there. So what we can do is, if we want durability, so notice that so far we're now looking at another model, which is where we're actually going to store in memory, and we can page it out to disk. So even if the memory is evicted, we're going to be able to still have it based on the disk copy. So there's a couple of other sorts of things that we can do. We can persist. So this is notice this is caching, and this is persisting. In other words, we're basically getting some slightly different accommodations here. So here's persisting with memory and disk. We saw that before. Here's a persisting with only memory 2. So we're persisting memory 2, so we have a node failure. So what's happening is, again, we're getting replication taking place. So numbers of ways to persist. So let's take a look at sort of the persistence levels that we've got here. So we've got a memory only. So it's deserialized Java objects. If it doesn't fit into memory, some partitions are cached and recomputed. So in other words, if it doesn't fit into memory, it's not they're going to lose the data. It's just the stuff that doesn't fit into memory, we're going to have to rebuild. So, that may not be optimal from our point of view. Memory or disk stored as deserialized Java objects. If the RDD doesn't fit into memory, those are stored on disk and read as needed. So it's a paging scheme. to page out things from memory onto disk. We'll get more into all of these different schemes later on too. Memory-only serialization means that we're serializing as data objects, and by the cache, by the way, is just a shorthand for doing that. Doing the memory only. Stored as memory only serialization, stored as serialized Java objects. We saw that, but there's computational overhead, but better memory management. Memory and disk gives us the ability to page out. We call it spilling partitions that don't fit onto disk. So you'll notice the problem is if we don't have a disk, model or we don't have a disk option in our persistence, we have to recompute the stuff that doesn't fit into memory. This actually goes and pages it out into disk. So again, there's another computation we have to think about is which, from my point of view, is going to be more effective. If I have a really, really expensive computation, I may opt say it's, I'm going to start paging it out to disk. On the other hand, if I have a real bottleneck with performance and disk I/O, I may wind up thinking about, gee, it might just be faster just to rebuild the thing. So disk only is we're going to store the partitions only on disk, and we'll see if we can find a use case for that one. And then we have the memory only 2, memory and disk 2. And this is where we're using the same clusters as before, but instead of using our redundancy failover on the same node, we're actually doing a replication scheme so that we're replicating the partition on 2 cluster nodes so that we can have persistence at that level. And then we're also going to look at later on off heap. And that is a term where we're basically kind of doing direct memory manipulation. So we can even get better memory management. And that's where we're getting into things like tungsten and tachyon and some of the other things. Tachyon is the serializer. Tungsten is the memory management tool. So obviously, if we're putting everything in memory as a memory-only model, then we're going to have to really, really be concerned about how we're managing memory. Do things fit into memory? What is my persistence model? What kind of failure can I encounter with my data when I'm out of memory? What are the kinds of things that, or if I get evicted from memory, what are the kinds of things I have to be concerned about? So all of that will come into play as we do our planning for these persistence levels. So I had mentioned off-heap caching, and so what off-heap does is tweak the JVM memory model. So when we put large amounts of memory on a JVM heap, then the good old Java virtual machine garbage collector will go and do cleanup for us on a regular basis. So the problem is that we do not necessarily want this program running because we don't need the functionality it provides. So so what we want to do is to say, well, how can we free up all this memory and tell the JVM just basically to keep its hands off our memory management. So so what the off-heap memory does is it bypasses a lot of these mechanisms and allows us to manipulate the heap memory in a way that's very similar to how C works with memory. So Cassandra was one of the first systems to experiment with this, and there's a number of others, and we're going to be looking at that as well. So Tachyon is an example of that, where we're basically allocating memory directly. Okay, so in other words, if we look at the JVM standard memory model, it is using the on-heap memory, which is in the JVM, and anything that's not in the JVM is managed in the JVM is going to be inaccessible. But the problem is once we put it in a JVM and manage it there, we've got all of this kind of overhead that's taking place like the garbage collector. So if we go back to C, what C does is it actually gets memory directly from the hardware using malloc. If you have never used C and malloc to memory, you've never lived dangerously. It's a thrilling experience. We used to malloc stuff all the time because that's all we could do to get memory. So once we...
I have a question.
Yeah.
Sorry, I have a question about the memory that you can use from the Linux system or whatever underlying system it is using. Is there a limitation on how much memory you can use? Because potentially, if you want to store something too big, you kind of like blow up your cluster, because the thing is, like, on the other scenario, you just blow up the executor dies. Worst case scenario, you just spawn another one. But in that case, you might completely destroy the node, right?
Yeah, and I think you can tune the parameters for that. I can't tell you right off the top of my head, but I think there are some guidelines as to what you can access and what you can't access, and I will get into that in the tungsten model in particular, which deals with those kinds of issues. And the memory that it actually uses is also split up into different areas, and there's a whole lot of memory management issues. So we will circle back to that when we talk about tungsten and address those kinds of issues. Okay.
Okay, thanks.
All right. Okay. So so the basic concept of off heap is don't use memory allocation through the JVM. Just go outside JVM and manipulate the memory directly on the host node. Okay, so this is a really good solution. It gives us lots more power in terms of being able to access the memory. Plus, we're not running all these processes that actually interfere with our computation. So if you can see from the diagram, we're basically getting memory that's outside the JVM. And then we also want to do, since we're now outside the ABM or the JVM, we can also use what we call custom encoders, and we can basically do very, very tight storage of the objects and serialization, which gives us even better utilization of the memory that's there. So this all is managed through the tungsten engine, which is the standard way to do it now. So we have a big section on tungsten later on in the class, so we'll get into it and explore it. But at this point, all we want to understand is what is this off memory or off heap caching, and basically, in a nutshell, it's that the ability to bypass the JVM memory management and manage memory directly through the use of tools like tungsten. Okay, so one of the things by the way, a couple of people asked me what was the difference between those two lab files, and I didn't look at them, but I have a suspicion that this was actually the kind of difference that we look at. So the first one is a standard RDD. Now the SC dot is the interface to the original Spark 1 point whatever it was before they had data sets. So this is the Spark context, and it produces RDSs or RDDs. Sorry. And if we take a look at the count, running count on this, if we count it's 0.9, if we cache it and count it, it's 1.7 seconds after the first cache, and then we count it again as 0.046. Now, the second one is a data set, and what a data set does is it operates, it's accessed through this, the SC is gone, it's actually been incorporated into this. So the data set is going to read the text file, and you're going to see it's going to take a little bit longer to count it. In this particular case, cache it, but when we cache it, the count generally tends to work the same. But then after the cache, the count is a lot faster, and that is because of what's happening in the caching performance here. So in other words, we're using a data set, we're using a different kind of caching mechanism because we've got a data set, and so we're getting a better performance. Okay, so again, we've got a little bit of a decay here, and we'll start to get into looking at these kinds of stats when we talk more about data sets and figure out exactly what it is that's happening here to account for some of the differences in these values and why we're seeing the numbers we're seeing. So tungsten is the caching, and tungsten, as you can see, take 100 megabytes of data, and tungsten uses a cache size of, or the RDD uses a cache size of 334.5. So I'm assuming this is all megabytes here or whatever. I'm not sure what that number actually is. Oh, there it is. Yes, it is. So the RDD name, and we've also got a text file. So we've got basically the same operation taking place. We're caching the entire thing into a number of partitions. And what's happening is that the size in memory is particularly interesting. Now, why is the size in memory so different? Well, one of the things is we've got a data set, and so we have access to typing information. And because we've got that, we've got the ability to figure out more effective serialization. So, so what Tungsten actually does is it's able to go and figure that out with the data set and get some very effective computations. So this is one of the reasons why data sets are so popular now in the Spark community. So memory is the new disk. Again, I'm not sure how current this is. 2019 is probably current. So year $1,000 per gigabyte. New disk, $3 per gigabyte. I'm not sure what they're measuring there in terms of what dollars, but anyway, so we generally can look up to about 2 terabytes of distributed memory on a typical cluster. And so because of that, because of the low cost of memory computation, or the low cost of memory, it's starting to become more and more attractive to be able to add more and more memory, to do more and more memory more and more processing in memory. So when I first started actually doing data analytics back in the 1980s, I had like a megahertz processor. I had one of them, and I got a $10,000 disk drive, which had almost 350 megabytes on it and weighed 50 pounds, and we had to wheel it in. So a lot of what we were restricted to doing was just sheer physical resource management. So the direction Spark is going is actually quite good, because as memory prices keep falling and falling, because the Spark model is already in memory processing, we can take advantage of that, and we get faster and faster kinds of computations, less and less spillage to disks, less and less need to actually store things and swap things in and out on disks. Let's also remember that Hadoop was also built at a time where we still had more expensive memory. So it might have biased some of the decisions that were made there. I'm not saying they did, but they just might have. So what happens is there's a lot of in-memory file systems. So Tachyon or Alexio, I don't know how to pronounce some of these things, and Ignite. So there's a number of other things that we can basically put as layers on top of this file system. So instead of talking to Hadoop directly, we can now basically do an in-memory file system caching, which speeds up our performance tremendously. And I do believe we'll touch on some of these things later on in the course. So we have a number of ways to continually leverage the increased amount of memory available per buck or per dollar for us. So Tachyon file system is one of them. In-memory file system. It is backed by HDFS, which means that it's really a projection of HDFS. Doesn't use JVM for storage. There's the ID here. So in other words, we're bypassing JVM entirely. And so that gets us out of the garbage collection, and it can accommodate very large data sets in terms of petabytes. And I think we saw something here about petabytes right there. So Baidu uses a 100-node Spark cluster with 2 petabytes of memory. I'm assuming that's complete. So I'll go back to the question about what's the upper limit. I'm not really sure. It may be something incredibly. It may be the answer just how much memory can you afford. But there's obviously going to be some practical engineering limits, which we want to take a look at as well. Okay, so this is the idea, is that we run this in-file memory system, and we've already looked at that. We get this sort of effect. So it doesn't use the JVM, so storage bypasses all of that stuff. And again, this is what we call automatic data promotion, which is basically moving data out of the Hadoop cluster independently of requests in order to populate the file system in using what we call cache policies. So there's a lot of different things we can do. Pinning data in memory, in other words, don't move this out to disk. You know, we have a lot of experience with paging algorithms and that sort of thing, which led people to come into think about applying those kinds of concepts to these kinds of solutions. So there's our Tachyon memory. Again, it's transparent to Spark. It's a layer that goes into here. So Spark is working with a file system. Just happens to be a cached file system, which is basically backed in memory. Okay, so and like I said, this is generally a presentation of this, and one person said, just think of this as being a virtualization of this. That's not quite right, but again, you can think of the fact that we're introducing another layer of a staging area that speeds up the actual access, because now we can do optimizations on how the data gets into memory and when it goes into persistent storage. RDD persistence. So we do our persistence using the various parameters, and we're not going to get too involved in this. So we'll because we're going to spend more time on data sets and data frames, but we just should know about it is that we saw persist before. And I'd mentioned that caching is kind of a shorthand for persist. And so cache, you can see there is the same as persist, storage level memory only. It's just a faster and easy way to write it. So our persist, and so persist and cache are basically the same operation. But then, of course, we'll use the persist with arguments in order to tune the actual persistence mechanism. Example down on the bottom is when we actually want to do this. Again, we're using the SC context here, so we are working with the older interface. So we've got an RDD called visits, then we've got an RDD called page names, and we're going to do a join. So the join is a very expensive operation. So if we have other things that are going to require a join, we don't really want to recompute it. So we'll cache that join so we can reuse it in subsequent computations. There's an example of where we just don't want to recompute something because it's too expensive. Okay, so we're going to try this out. And this is our lab for caching. And this is going to be lab 3.6. Now, I haven't gone through these labs yet. I'm still just actually kind of getting all the logistics here sorted out. So I will take a look. Now, I do have solutions for this, but not yet. I've asked Mark to give me the solutions, and I'll see about providing solutions for everybody tonight so that you can actually go and look at the solutions to all of the labs as recommended by the course designer. Okay, do we have questions about caching? I know I've deferred a lot of the discussion into our module on tungsten, but this is really just sort of a high-level overview. Okay, so don't worry too much about the low-level details. Any questions about caching? All right.
Yes, I have one question.
Yes, go ahead.
So there was memory and disk, and then there was disk only. Why would you use disk only if there is memory and disk, and whatever doesn't fit in disk is spilled into memory anyways?
I think it's more of a use case issue. I mean, I think what happens is that if you want, like, if you're doing a really expensive computation, and like I know I was working with some people in Statistics Canada, and they were doing a query, an SQL query, and it took 3 days to run the query because of all of the complexity of the data. And what they did was once we had the results of the query, that became their operational database, and everybody worked off that. And it was actually stored in a separate database. The use case here is that getting the data into a form that we're going to want to use over the long term, not just in the immediate, that's something we're going to come back to over and over and over again. It may be more efficient to cache it to disk, and then when we actually come back and get it out of disk, we're not burning up memory. So I'm suspecting the use case for that is that when you're looking at wanting to persist something to disk for a relatively longer period than the immediate calculation, maybe you want to save it there and use it in another problem. That's my take on it, and I hope I'm right. I'm not sure of anybody I've ever talked to who's actually used that. So I'll check for the other use cases, but that's the use case that occurs to me when I first think about it.
Okay, thanks.
Okay. Yeah, I don't really think caching disk only is something that you would normally do if you're just running like a Spark job, because I'm not seeing any advantage to it, but I can see advantage if you're caching stuff that you're going to come back to much later, but you don't want to you don't want to occupy the memory in that intermediate time. Okay, so I'll let you guys get to work on that. I'll check in with you in about 10 minutes and see how you're doing. And then that'll probably bring us fairly close to, so it's at 7 minutes after the hour. Yeah, we'll probably be able to finish this up and start talking about data frames today before we take a break. So I'll give you guys about 10 minutes. You guys are really good, so I don't think you're going to need all of the approximate time that's required.
You don't have a thing to add memory only, because it's the default. Maybe, yeah, and persist. But this is done and persist.
It used to be a memory only serialized. This is the random data, right? So it used to be serialized. Now I'm doing.
Now you have to did you unpersist?
Unpersist with brackets.
Yeah.
So
And now you have to count whatever.
Yeah.
Strings, what's it? Internet, like are they sort of cached as singletons within the JVM? So if I use the same string, like I just define two variables with a string literal ABC, will Java create two ABC objects, or will it be the same object in the end?
That's a good question.
Because I mean, I think Ruby kind of does that explicitly via symbols, and then I think Python does that automatically, or I don't know exactly, but
Excuse me, what was that question? I didn't quite catch it.
so this is more of a JVM question, I guess. So I know that some languages either explicitly or implicitly they automatically define singletons for some let's say values like short strings. So if my application I use the same string literal 1,000 times, it's not like it's going to create 1,000 string objects, but it will just reuse the same object as a singleton and just provide a reference, right?
Yeah.
I don't know if this is the case in the JVM or not, because of course this has implications on the amount of memory that deserialized data structures will.
But I think it's syntactic sugar and it creates symbols like for each of them referencing the singleton.
So are they cached in the JVM first of all? Because I was thinking about the Tungsten project.
Yeah. So I mean, this is completely unrelated to Scala or Spark. That's the general question of JVM, whether there is this mechanism within the JVM that it is sort of or tries to be smart in that sense to keep internally singleton objects for this repetition.
Okay, there's actually an interesting sort of answer to that.
Immutable. Okay.
Yeah, in the sense that the original RDDs were opaque, so that kind of optimization could not have taken place with the original RDD interface. But with the unified dataset interface, there is a mechanism like you're talking about, the typing with the RDDs that allow for that kind of optimization to take place. So a lot of it has to do with the introduction of typing into the RDDs, which is where the new RDDs are different than the old ones. They allow for kind of hooks into that, not that specific, but that type of optimization.
So what I'm seeing with these exercises is that they are very simple, right? Just run a couple of months, but the interpretation of what we see as an outcome, that's more challenging than I had anticipated. And in that regard, they are quite interesting just to revisit later and really try to grasp what's exactly going on. Because some of the problems are not that intuitive, or so yeah. I guess there's some homework in this.
Yeah, well, there's a lot of things going on under the hood at this particular point too that we have yet to explore. Okay. Well, I'm going to suggest that we take just a few minutes here to close off. I want to get about off in about 10 minutes, but I'm just going to introduce as a kind of this section that's at the end of this module as a kind of a segue into data frames tomorrow. and this is this notion of key value pairs. And this was kind of one of the motivations behind sort of the new kinds of RDDs, where we work on key value pairs. And we all know what key value pairs are, so it's fairly straightforward. But we also can use the key to do various kinds of operations. So count, group, reduce, sort are fairly typical examples of pair functions or pair operators. So we won't. So group by key does what you would expect. Groups all values the same key. So we're grouping all of the elements together, and we can do a group by key and then collect the results and get our arrays back appropriately. So we're just going to take a look at kind of the underlying mechanism, because group, and this is where we wanted, and this is the point I just want to get to before we go as an introduction to what we're doing tomorrow. Grouping by tends to involve a shuffle phase, because we may have keys in multiple nodes, so they have to be brought together through some kind of shuffle operation. So this is one of those performance hits that we take when we start to do grouping kinds of operations, because now we're moving stuff over the wire, and that starts to become a little bit more expensive. Okay, so and I just want to kind of go over just a couple of those points. So we can join on a couple of pairs. So we'll just take a quick look at a code example. We've got a bunch of people that comes in a CSV file. The format of the data looks like this. It is still at this point opaque to the RDD. These are just still strings of text. But what we can do is we can put it through a data transformation, create an RDD of people, in which we tokenize the string, and then we basically create a couple of variables or keys, or a couple of key value pairs for all of the things. So, and then we take those two tokens and we create them from int, and so we now have our name and a gender and age tokens. So we take the first, second, and third tokens and convert one, and we wind up with the tuple. Now, once we've got that structure, we've got something a little bit more easier to work with, because we've imposed some structure onto the underlying RDD. And so what we can do is now do filter, and in this case, we're going to filter out all of the men, or all of the males, and we wind up with a new RDD, which has that filter in place. This could not be done without a pair, because again, the data would be opaque. So data is a simple RDD of string type. Each line is an element, and we wind up being able to tokenize this and take this flat RDD and put some structure onto it. Okay, so now what we can do is we can go and selectively do some comparison operators that we couldn't do before when it was untokenized. We're actually able to do a reduction here, or a filter, which we couldn't have done before without a rather extensive computation. So in this particular example, what I just wanted to kind of close off today with is this idea that in Scala, we're writing this code here and doing a count by key, and then we over here have to parallelize things and then filter on each of the individual chunks. So the idea here is that, and we're not going to do this lab today. I just want to introduce this as a concept for tomorrow, though you can try to do this if you want. So there's a couple of other interesting things here that we can do. And this is where we're going to be able to, for example, reduce by key is a very efficient operation. Sort by key are operations, and some of them are going to be require shuffles, and some of them are not going to require shuffles. And we'll get into some of that kind of stuff later on. But I just wanted to introduce that as a kind of a concept for what we're going to do tomorrow. Basically working with these kinds of Oh, hold on for a second here. Just one moment. Sorry, I accidentally muted myself there. Okay, so again, this is the idea of the transition from this into data frames, is the idea of imposing structure on something. Okay, so tomorrow, what we're going to do is we're going to come back and start looking at data frames. We'll make through, and that shouldn't be too complex, and then we'll get into data sets. And as we get through that, we've kind of finished the initial architectural kind of position or architectural part of the course. And we will be looking at, I'm not even sure where those slides are at this point, but anyway, we'll go do a little recap on what we're actually going to be covering off tomorrow. But what we're going to be doing, so how are you guys, enjoying things so far, or how are things going for you? I'm going to do a little poll before we leave. Suggestions? Options, opinions?
Might be a little bit too late, but can I ask a question about the latest exercise that we did?
Yeah, sure.
Well, maybe not a question, but rather I just wanted to confirm something. So incidentally, I've tried doing the serialization, storing in memory only without serialization, and with in memory with serialization, but not for the data which was like the examples that we needed to work for, but with the random data.
Okay.
And I figured out that serialization doesn't really help. So it reduced from 105 megabytes or so to 102. So does it essentially mean that serialization here involves compressing the data as well?
Yes, I believe it. Yes, that's a critical part of the serialization. Yeah. That's why you're able to get that compression. So if you've got truly random data, then, the serialization is not going to give you any significant data compression.
Yeah, okay, thanks.
Okay. All right. Well, I'm going to bail out now in a minute, but what I'm going to do is, I just want to get your opinion on something. I am going to be shutting down all of the virtual machines after class so that they don't get attacked. And then I'll start them up just before class. Now, if anybody wants me to start up the machine for them at another time, just contact me by email or on the Slack channel, and I'll put your machine up for you. I just don't want the machines to be damaged. So I will do that in probably about 20 minutes or an hour, just to let you guys get a chance to kind of close up what you're doing. So it's about 1:45 now. So let's say within about an hour, I will shut the machines down unless you tell me specifically you want your machine to stay up. All right, does that make sense?
Yep.
Okay, good. Yeah, I don't want to inconvenience you, but at the same time, I don't want us to do silly things. Okay, all right. Well, I will end it for today, and we will see you guys tomorrow, and when we explore the wonderful world of data frames. So hang tight and have a great evening. Take care, everybody.
Thank you.
Yeah.
Bye.
Bye. Thank you.
Ciao.
Bye-bye.
And remember, I'm available on Slack. All right. So what we looked at yesterday was the RDDs, and looked at a sort of the idea of how they were conceptualized from the logical perspective versus sort of what was going on in the underlying implementation of them. And this gives us a basic idea that we're going to follow through with a little bit today as we get into data frames and work with the data frames of the idea that this conceptual model is opaque to us, or makes the underlying implementation relatively opaque, so that we can model the processing from a strictly logical point of view, which gives us a logical work plan, but then this logical work plan is optimized in some way. And then we also wanted to look at how we can optimize that even further. The one point that we did make about the RDDs is that they are relatively opaque to Spark, so that there are some optimizations that we could do that Spark can't, because it doesn't have a semantic sense of the data. So the other thing we looked at also was this notion of caching. which was a fairly interesting notion where we're looking at some things that are all coming into optimization as well, where we're looking at being able to fundamentally save intermediate results for further processing. Okay, so any questions before we begin?
So yesterday we were using data sets, not data frames, right?
Yeah, we were. Yeah, well, here's the thing about that terminology, and I find, and I'm also guilty of sometimes being sloppy in my terminology. Data frames are basically similar to data frames as referred to in other things like R. We're really looking at tabular data, like SQL type of data. Data sets in Spark is a unified interface to both RDDs and data frames. And that is where you were noticing the other day when you were actually working on it, there's two interfaces to Spark. When you were at the command line, one is the SC interface, which is the Spark context interface. That's the older interface, which is basically allows you to work with RDDs. The other interface, which was the Spark object, is a unified interface that allows you to work with both RDDs and data frames. And that interface adds a little bit more functionality to the old RDDs so that they become, they're easier, more efficient to use. So data sets are a unified interface to both data frames and RDDs. And that's just the terminology. Does that answer your question?
Yeah, thanks.
Okay. So I personally get a little bit sloppy. So if I get if I sound confusing about it, sometimes just call me up on it. Okay. So let's we're just finished off with this, and I'm just going to take a look at a couple of points in here, and then we're going to jump into data frames, and there's some various labs that we're going to do just to experiment with the underlying model. And this is what we stopped with yesterday. And this is where we're adding a bit of structure onto the RDDs, and I mentioned this notion about introducing the pairs. And I think we looked at this example here, where we maybe there wasn't this one. I think we did a little bit further on. Well, let's go back here for a second. So we also introduced some idea of underlying shuffles here. So the key value RDDs, and this is kind of the evolution of RDDs, provide some operation centered around the key, and this is kind of an evolution towards dataset is the pair RDD. Now, once we've got this, we have this underlying structure. We have a little bit more power that we can use, and we can get a little bit more efficiency. So the standard kind of operations that we can now employ are counting by keys, grouping by keys, reducing by keys, sorting by keys, kind of fairly typical kinds of things we would expect to be able to do. The count by key counts all the values by key. So we get a map of keys, and this is would be considered an action because we're not getting an RDDD, we're getting a counts. So now there's the example of our pairs, and we're doing a count by key. So we've got fruit and some value, we're parallelizing it, and we wind up getting a map of strings and longs, which is obviously not an RDD. So this is going to be considered to be an action. Remember, the thing that distinguishes an action from a transformation is that transformations on an RDD produce another RDD. Actions produce some other kind of data structure, which is really the termination of that RDD's lifeline or life cycle. Group by keys return all values of the same key, so it's a form of selectively a form of selectively extracting the data. And we're going to come back to this kind of notion of the different optimizations on when we're doing grouping operations on the data. There are some significant savings we can get if we structure our grouping operations appropriately. Then this is one of the topics we will be delving into in more detail later on. So here's in our example, we have our pairs again, our pairs. I was looking at this one and saying that could sound confusing, but we've got our pairs, and the grouping by key collects them into, again, an array of strings and iterables. But again, because this is not an RDD, this again becomes an action. The group by key, and this is where we start to look at the underlying issues that we have with the efficiency, is that because we've got this data distributed on the nodes, a group by key usually involves a shuffle phase, which means we're going to have to reorganize the data in order to get the grouping, because that data may be distributed. And that's where we start to get a performance hit. So we're going to address this kind of issue as we go forward. But at this point, it conceptually should be clear that when we start grouping data, we have no guarantee where that data is going to be. So we can assume generally it's going to be random. And if it's randomly distributed, then there's almost definitely going to be some form of shuffle going on. Remember, what shuffling is: the process of reorganizing the data on the nodes. And that becomes expensive because we've now got network I/O that we have to invoke as overhead. The other thing that we have that can be very expensive is the use of joins. So that we can now, with our pairs, talk meaningfully about the concept of joining RDDs. And the example there is we have R1, which is a group of pairs, R2 is a group of pairs, and we can join on the key value. Okay, so that is another example, but again, it has optimization implications because there's going to be performance issues depending on how that data is distributed. So we can see there's going to be a fairly significant example or fairly significant issues coming up. So here's the example that we had, and this is working strictly from an RDD point of view, where we are imposing structure onto an RDD. The interesting thing, at least I think is interesting, is that there's no underlying Spark mechanism that allows us to extract this information. We're doing it manually, but what that means is that if we are imposing structure on this manually, that structure is opaque to Spark, and Spark cannot optimize on that. We may be able to optimize for some of the things that we're doing from a logical perspective, but Spark does not know about that structure, and so it is not able to optimize the work. It can do the work because we're defining the structure for it, but there's no way that it really has naively or natively to optimize it, which is what kinds of leads us into the notion of the data frame. So the data frame is going to basically take this concept of having structure, but now making Spark aware of what that structure is, so it can optimize, particularly with Catalyst, the operations that are being done. So there's no way here that Spark, from its perspective, can optimize any of the operations that we've got, because it doesn't really know what this structure is. So this is where we hit the limitations of the RDDs. And again, this is where we've imposed structure on an RDD, but from Spark's point of view, the RDD is still basically a string that we've imposed the structure on. So our structure is not going to be particularly useful. It allows us to do a number of things that we couldn't do before, and we can do this grouping with the pairs, but it's still not really adequate. So the idea here is that this is a better sort of approach. Now, we're not going to do this lab at this particular point, But I will mention just a couple of things. If you want to do it, you can go right ahead. But I think we want to get into the labs on the data frames instead. Reduce by key is combining values of the same key and creating the new new RDD of pairs form. So that's a little bit better. Reducing by key, so we apply some function and we wind up able to reduce by key. Okay, but we're still rather limited on this, so I'm going to just go over the last couple of points here, and then we're going to jump over to data frames. So we have just an example of where some of that optimization is taking place in terms of an actual task, as opposed to being able to work with the underlying data. This is just a little example that gives us the word count, the old word count, counting the number of words in a string problem. So we've got a bunch of text, we split it into words, and then we map these into count pairs, and with the word value, and then an accumulator associated with it. And then what we do is we just reduce by key, which goes through and accumulates across each of the keys all of the values and coalesces and condenses them down into a final count. Now that is, if you stop and you think about it, that is a little bit more efficient than grouping by key. So and stop and think about, why is it more efficient? Any suggestions as to why a reduce by key wouldn't invoke the same kinds of overheads as a group by key? Any ideas?
Well, grouping needs to know all the other tuples or whatever.
Right. Okay. I think I see where you're going with that, and I think you're absolutely right.
It operates in the partition level. So reduce by key basically does the computation on the node where it is, and then the driver gets the result, where group by key is to shuffle, because some driver might not have all the other keys. So you have to kind of like do a shuffle before being able to do a group by key. That's exactly right.
That's exactly right. So it's again thinking in terms of the implications on the data shuffling from the node. So perfect. Exactly the right answer. Okay, so I'm going to just finish this section up so we get the basic idea. And I think we're going to. Okay, there's this one other thing here. I think I want to. Okay. There we go. So there's just a couple of things here about optimization I want to cover before we get to data frames. This first one is this notion of implications of caching. So this is, again, this is the classic time versus space trade-off. So if we take a look at processing time for serialized data versus raw data, and this is our latency, we'll notice that we get a very, very dramatic difference in performance as we go up in size in terms of processing time. But remember, again, the trade-off here to get that raw processing time is that fact of using 3 to 5 times more memory than we did than the actual RDD. So this is one of the things that we are going to take into consideration later on when we talk about optimizing, is what's going to be my trade-off on the use of various kinds of caching approaches. Here's the other aspect of it, is serialized caching uses less memory, but the processing time is more. So my RDD size in megabytes, and then the memory footprint, which is the amount of memory actually being used in order to store that RDD as a function of size. And so there's our classic dilemma right there, is that serializing data gives us slower access time, but it takes up more memory footprint. Okay, so that's basically what we wanted to just really emphasize there. So a couple of guidelines is that if your RDDs fit in memory, then just use the memory only. It's the most efficient of the techniques. And if not, use the serialization. But then we have to choose for our optimization a fast serialization library. So things like the one we were looking at the other day. Yeah. I'm sorry.
Okay. I thought you were thinking about that serialization library you were mentioning recently. You didn't find the name, or did I miss something?
It's Tachyon, I think. I start to lose track of all these different names after a while. There's a number of different serialization libraries that we can use. Java serialization, generally, I don't think anybody really seriously considers just using standard Java serialization anymore, not with the availability of the other more rapid serialization libraries and efficient ones. The term spilling to disk is the idea that it is basically paging out the memory. So we want to try and avoid that as much as we can. But if we have a situation where we're going to start imposing lots of disk I/O, it may actually be faster to recompute. Any suggestions why it might be faster to recompute? Why would it be faster to recompute than going out?
Because maybe you already have the source data in memory?
Exactly, because very often it may be a lot faster to recompute because we're going to be just working with memory alone, okay, as opposed to disk I/O. So recomputation, if it's all done in memory, is going to wind up being faster. Replicated storage for fast fault recovery, that's what we looked at when we had that multiple node storage recovery. Remember the notion of off heap is where we've got Tachyon. That was right. Okay, so we have multiple executors sharing a memory pool. This will be one of the themes we see when we get into tungsten is that optimization is efficient because we bypass all of the nice safe sandbox memory memory management facilities and work with the bare metal essentially on our own. So the idea is, and we're about to going to do review questions. We'll just do a couple of we've already got that. So just remember again as we go forward what this stuff is. We have a Spark session which has a number of actions. Actions are then broken down into stages, and these are then mapped out into tasks on the nodes. Just a reminder of some terminology. Okay. So now we're going to jump into data frames. Okay, so this is the model that we've looked at already before. RDDs we've just gone through. And the advantage to data frames is that they are relational, so they fit very nicely with a lot of the data that we're already working with. And the big advantage we have is that we have this Catalyst query optimizer, which enables us to get even better optimizations. And that data set unification is where we started typing the RDDs using type data. And that allowed us to integrate a lot of more useful optimizations, both from a memory perspective and a performance perspective. And then the Spark object gives us a unified interface to both of these underlying concepts. So there is actually a second generation RDD, which incorporates a lot of the ideas that came out of data frames. So in data frames, we have it organized into tables or columns, and it's basically a relational data set. And we can build these from various kinds of data sources, which also have some kind of structure imposed on them. We can build a data frame from RDD. Using pairs, we kind of saw a primitive form of doing that. Structured data files, Hive tables, external databases. I think the issue for a lot of people is that this is so ubiquitous now in terms of structuring data that thinking in terms of a table does not impose any really undue constraint on our problem. So we can actually now start thinking in terms of querying using a data selection language and SQL. So the underlying architecture looks like more like this. So we have RDDs. So RDDs are still accessible, as you can see that arrow on the right here. So using my Scala, I can still work directly with RDDs, but I can also work with the data frame API and the SQL query language. But where we get the performance is then we add this Catalyst optimizer layer in here, which we aren't able to access on our basic RDDs. So RDDs have the data. Data frames have data plus scheme. So this is the way to think about a data frame is RDD plus schema. Notice that, like we said, we were doing that. I started off a little demonstration where we had imposed a schema on the RDD, but there was no way for Spark to know what that schema was other than our own code. So Spark was kind of blind on the manipulation. If we go back to this diagram here, when we were looking at that pairs of data and the pair operations, we were still operating down here. So that was not an acceptable approach from an optimization point of view, because the structure was not known to Spark. So this introducing this layer of the Spark SQL layer and the data frames allows the Spark to become aware of the structure so that it can perform the optimizations. So we're still working with RDDs at the bottom level, but now we're making Spark aware of a structure that it can use to work with the RDDs. So the data frames now have a schema that is knowable by Spark, and we now have a unified way to work with the data. And we can have the various kinds of things that would be functionality that would be appropriate from or not appropriate, but consistent with what we're used to in the SQL world. And by the way, that often means that we have the opportunity to transition a lot of query type logic that we may have somewhere else into Spark without having to modify our logic into managing just the underlying RDD. Okay, so a number of supported formats. So there's a whole variety of formats that are supported. Built-in formats are ones that are supported directly by Spark, and then external ones which can be supported. And I believe those are means that's exported with an add-on, and that pretty much covers a lot of the main sorts of kind of tools that we might actually be used. So the case for the data frames is number one, it allows us to access data from multiple sources. We don't have to extract data and then transform it into an RDD for processing. We're able to really import it directly. The high performance Catalyst optimizer, and we'll talk about how that catalog, I think we'll get into that in this lecture, but then we'll come back and look at it in more detail later on. The Catalyst optimizer is going to construct similarly to the directed acyclic graphs. It's going to construct a logical work plan, and then from that it's going to generate multiple possibilities for implementation plans, and then choose the one that is optimal out of that. So it's actually a pretty interesting approach. I think it's actually I was listening to a couple of lectures by the guys who invented it, and I thought, wow, that's really somebody really earned their money on that one. It's really a lovely piece of engineering. I absolutely love it. However, because we also have the structure, it also has implications for memory use. So now, instead of thinking of just writing data in kind of big chunks, we're actually thinking of being able to write data at an object level. So that structure gives us additional things. I think somebody noticed that the other day when you were doing random data, you didn't get a whole lot of savings in terms of storage because the data was random. There was no way to actually optimize what was going on there in terms of the compression. But once we start working with objects, then that gives the memory storage routines, and particularly tungsten, able to some hooks in which they can do a little bit more optimization. And this will show up in the performance numbers. So if we take a look at time to aggregate 10 million int pairs, so even using the pair structure that we had at the last section, those last two lines down there will only look at the Scala rather than rather than the Python. So we're taking 4 seconds, just over 4 seconds, to do the integration. But if Spark knows about the structure, then you'll notice we've cut our processing time in half. So this is where we get the advantage from giving a schema to Spark that it can use. So again, we come back to the idea is that when we did the pair example before, we knew the schema, Spark didn't know the schema, Spark wasn't able to take advantage of it. Data frames gives Spark an opportunity to look at the schema and be able to do optimizations based on the schema. So this was the primary consideration for really introducing the notion of a data frame. Okay, so let's work with data frames. Data frames can be created from any kind of structured data. So JSON is a perfect example. From that, we can do a data frame. Now, what we're seeing is the Spark object. So we saw SC before. That's been replaced by Spark. So Spark now is the unified interface into the data sets. So we're reading a JSON file, and we're creating a data set or a data frame from the JSON file. And as you can see, when we actually get the output here, we get a data frame that's coming out, and the data frame has the structure. We can print out the schema of the data frame, and we can show the data frame, which in this case is going to give us a table which looks pretty much like any other table we would get in any other kind of relational system or structured system. We're not going to do the Python. There we go. So we can now query and use queries on the data frame using DSL. So now we've created our file here, and now we can do a select on name and show show the results. We can filter on the we can filter, do a filter on the data frame to pull out all of the names that are equal to John, and we can then show the result of the filter as well. So there it comes out. We've got John. So the excuse me, just a second here. There we go. I got a little issue with my mic. There we go. So we can filter out the data set, the rows, and we show the rows that we filter out. We can filter on, and there's a couple of different syntaxes here. So we can do a variety of different ways of doing this. We wind up with our result here. So And we can also filter on using other kinds of queries as well. So the idea here is that once we've got that structure, we're able to go and extract data in a variety of different ways. So there's a comment. So we would expect that the data frames would support the kinds of operations that we're used to. So selecting columns, joining, aggregation, and a query is composed of the operations, and the expressions are passed as arguments to the operators. So here's a query. This is what we were looking at before. So what we're doing is filtering through the data frame, and we're grabbing every row where the name value is equal to John. So this is again fairly straightforward. The df name specifies the column, and the value, of course, John. So this is again done so that hold on here. There we go. Okay, there we go. I have the connection to my microphone just keeps coming loose, so I just don't want to suddenly drop out. So so we're looking at again a standard query operation. We have we get a column object back. So again, in plain English, is where the value in the column name is equal to John. The triple equal sign is the equality operator, not a double equal. So this is also another syntax that we can use to do this. So we can filter on where name is equal to John. The difference being here is that it's the triple equal sign is used in this format, whereas as we're using the double equal sign in the embedded format. So this is the shorter version. But we do also are able to do this in terms of equality, because we now also have the ability to use it with various kinds of type data. And so we've got the standard kind of data that we would expect: integer types, numeric types, long types, float types, and double types, and also a large decimal type, which is also there as well. So there are a variety of different supported data types, which Spark is aware of: strings, binaries, which are blobs, booleans, dates, timestamps, fairly standard stuff. And we also have various kinds of more complex nested structures, arrays, map types, exactly what you would expect, and these map up to the appropriate or the corresponding values in Scala and Java or in Python. So we have arrays. There we go. Arrays, sequential arrays, map type structures, and general structures. So the supported data types now is a richer set of values than or a richer set of tools than the original RDD, which was basically untyped. All right, this is where we start to get to the interesting stuff, which is the Catalyst optimizer. So, using the same idea before with RDDs, they were processed in a lazy manner, which meant that they weren't actually processed until we hit an action. And in a similar way, the Catalyst optimizer is can be used because data frames are evaluated in the same way. So we'll have a series of transformations of the data expressed in the DSL that we're going to apply to the data. And then what Catalyst does is optimize those by looking at various what we call work plans or physical plans. So one of the obvious optimizations it has is to look at pushing filter operations up, which means rather than filtering later in the sequence of events, it'll filter earlier to reduce the amount of data. And it does other kinds of optimizations like expect the logical meaning of the operation rather than arbitrary functions. That's something you can't do with RDDs, and it will know how to optimize specific operations like filter, map, and join. Now we can do almost anything we want with the data, but the ones where we're sticking with the data frame operations, those give us the ability to actually let Catalyst do the operation, do the optimization. Okay, optimizer may not be able to optimize arbitrary user functions because it doesn't know how to evaluate the cost of those arbitrary functions. And I think we'll look at ways later on of working with arbitrary functions. But the fundamental idea is that there's a basic set of operations that Catalyst can figure out what the cost of those operations is generally going to be, and it can then determine some kind of optimization on those operations. So this is the process that it uses. It takes a query that it's going to optimize, and it takes a data frame, and it has a unresolved logical plan. Now that unresolved logical plan is basically what you've told it to do. It then goes to the catalog of the data plan and then converts this in and resolves this with all the different references that were made in the query to the logical plan. It then does a logical optimization, which means there are certain optimizations that can be performed on the logic plan, like pushing filters down. And from that optimized logical plan, it produces a set of physical plans. I keep using the old term implementation plans, but these physical plans are then evaluated in terms of the cost of implementing each physical plan. So each physical plan has an associated cost, which is then goes through a cost model where we can choose the physical plan that has the lowest cost, and that physical plan is the one that's selected, and then from that, we do the generation of the code that produces the final result. Okay, so this is what Catalyst does. Now, Catalyst also has some hooks in it where we can plug in some of our own optimizations, which we will deal with next week. So one of the optimizations that it does is called a pushdown. So what a pushdown does is Catalyst looks for specific filters, and it goes and does the pushes down the filtering. By pushing down, we mean it moves the filtering closer to the data. So in a certain sense, let me see, can we see the diagram here? No, okay. So if we're doing a query and then a filter, that might be a lot more expensive than doing a filter and then a query. So the if we do, or even if we do a join and then a filter, it may be more simple. Excuse me. It can be a lot more efficient to do the filter than the join. So here's our example. We have a data set, small data set. We have a filter. The naive approach is read all the data and filter out the records. The smarter approach is to say, well, look, if we're going to do a read and then filter, why don't we just read the data that only matches the filter, because we're going to throw away the other data anyway. So we're filtering on age, so we apply the following condition: age is not null, and it's greater than 30. So that's only the data that we're actually going to load and work with. So here's the optimization. Is that we've got the original data, we read all the records, and then we filter. And that is a very natural way to write it in terms of thinking about how the problem is going to work. But Catalyst says, actually, the more simpler thing is to push down the filter. And by pushing down, ironically, it means it's kind of moving it closer to the data, which in this diagram is pushing it up a level. And so we're saying only read the data that actually meets that condition. So as we read in a data record, if it doesn't match that filter, we don't even bother loading it into memory. It just gets discarded and we just go on to the next one. So our data set winds up being a lot smaller when we load it into memory, when we read the data. So here is one of the options that we have with Catalyst is we can do an explain. So here's my filter. So I'm taking my filter and creating a new data frame from it, from filtering my previous data plane. And then I can ask it to explain what happened. And so the output here gives me a little bit of history of what Catalyst did. So it parsed a logical plan, filtered by the 30, and it analyzed a larger plan by looking at the various values and various data types. It then looked at a couple of other aspects of what was going on. So this is a JSON file, and there's a relationship here that it's looking at, and these numbers here are indicating some internal record keeping. Then it does a optimized logical plan, which is what we just looked at. So now it's saying, okay, well, we'll take this and transform it into this optimized logical plan. And then we have a physical plan, which goes and describes what we actually did on this. And then we have the pushed filters, the filters that we actually push down. And so then it has the read schema, which is how it's reading the data in. So we can actually go back and ask Catalyst, what did you do to read in the data? And it will go and explain the steps that it used in the optimization. So Catalyst generates the code for the execution plans with the Genino compiler, and this can boost performance tremendously. Okay, so now what we're going to do is jump into our data frames lab. So I think should be able to get into that. So we're going to basically create a data frame from a JSON file and do some basic querying just to get some hands-on with the data frames. All right, any questions before we do that? All right, well, I'll let you guys jump to it. Same procedure before when you did the labs before. So we're in 4, the instructions are in the 4.1 README file. And if anybody has any problems with the VMs, let me know. All right, and I'll check with you in about, I'll have my mic, I'll be listening in, but I'll have myself muted, and we can check in with you in about 15 minutes to see how things are going.
All right.
Because again, we're using the schema information that is available. There's the diagram we saw before. So the primary motivation here is that while we have gotten some improvements over the Hadoop MapReduce interface, it's the RDD interface is still, a pretty large API, and it has the disadvantage of the fact that we're still treating the data as big blocks of data, so we don't have a lot of things we can do with it that would be really convenient with structured data. Hold on here. There we go. So the two different points that Spark is making here is, number one, we want to be able to have people use Spark in a way that makes sense to them, rather than thinking just in terms of RDDs. In the world today, everybody thinks in terms of structured data. Not everybody, but structured data is a fairly common kind of way of thinking about data. The data we look at as structured is one of those things that tends to be a self-fulfilling prophecy, is that we use structured data because most of the tools we have are structured data tools, and because most of the data winds up being structured, then most of the tools that we have wind up being structured data tools. So the data that we're going to want to work with is generally going to be in some kind of structured form. So the other thing that we do is we have a long history of understanding how things like queries are optimized, so we can leverage all of that kind of general knowledge to be able to do optimization. So number one, we make a more intuitive and clearer user interface when it comes to working with data. But number two, we're also able to introduce optimizations that we wouldn't otherwise be able to work with. The comment here is objects and transformation functions are opaque to Spark. And that's the comment I've been making earlier, is that Spark knows that you're doing a transformation on the data, but the data itself is just a big black box. So Spark can make, in terms of RDD, some optimizations, but a lot of those optimizations just are not, are more general, and they're limited. So the other aspect of it is that we also have use case requirements for being able to do various kinds of queries into data. And the fact that, since, as I mentioned earlier, most of the data that we're working out there is in a relational type of structure, Spark is Spark is unable to support SQL and relational types of operations, and it becomes extremely limited and is sort of the odd man out. So the primary motivation behind it, like I said, is twofold. Number one, it is a standard model. It is well known. We know optimizations on it. And number two, it also introduces the ability to do more optimizations. So we can query data frames using SQL. And here's an example in Scala. We're reading an JSON file, same thing as we had before. Now what we do is, in step two, we're actually creating a view of the data that is essentially a table structure. And then we can start to query this as we would any other table. So the example in step three is the string in the double quotes is a standard SQL query, and then we can show the results of that. And again, the line down farther down here is also a standard query. Now the difference here, to go back from here, if we want to just keep this in mind, is that we have a more the operations that we were using here on filtering and these sorts of optimizations, while we were taking advantage of the relational structure, we still didn't actually have enough structure to be able to do SQL. So in this operation here, we're actually creating an intermediate form that allows us to do SQL type of operations. So what about this intermediate form? Well, the temporary view is like I said, it's just an intermediate form. It is a conceptual construct that is created for us to be able to interface with the data as if we had an underlying table. We can also create a persistent table, and we can also create a temporary view. So we may have in our Spark application several stages that allow us to use a table in a transitory manner, or we can generate a table that we're going to use consistently, which is our global temporary view, or we can actually restructure the data and save it out as a table using a save as table command. And there's use cases for each of those. So here in the example, we are taking a data frame. Now we've already got a data frame, and we're creating a temporary global view that from the data frame. And we are okay. So here the global temporary view is tied to a system preserved database, global temp. So in other words, we are actually able to use this interface, but it's still tied to that underlying data store. So now here is our view, and we've specified that this temporary view is people, and so we've got global.temp people, which is our intermediate view on the table. So we can also, now because we've created a global temp view, we're actually able to start a new Spark session, and we're able to access that table again. So it doesn't have to be saved more than once, or it doesn't have to be created multiple times. And then when we're done, this table may be useful for reuse, so we can go and save it as a Hive table. Question is, and this is going to be fairly obvious, do we use data frames in RDD wherever possible? They're faster, they're easier. Why are they easier? The model is well known, and that is generally, as I said before, those 2 points that we have with data frames. People generally conceptually tend to think in terms of tables, particularly because most of the data that we're using is in form of tables, because most of the tools are tabular. There's a very natural relationship there. They're easier in that sense. The fastness comes from the able to do the optimizations. But the other thing that we keep in mind is that because of the nature of how data is maintained out there in the real world, that most of the time tables or in some form are going to be the appropriate tool for various sorts of use cases. Obviously, it's a little bit different when we talk about different kinds of streaming data and other sorts of things as well. So now we come to our next lab, which is the working with SQL queries instead of the DSL. So again, notice that there's 2 distinct ways to run queries here. One is with the DSL, which is the stuff that you were just using, where you're actually not representing things as a table, but you're actually just working with the implied structure. In this one, we're actually going to be using the intermediate table in order to actually run the SQL query. So I'll let you guys get at that one. Are there any questions before we start? Hello?
Oh. Hello?
Yeah, I'm here.
I didn't hear it for some reason. So question. I was playing around because I was finished. Tried window functions and things like that. Everything on first glance works. Question. Is it really full SQL that is supported, or are there things that are not supported from the standard?
I think you're probably going to find that it's not going to be the as rich an SQL environment as you have in other kinds of products. I'm not exactly sure, but the core SQL is certainly important in this sense, in terms of being able to run queries. Were there specific SQL features that you were thinking about when you were asked that question?
No, just things to look out for. Like if you know of anything that doesn't work, that probably should, right? Like things like group by will work, but I was like, okay, window functions, do they work? Yes, they do. So are you aware of anything that is, let's say, outside?
Not off the top of my head, no. But I'm sure that there may be some real peripheral kinds of things that are not that common that may not be implemented. But most of the core sort of SQL type of structures and queries should be implementable in Spark.
Okay, thanks.
Okay.
Different question. Is it really widely used? Because I haven't seen it that much in any production environments or production code.
You mean the Spark SQL?
Yeah, Spark SQL, yeah.
You know what? I really don't know what the usages of it are in terms of actual numbers, because I don't kind of follow patterns in the market. But the thing to remember too is that it's only been out for a few years, and what I encounter with a lot of people that I talk to, not just with Spark, with other kinds of products like this, is that they often, if they're early adopters, they wind up getting a whole bunch of production stuff that's sort of in, like an early kind of model. And then they really, if it works for them at that point, they're often not quite that eager to make a transition into another sort of version. So I suspect that there are a lot of people out there who have adopted Spark, who got involved with it with the RDDs and found it was adequate for what they wanted to do, and they haven't had the use case to want to migrate to SQL. I think we're probably going to see more of the SQL with people who are now currently adopting Spark, who are able to take advantage of that. And this seems to be characteristic of a lot of technologies. So, for example, Hadoop came out and solved a very specific problem, and even though there's been enhancements to the entire sort of clustering system, a lot of people are still using the model that came out earlier simply because it meets their problem or meets their requirements. So that's the only insight I think I can offer. That for a lot of people, RDDs may be exactly just what they needed, and so they haven't progressed on this. But again, it's more of an issue where I think you have use cases where RDDs do not become, or for performance or other reasons, stop meeting the requirements that people look towards transitioning. I've discovered from my client base that people are very resistant to change. So who knows? Does that help answer your question?
Yes, definitely.
Yeah, yeah. It's. I think that, like I said, I think probably people who are adopting Spark now would be more likely to work in this environment than the old RDD environment, whereas legacy users may not be. All right, how are we doing for time? Has everybody got, anybody need a little bit more time? Sounds like a lot of people are finished. All right.
I think we're good in Berlin.
Yeah, good. Yeah. Okay, you guys are really fast. You're taking about half the time you're supposed to for this, so we're going to be a little bit ahead of schedule by the end of the day, which is Friday. So maybe that's a good thing. Okay, so now we're going to talk about data set. So data set is so actually, if you look at this table, just in reference to the previous question, RDDs are 2011. So that's about 8 years ago, and Spark, when it came out, was really sort of explosive in what it was doing. Excuse me for a second. It was explosive in what it was doing. So I think we probably would see a big wave of adoption at that particular point. And those are the groups that I'm thinking maybe sort of it solved a particular problem for them, as they saw no reason to change it. So data frames comes in 2013. Now we have two different models that are fundamentally incompatible. So you are kind of using two different APIs into Spark. And in 2016, they're unified under the dataset API. So the data set unifies that, and it has typing. So we have strongly typed and we have untyped, and the data frame is an alias for an untyped generic object. It's not really clear from the side here, but the big thing that happened with data sets is the introduction of typing. So the introduction of typing, whereas before with the RDDs you had pretty much just kind of blocks of data, And we saw before you could impose structure on it. But when you can start putting typing into that, then you start to get real good optimizations for things like serialization and other sorts of things, memory usage and execution performance. And that's why the dataset API doesn't work as well in Python. Now, Python can still use the RDDs, which use the older model, but it can't use the modern data set because it relies on this underlying typing. So this is an improvement that came into effect primarily for optimization reasons. So the dataset API is not in Python because it can't support the kinds of operations that depend on typing. I'm suspect that somebody will come up with some kind of extension to modify that. But a lot of the features are available. But it's just not a full implementation for Python. So we can have in our data sets two kinds, which are the strongly typed and the untyped. And the untyped are really more like the traditional RDD. And the data frame we also can use as for an untyped. So what happens is that the big innovation with data sets is the use of strongly typed data. So what we can do is read data from some kind of structured source, and then we can create a data set out of it. So let's look at the example there, and we can also convert an existing RDD to a data set. Again, using the idea that we're introducing typing into a data set. So we've got an example here of creating a data set from a list of things. And so now we've got a data set from the list. We can read it from a file. So there's an implicit conversion to a data set because a JSON file can be parsed in order to determine its structure because there's an inherent structure in a JSON file. And we can also go and convert RDDs convert from an RDD. Okay, again, but again, notice the comment here, assuming this RDD and the person class actually exist. So what we're actually doing is creating a typed structure when we do create data set from the RDD in order to create it. Now, if the class person, the typing doesn't exist, then this isn't going to work. So just to summarize to this point, we've enhanced RDDs into data sets primarily by introducing structure. The data frame now is a variation on the data set or a subtype of the data set, but the data set introduces this strong typing. So we can utilize this notion of the typing in both the new version of the RDDs and the data frames. You got to think of this as the data set is introducing an underlying representation of the data, which now can be accessed through a couple of different APIs, which is the dataset API and the data frame in the manner that we've looked at previously. So now it's become a lot more flexible. So if we take a look at this example here in Scala, we have the implicits, which does a lot of the implicit conversions. And so we can create a data frame and do a query. So we can read in the JSON file, so it creates a data frame and query. So that's a kind of data set. We can read CSV, which also has an implied structure. It tries to read the column headings or infer the columns from the header. So it figures out an internal structure from that. So CSV files. And it can also load a more traditional approach, which is the text file, and operate on it on a more traditional level here, where we're doing a filter on our data set. So we can so the data sets really cover the whole kind of wide range and usage. The thing that make data sets fairly powerful is this inferencing of schemas. So once we have a format like ORC, Parquet, JSON, you can start to infer a schema from that. So there, as it says here, there's convenience, but there may be, depending on the format that we're using, some sort of performance overheads. So the certain formats have a catalog that go along right with the data. So Spark doesn't have to do any analysis of the data. Spark can just go and look at the catalog or the schema and determine the structure right from there. So a couple of formats, Parquet and ORC, have that. However, the other kinds of formats, you have to do some inferencing of the structure. So the cost of actually doing that can be very high depending on the size of the data set. So what we can actually do is sample the data and go and infer the structure from the sample. So as illustrated in the example, we could go through all the records, or what we could do, and depending on the size of the data set, this could be quite expensive. Or what we can do is just pull up 30% of the records and sample the data in that sense, and then print the schema that comes out of that. So there are a couple of things that we can do to do that in order to. I'm sorry, there's a couple of things we do to cut down on the overheads. This is one of them, the sampling. The CSV files as data set is an innovation, which is where the header is used to inference from the column names, and it'll go over the data. So it's inferring all columns as strings, and we can, so that allows us to specify the schema when loading. So there's our CSV file on the right with the 3 headings and the appropriate rows of data. And now when we're doing a read, we're reading the CSV and assuming that the header is there. That's that option clause. So we're reading our CSV file and we're saying, look for the headers, and then we can go and print out the columns and print out the schemas. And we have another way of inferring the structure. So we can also specify this. So this specify the schema when loading as well. Okay, so here's an example of specifying the schema. So we can go take a look at this. So we are going to implicitly convert this RDD to a data frame. So there's our imports. So here, what we're doing is we want to get this structured field. And let me see, this is going to be name, gender, and age. So we're talking about name as a string. We have some other information in here as well. So we're basically have a particular kind of structure, and we're going to specify certain kinds of typing on this. So now we're going to specify a name field, and this is going to be we're going to give it both a name and a typing for that name. Gender is also going to have a string type, and age is going to have an integer type. So what we've done now with our data set is we've actually started to put strong typing on the underlying structure. So now we can create a schema which takes the name, which is it takes the name field, gender field, and age field, which we've defined here in terms of structure. And now that we've got our structure, we can go and read this data in a very efficient way. So here's our actual read operation. The option header is true, but we're also now giving it the schema as we read through the CSV, and now when we print out the schema, we see that we've got an appropriately typed object. Okay, so this is a definite improvement over what we were doing before, because now we've got a really solid structure. We've got typing in the structure, and because we've got typing, all of our serialization routines and a lot of the other routines we're looking at are going to become much, much more efficient, because we know exactly what kind of data we've got instead of just looking at really a blob of characters or a blob of bytes. So we're going to skip over the Python here. Here's another example of structure. In this case, we're defining structure in terms of a class definition, and we can read the data in now as simple text. So we've got our CSV file. We read it in as a simple text. But what we've got here, unlike before when we were just doing this with RDD, and we were just imposing a structure on it, that structure was opaque to Spark. Spark didn't know about that structure. But what we're actually doing now is we're able to actually communicate to Spark exactly what that structure is. So we're putting this into a data frame by using this class definition. We're reading the text file, and then we turn it into a RDD person by going and splitting up the lines and creating a new object. Now, this is what we did not see before. Before, we just actually split it up, and we had the data in a form that we could manipulate, but it was, like I said, opaque to Spark. Spark didn't know what we were doing. Now that we've got this person object, we are actually able to construct this structure. So we're still not completely done, because even though we've defined the schema, defined the object with its strong typing, and even though we've turned it into an RDD of persons, we still have to convert it internally to a data set that can be utilized by Spark, and that's what happens here. So we've kind of imposed some structure on the RDD, and now we're basically converting that into a data set so that we are able to access the full ability of Spark. Okay, so it's a subtle point, but again, just is worth repeating. Spark cannot do optimizations on type data unless it knows what the type is, and this is our ability to be able to communicate that to Spark. So this is where the data set is an enhancement of the RDD, because again, we're creating an RDD which has been typed, and then we put it into a data set. Okay, so here is so here we have the ability to move between these different formats. And again, we want to move between these formats because we may want to operate on the data from multiple points of view. So we have a people RDD, which is an RDD of persons. Now, again, the difference between this and the older RDDs is that we have, you'll notice it says people RDD, because we've got a RDD full of person objects. That's the big enhancement on the RDDs in the data set in the data set world. We can convert it to a data set, so we can work with it as a data set, and we can do a number of different ways of doing that conversion. And we can also go back and still access the underlying RDD. We can put it into a data frame so that we can use data frame kind of operations. And we can also take a data frame and convert that to a data set, which just means that we're now using that standard interface with the data set, and we can do this kind of version. So what we're looking at here is multiple views into the underlying data. We can look at it as a data set, a data frame, and an RDD. depending on how we want to work with the data. So these conversions are shifting basically our views of the data. Okay, so any questions before we jump into a lab here?
Yes. So in all of these conversions, like from RDD to dataset or data frame and back, is there any cost on those conversions, or is this just like very thin wrappers around each other?
Yeah, there is a cost, but the cost is really minimal because, as you said, it's kind of like different views of the underlying data. The thing that makes this really work is once you've got the data structured in some way and you've got an associated schema, it really is representing different ways of looking at the data. So yeah, you can implicitly convert one back to another. If you think about how Spark is actually working, the conversions are basically just referencing different, we can think of it as templates that you're looking at the data through. So you're looking at the data through multiple lenses. And so I think you're correct in saying it's like wrappers. I think of it more as being just different kind of views into the same underlying data. So you're not moving the data around. What you're doing is taking different views of the data. So there is a certain cost, which is computational, but the cost doesn't involve restructuring the data. But the key point here is this typing of the data that allows this conversion. Okay, now if we just had a raw RDD full of text, we would have to do all kinds of work on it to try to get it into a form. We could look at it as one of these other things. But once we've got this underlying kind of structure in place, and remember, the schema is nothing we do to the data. The schema is a description of what is in the data. So we're not really doing any converting of the data into a completely different format. It's kind of in the same way that a view into a relational database doesn't actually create new data or do a transformation of the data. It's basically just giving us a different perspective into the data. Does that answer your question?
Yes, and
Okay.
I have another one.
Yep. Go ahead.
So if we have a data set and we have this, was it people or person type? So we are giving Spark information that it can leverage to, let's say, optimize, for example, when encoding data to keep in memory. Do we have the same benefits or similar benefits or a subset of those benefits when we type an RDD with this person case class as well? I mean, by having this case class in there, can the RDD become more efficient in terms of caching, for example, than just a string RDD?
Yes. And that is one of the main motivations behind this notion of having the typing imposed on the RDDs, is that it allows for significant performance and improvement on caching and other things, because now there's structure and data typing, so appropriate optimization decisions can be made.
And in that sense, is there any benefits in moving from the person RDD into a person dataset in terms of optimization?
No, because the underlying data is still the same. It's the fact that we have now typed that underlying data in terms of persons. Whether we're looking at it a data frame or as an RDD is just our view into the data. But the data now has a way of being chunked into structures, and it's this chunking of the data so that makes things efficient. So for example, now instead of looking at this as just a long string of text, each row is a string of text with the name and age and whatever and gender. Instead of just looking at it as text, each one of those chunks is now been typed with a small schema on it. So the idea here is that once we've kind of schematized the underlying data in terms of these types, it's very easy for us to go and build a representation of that in a tabular form. And also we can go and just look at it as an RDD. But now the optimization really starts to take place when maybe it's something to go and cache that or to serialize that out, because now we have a lot of information about the underlying types, and that can be used to make optimization decisions. So this is really kind of an approach of imposing a certain kind of structure. And once that structure has been imposed, it allows these multiple views, but it also allows us to do a lot of optimization that we couldn't before. I think, did I answer your question, or did I kind of go off on a tangent there?
Yes, that's clear now, thanks.
Okay, good.
So then it is my understanding that the conversion from the RDD into the dataset, assuming that RDD is already typed, what it gives us is just access to higher level APIs, right?
Yeah.
So data doesn't change, optimization doesn't change, but it gives us access to, again, maybe this SQL interface or group by operation, or so this higher level API. So that would be the reason why at some point we might want to move from RDD to dataset. Is that right?
Yeah, and I think that one of the two things you have to look at in deciding to do that conversion are, number one, performance issues. As you start to think about caching and serialization, and we can start to get better performance in a data set. That's one argument. The second argument is, what are people using the data for? So if there's a lot of data analytics and a lot of people experimenting with queries, that you clearly want to get into it from a user perspective on the approach of what's going to be easier for my users to use. What are their requirements for the use cases? Does that make sense?
Yeah. So I think in Brilliant Group we finished with the task, and we'll have a discussion on how exactly performance or memory, or both performance and memory, are optimized if we predefine the schema using the data frames.
Mm-hmm.
If you work with them as an RDD.
Okay, I'm sorry. Can you repeat that? There's a lot of echo.
So we load in data using data frame API or data set API, right?
Mm-hmm.
And then we convert it to RDD and continue working as an RDD. Do we still have optimizations we got for data frames and data sets?
Do you still have the what you got for data frames and data sets?
Optimizations, like not loading everything. Okay. Good.
Yeah, in terms of the caching and optimizations, yes. In terms of the optimizations of queries and operations, generally no, because now the operations you're performing are in a form that that can't be optimized through things like Catalyst. But the other kinds of automations which are based on the underlying structure of the data, like the typing, yes, you do get that optimization. Is that
so? What exactly are these memory optimizations we still have?
Well, this comes from the typing, and the fact that once you've got that structure on the underlying data, that can be used for the optimizations. Now, whether you view that data as a table or an RDD, is a different interface into that data. Okay, does that make sense?
I guess it does, but I still didn't get the part about the memory optimizations. What exactly is optimized this way comparing to?
Okay, well, when you talk about things like serialization, for example. Okay. Serialization, if you know what the data structure is and the type of the data, you can make choices about serialization which you couldn't otherwise. And that's just sort of an example of that. This is something we're going into more detail next week about those particular optimizations and how those optimizations work. Okay. But generally if I know that I've got, say, integer data versus string data, I can think in terms of optimizations of how I'm going to work with things in memory. And
So
also,
basically storage
yeah,
utilizations.
and right, and the other thing too is if I've got structured data, then there's a certain access efficiencies. So if I have a long string, and I want to access something, I'm often doing some kind of linear search through the string. But if I have, say, chunks of data that are of a known size, it's easier for me to get to a particular point. So let's suppose I've got a bunch of person objects, and I know that the person objects have say a fixed size. I'm just using this as a hypothetical example, and I want to search for a particular element in the string, and this is not necessarily with Spark, but just an example. If I don't know that underlying structure, I have to start at the beginning and kind of search all the way through from beginning to end. But if I know that every n positions on, I'm starting a new object, I can optimize my search by looking at position 1 and then position 1 plus n and then position 1 plus 2n, and I can speed up a lot of optimizations. So knowing something about the structure of the underlying data, knowing something about where things are sort of positionally, enables me to do various kinds of optimizations. Okay, does that make sense?
Absolutely.
Okay. All right. So this is why that typing is so important. And this is why Python has such a problem with it, because Python is not really intended to do that kind of typing. So Python can do some of it, but Python has struggles with a lot of it. All right. So
can I ask one more question?
Yeah.
That's kind of related then. So I see we are sort of providing types in two different ways. So one way is, let's say, when we read a CSV and we provide this schema, right? Like this, struct fields and so on, right?
Mm-hmm.
Okay, so here we are providing types for the data frame or data set.
Right.
And then, like, separately, we are applying a case class in Scala, right? Don't we already have the types if we provide this say, set of struct fields already?
Yes, there are two different ways of doing exactly the same thing. In the first one, you're inferring it. You're doing an implicit typing. In other words, you're reading the data and inferring the typing from the data. And generally, that kind of operation can be expensive because there's an inferencing component involved. Okay, so in that view, we're saying we'll let Spark. In the data is an implied structure, and we'll let Spark figure out the structure and pull out a schema from that. In the other way, what you're doing is you are explicitly typing the data. You are defining a data class, and then you are explicitly putting the schema into place to do that data class. So one's explicit, one's implicit. You can use either approach. Some use cases, the implicit approach is going to be easier, particularly if using data that is really, really well structured and has associated schemas. The implicit approach is going to work really, really well. But if we're working with, like I said, JSON data or CSV data, it may just be expensive to do it that way. So we can switch over and do it explicitly. Or sometimes we may do it explicitly simply because we want to have that explicit declaration there, so that it's something that is well documented. Does that make sense?
Mm-hmm. And if we think, for example, from the Python perspective, I can, from Python, read a CSV file, and at the time of reading, I can provide this array of struct fields, providing very explicit types. And therefore, I can get a data frame that is typed, and therefore, I can get all of the optimizations that we are talking about.
Yeah.
The only thing that I'm not getting from this dataset API is the compile time safety, right? But in terms of optimizations, I can get exactly the same thing from Python just because I can provide this schema via these struct fields. Okay.
Yeah. The optimizations are not dependent on the language API that we're using. the problem with Python is that there are just certain things we can't express in Python. Or that I'm assuming this, I'm not sure of the exact details, but my inferencing is that there are just certain things that we just can't express in Python that we can express in Java and Scala in terms of typing, which makes just the API for Python somewhat problematic. So whether we're using Scala or Python doesn't change the underlying optimizations and things that's happening within Spark. It's just that the Python API just doesn't have the full functionality implemented. And I have a suspicion based on what I was reading is that that may change in the future as somebody puts some work into it. But it's more an issue of trying to figure out how to do the language bindings to the underlying API. Hi there, are we all back yet?
Hello.
Are there?
I'm here.
I'm here.
Okay.
Yeah, we're all here.
Okay, good. I was just worried that Berlin may have gone off and got sidetracked with something there.
Almost.
Almost, yeah. Well, it's it's the problem with taking breaks if you're actually in your office is that as you're going to go and get a cup of tea or a cup of coffee, somebody always comes up to you and says, "Could you just have a moment? I know you're in class, but could you just have a moment?" And then you spend your time just trying to get rid of that person so that you can get on with your life. So it's always an issue.
It feels like we are the only ones in the office.
Okay. All right. Okay. So now, are you guys familiar with Hive?
No.
No.
Really?
Okay. Okay. Well, I'm not a big Hive person either because I really haven't had much opportunity to use it. So basically, just to give you an idea of what Hive is, it's basically a data warehouse that is kind of built on top of a Hadoop cluster, and it allows you with all of these kinds of things with. And we'll go back to that question before about SQL. When we're looking at these kinds of analytics with data, there is a subset of SQL that really isn't applicable. Things. So SQL itself is primarily useful for transactional data. With normalized forms, and you want to make sure that you don't corrupt your data when you insert records and delete records. And there's this constant notion of data in motion and data shuffle. I don't know if I say shuffling, data constantly being modified. And so we have things like normal forms that present against that. In fact, I was just talking to somebody, a class a couple of weeks ago, and they said, well, why should we have normal forms? And I had to quote Mitch Hedberg, who said, computers allow you to make mistakes faster than possibly anything else in the world, with the exception of handguns and tequila. And if we don't have things like normal forms to control that, then we don't. So a lot of the SQL model is built around not queries, but is built around the data update and the building these structured data forms. The data that we're working with in Spark is generally not transactional data. So a lot of the SQL stuff that deals with updates and deletes and normal forms, it doesn't apply here. But we're primarily focused on queries. So when I was making that comment earlier, I was trying to think, is there anything about the querying that really is different in Spark SQL? And I guess I should add there is that Spark is not really going to be if you're running update queries using Spark, you're using the wrong tool. It's just not what Spark is for. So I'm thinking in the context of just being able to query data is primarily what we're looking at, and being able to transform data, but we're not necessarily interested in transactional types of operations. So anything that SQL does that's highly transactional is generally not supported in these kinds of SQL-like environments. And if they are supported, they're not very effective. So Hive represents a data warehouse type operation, or a data warehouse type structure that's on top of Hadoop, and it has its own version of SQL, which again, because we're working with a sort of analytical kind of data rather than transactional data, doesn't really do a lot of the updates. And because it's also a data warehouse with sort of all the implications of we're not going to be modifying data once it's been stored. All we're going to be doing sometimes is restructuring it and looking at it in different ways. We can throw out a lot of the SQL stuff that's associated with data modification. So the Hive QL is a subset of SQL, which is primarily query based, and it also has a couple of other parameters and commands that relate to the fact that it runs on a Hadoop cluster. So there's a little bit more that you can do with it, but it is primarily a data warehouse model. One of the things that Hive does is it also creates tables. And like I said, I'm not a big Hive person, but I do know that I'm not sure if the tables are actually structurally created. I don't believe so. What I believe is that table descriptions and schemas are kept in a separate database. And that database basically contains a schema and structure descriptions, which are then used to format the queries, which are then executed through a variety of MapReduce kinds of operations. So Spark can manage the data directly in Hadoop, or it can utilize Hive tables, which is a structure imposed on the underlying data. So it depends sort of on the use case as to how you've got stuff. If you're using Hive, then this is an appropriate way to do it. And if you're not using Hive, there may be an advantage to actually thinking in terms of using it, or there may not be. So hopefully by the time we get through the end of this stuff, you'll have a sort of an idea of whether or not it's something that's useful for you. So Hive tables can be thought of conceptually as tables like everything else. So we can go into the Hive shell, and this is going to look very much like any kind of standard SQL type of shell. So we have show tables, and it shows a table of clickstream. It gets the SQL context, and this Hive context is available in that Spark object. You can, I think it's also in the SC. I don't know if it's in the SC object, but it's certainly in the Spark object you get in the Spark 2. There is a Hive context inside that, so you can actually access a Hive context in that Spark object. So now, if they're working here in a Hive shell, so there's show tables. Now in the Spark shell, you've got an SQL context which can do a similar kind of operation, and this SQL context is the interface into the Hive API. So we've here created T, which is a reference to the underlying table of clickstream, and we can now print the schema from that table, and we can show the data that's there. And now we can use these queries. Now that we're attaching ourselves into that Hive context, we can execute basically the Hive QL query. Now, for things like select statements, most of these data warehouse like Hive and everything else generally support select statements in a pretty much standard way. So the queries are fairly standardized across it. It's in the other stuff where we start to get some variations and differences. So now we've got a context. We execute an SQL command, select all columns from clickstream limit 10, and then we can show the result, and we can do a count. And again, fairly standard SQL kinds of queries. Again, the Hive QL is intended to look like SQL for most of your basic query type commands. And you also have the catalog, which is the interface to work with the metastore. Now, the metastore is the actual descriptions that Hive maintains of the conceptual table structures that are there. Okay, so we take a look here. Is that we have a catalog, which is the catalog interface for Spark, a column, which is a column in Spark, a database, a function, a table. So we do have those particular options. Okay, so here's an example of using the catalog. So we've got the Spark catalog, and now we can go in the Spark catalog, do tab, and we get the kinds of commands that we can use. Drop temp view is cached, list tables, get table. So we do have a number of fairly standard commands that we can use. So we can take one here of list databases. Now we've got the name of the database, the description, and the location of where that is. Again, these are generally going to be some sort of warehouse model that we're using. Then we can list the tables that are there as well, and we get people and logs and the type of table we've got. And again, that's more of a Hive kind type of thing, and whether or not the table is temporary. Okay, so so we can again use our Spark shell to do the same thing that that we've got here. We just did that, I think. There we go. So Hive data warehouse for Hadoop. We can directly query the Hive tables using SQL. So we don't have to switch over to Hive. We don't have to redefine the tables because we were able to access all of the metadata and catalog data that Hive maintains using the tables, or using the tables that Hive sets up in terms of the metadata. Hive does have, see, if we think back on what we were looking at before, when we were looking at Parquet and some of these other formats, because they have attached schemas, Spark is able to work with them much more effectively. In this particular situation, since Hive maintains a database of metadata, Spark can utilize that metadata to get the same kinds of efficiencies in terms of getting information about the structure of the data and the nature of the data that it got when we were using some of these other structured formats. Okay, so so basically Spark gives us a context, which is a Hive context, which is an interface that we can use directly into Hadoop, into the underlying data warehouse. There is no need to redefine tables. In other words, there's no data transformation involved, and Spark gives faster query times than Hive. And again, that's because Hive is using the underlying Hadoop system, which is mapping these out as MapReduces. And we know that from the way Hadoop works in native format, there's a lot of disk access and that sort of thing. So the we get a much faster performance in using the MapReduce engine, and we do get other kinds of performance that are able to on other kinds of implementations. So generally, Spark, because of its processing model, is going to be a more effective way or a more efficient way of processing stuff that's stored in Hive. One of the use cases for this is that a lot of people went to Hive as a way of as imposing a data warehouse structure on top of their kind of big data solution. So they've all this stuff in Hadoop, and you want to know, well, how can I access it directly? Well, let's conceptualize it as a data warehouse. So Hive comes along and gives us that structure, that interface, maintains all the data we need to work with the underlying data as a data warehouse. And now what Spark does is Spark gives us a way of optimizing. So in this diagram, while it looks like Spark is actually going through Hive, I think it's a more accurate representation to say that Spark is sort of short-circuiting some of the stuff that Hive does, but it's using all of the information in Hive to be able to structure its queries. So I think it may be a more accurate representation to say that Spark is actually bypassing generally the slower parts of Hive and kind of giving us those performance in reduction. That particularly shows up when we're bypassing the native Hive implementation. However, we can also save data in Hive tables. So we also have the ability to do persistent data. So there is a couple of operations here that are not generally native to the Spark world. We're not, thinking in terms of saving tables in Spark, but we can basically reference saving tables through Hive. So here's our model again. There's our HDFS. Here's Spark. And the Hive represents a view into the HDFS system, the underlying data that Spark can use in order to execute various kinds of data warehouse type queries. Okay, so now this will be a really quick and simple lab, which will let you look at using Spark SQL from a slightly different perspective. And then we're going to be closing up a lot of stuff with the data format stuff. And that'll give us a bit of time to to start talking about some of the other topics. This will represent the end of kind of the basic stuff that we want to talk about Spark, and then we'll get into some of the more interesting stuff that you guys are particularly interested in. Okay, so I'm going to let you guys do this lab. And one of the values of doing these labs is just to become more and more hands-on familiar with the environment. So are there any questions before we start the lab?
So step 1 says open 2 terminal sessions to Hadoop node, and instructor will demonstrate how. And I think we need this demonstration because
I don't have that demonstration here. So
maybe explanation would be fine.
Pardon?
Or maybe an explanation would be also fine.
Yeah, there's okay. Again, I'm still sorting through all this documentation. Let me check on this. There's to tell you the truth, I don't have that explanation on how to do it on there. So maybe what we'll do is we'll defer this lab until I find that documentation. I didn't get a lot of this lab stuff until just a couple days before the class, so I didn't get a chance to do that. Okay. Yeah, so how about if we just move on? We'll move on for now, and then we'll come back to this lab later if you want to do it. Will that work?
Yes.
Yes.
That'll give me a chance. That'll give me a chance to hunt stuff up. Okay. All right. I apologize for that. I'm trying to assemble all of the stuff as we go along, so sometimes it can be a little bit tricky. Okay, so let's work on with data formats for a bit. Okay, so the notion of data format is that we think in terms of how data is actually being stored in terms of tabular data, and how records are actually stored together. So, or how records are actually stored. So in most systems, we use row-based storage, where records are stored together. And so we have, this is the model that most relational databases actually used. And this is generally, because the granular level that we're working at is the individual entities that are represented by the individual rows. The advantage also is that our select queries work kind of nice because we can kind of select all of the columns and just kind of go down the row and select columns that, or go down the table and select the rows that are appropriate. So from an advantage point of view, it makes working with the data very, very nice. The disadvantage is that if we're actually searching for things based on some kind of row, some kind of column value, our search time tends to become at least linear. And so we have to index the various columns if we're going to search on the columns. So the indexes are a way of actually compensating for that. Now, in the column format, we're storing it column by column, and this is the reason why we don't do relational data this way is because when we're adding records, it's very difficult to insert records, whereas with row-based, you just add another row to the table. However, the column format does have some significant advantages because we're often doing some kind of column-based work, like the example there, select the max temp from sensors. We basically can do a very fast access into a chunk of the data, which is all based on a column. It doesn't work well for select queries because if you visualize it, you're going to have to basically kind of jump from chunk to chunk, looking for that particular record. So if we have say 10 records, and we want to select record 5, we have to jump from each column chunk to each column chunk, looking for what part of that column belongs to record 5, and so we get a much more difficult process of assembling a query. So, like everything else in life, there's advantages and disadvantages to column-based rows. So here's our row-based store. And the disadvantage here is that when you want to do aggregations, there's that a seek. So I want to sum up column 1. I have to kind of jump from place to place and pull out the values for column 1 and assemble those into some intermediate form, and then do the operation on those forms. On a column store, when we've got something like this in the various files, it's very easy for me to go and do operations on the column. Very often for data warehouses, this is often a very effective thing because you're not interested necessarily in individual records. You're interested in various forms of aggregate data. So you're interested in total sales by region or something like that. And so a lot of the operations that you're actually going to be performed are doing operations on columns of data across the data set. So in doing a column store, you are getting very, very fast access times for column-based data. So that's one aspect of storing data. Now the other aspect of data storage is the actual format of the data. Text, binary sequence, Avro, Parquet, ORC. So there's a number of different formats that also interact with this, and each one of them again is going to have their own particular advantages and disadvantages. The standard, what we might call pseudo-tabular data, which is CSV, JSON, which we also might consider to be sort of Excel-ish kinds of stuff, involves more or less explicit relationships between a key and a value. The advantages that this has is that they're human readable, which is one of the big reasons why JSON's also preferred over XML, is that it's much more human readable, which is an advantage with various kinds of things like configuration data and other things where you want things to be human readable. It's compatible with tools. There's a lot of tools out there. It's a schema independent store, so you can move stuff from databases to data warehouses to other kinds of environments. So it's a JSON and CSV might also be considered kinds of transitory or transport tools that you would use to move data around. Because that's one of its strengths, it also is one of its weaknesses. It's because it's human readable and because it's sort of in a neutral format, it's certainly not, it's not size efficient. It's got a lot of redundancies in there. The other thing that it has is that it's really difficult to query this data. There's no optimizations that we can really perform on it. So in order to work with this data, we generally have to convert it into another form. And it does not generally support some kind of block compression. So it's also something that doesn't lend itself well to various kinds of compression algorithms and things like that. Binary sequence, binary key value pairs, row-based. It's got the advantage of that it's supported within the Hadoop ecosystem, which we're building our Spark and other things on sometimes. It supports compression, which is really good because that gives us various kinds of optimizations, but it's not human readable. And again, I'm not really convinced that that's much of a con, because if I'm looking with a lot of this data, I'm not really going to be reading the data. I think I'm going to be more looking at the results, and particularly if I'm doing any kind of analytics, I'm going to look at some kind of representation of the data. The problem is that outside the Hadoop ecosystem, this is the big con, is that if I want to start using data that's not really Hadoop based, then I might start running into problems with this format. Avro is a serializing format. It's a row-based, and it's got the advantage that the schema is stored as part of the data. And as we've seen before, having access to the schema makes a lot of easy decoding taking place, so we don't need separate data dictionaries. And again, if it's a serializing format, okay, so if you have a schema when you're serializing, your serializing becomes really efficient. And if you want to think about how this works, the place you really get the efficiency is in the deserializing. So if I know that when I serialize a number of data structures, each one of them is going to be marked in some manner. When I deserialize, I can generally chunk up the byte stream much more efficiently when I'm pulling it back in. So the idea here is that when I have a schema that's available, I can do a lot of more appropriate, a lot more optimizations, particularly when I'm deserializing. Serializing is generally not going to benefit too much necessarily from some of these in this context from this kind of operation, because I still have to do all the serialization. But a lot of the deserializing problems are sometimes involved in trying to figure out, like reading it enough to know when to stop. So when a bunch of serialized data actually represents something. So you can have some optimizations in there. It does support schema evolution and versioning, so it does enable multiple versions of a schema to coexist. Now, Parquet is something that's coming out of Twitter and Cloudera. It, on the other hand, is column-based, whereas these other things are row-based. It's binary, and the schema is stored with the data, and it's very efficient for column-based queries. So we have a couple of different data formats, which are usually using different data storage mechanisms. So Parquet schema, again, stored with data, but now we're looking for very efficient column-based queries. Okay, so now we have another data format is ORC optimized row columnar, and this is evolution of something called RC file, and it's a hybrid format where it stores rows, and within the rows, data stored in columnar format. So it basically has a nested sort of structure where we have a column format within the rows. So what we're really doing here is, in the optimized row columnar format, you think of it this way, is that the rows themselves in a normal row-based format tend to be hard to find, or the columns tend to be hard to find because we're really thinking in terms of rows. But if we can overlay on top of that a structure so that we can easily move down a column with rows through some kinds of hints as to getting into that, so we can go from row to row with navigating through a particular column, from row to row through a column, then we get things a lot easier. So this gives us a much better performance on column-based operations. So how do we decide what we're going to do, what data format we're going to choose? We come down to to a number of considerations. Oh, hold on here. Sorry. That was my timer to have you stop your lab. So the workload, ETL ingestion systems, obviously, if you're using Hadoop, that's going to be one thing. If you're using a different kind of system, you want data formats that are going to be compatible across those areas. Is human readability a big deal? If it is, and you can develop use cases for human readability, so there's times when you may want to look into the data and have human readability. And again, my personal feeling is that when we're operating in kind of a Spark environment, by that time we should really have a good sense of kind of what our underlying data structure is like and how it's working. So human readability, generally, I think it's probably not as big an issue. But if it is, then we want to use some kind of human readable format. Speed, Parquet ORC, because of the way in which the data is organized. If you want to be able to use data frames that are supported natively, then the things that have that structure associated with them is JSON, Parquet, Avro, and apparently right now, and I'm not too much up on what the current trends are exactly and what everybody's using. Looks like Parquet and ORC is a preferred format. And again, I think the ORC looks like it's got some really, really good advantages, and Parquet, again, because it's column-based storage. And part of the reason for that is that we're also, if you stop and think in terms of a query, a lot of terms of our query are being done in terms of searching through a column for particular values in a particular column. So you can see where optimizations would come up from that format, from using that particular format. Okay, so Parquet and ORC preferred format. I don't know who says their preferred format. I'll just trust what the guy who wrote this said. But what happens is that we do have the option of being able to convert between formats. So we can actually, as the example shows, we can do migration from one data format to another. And so we've got a JSON data frame. We're reading JSON. We're getting a data frame. But now we can write it as Parquet. My understanding that what this writing does is it's actually creating all of the metadata in a Parquet format. And also the same thing with ORC is that it's also doing a lot of the metadata work. I have to go and check and find out exactly the amount of overhead that's involved in doing this, because I don't have those values right offhand. But the idea here is that from an operational point of view, I can generally go and create various formats. Now, I'm going to suggest that the choice of migrating from one format to another may be dictated on how we are going to be working with that data. So we may have data, it's one format, we read it in, but now we realize that the operational stuff that we're going to be doing isn't really a great data format. We can switch it to a different data format and we can get some easy migration. Okay, so now we can hopefully be able to do some good labs, and I'm going to go while you're doing that and try to find out where that thing I'm supposed to show you is located, because I don't know how it's actually set up on that system, but I will do that. Okay, so we've got another 50. First of all, questions about data formats and things like that. All right. One thing to remember is a lot of these data formats rely heavily on how the metadata is structured. There is a lot of the conversion that can take place is actually conversion of metadata and doing mappings of metadata. Not all of it, but a lot of it. So there are efficiencies in that format, in that aspect of it. Okay, so I'm going to let you guys do 4.6. I'll give you 15 minutes. There's no questions, so it looks like we're fairly good. All right, how are we doing now? Are we need a bit more time, or are we good?
Some of us are good. What about Gerald? Are you okay?
Good. I still didn't finish.
Okay. Yeah, some of us are not.
Okay, another 5 minutes. We're in no rush here. We're really far ahead of where we should be. So, you know, I don't want any of you to feel a little bit rushed. So those of you who need more time, you can take it. And those of you who don't need more time, you can stare at the people who need more time and make them feel uncomfortable or something, you know.
But I have a question. So,
But if you have any questions?
yeah, I have a question. So it says, so the lab description says that we need to record the load time into the spreadsheets. However, this is a little bit complicated for ORC because it doesn't explicitly show the load time.
Okay.
Or at least I'm just unable to see where it is.
Okay. I'll take a look at it too, and I'm taking a note of some of these things, and I'll check onto them over the weekend and see if there's something I can come up with. Okay.
Yep.
All right. Anything else? So do you want to take another little bit of time, or do you want to kind of move on a bit? It's up to you guys.
Well, I still didn't finish, so.
Okay.
Sure. How comfortable?
Let's say another 5 minutes for those who.
Sounds good. 5 minutes. Yes.
Yeah.
Okay, good. We'll do 5 minutes, and then we'll get back to it. Okay.
I have one more question though.
Okay, go ahead.
Fill those 5 minutes with. So at the end it says you should sort of you should be looking at where is your resource ceiling, whether or not it's the memory, CPU, or disk. I was sort of trying to monitor the ATOP output, but apparently the sampling rate wasn't very good.
Mm-hmm.
So I didn't really get any answers for that. I mean, I have some hunches, but
well, what's your hunch?
You get some actual results for which ones were bound by which.
Okay. So what you said you had some hunches. What were they?
So like my, as far as I understand it, if you read JSON, that's a big file format. It's even apparent when you list the files and look at how big they are. So it's going to be both disk bound and CPU bound because it has to parse both. So like there, it just depends on how fast your disk is. If it's an SSD, it may be CPU bound because it takes so much time to actually parse it. If it's a slow spinning disk, then your CPU is probably fast enough, so your disk is going to be your ceiling.
Yeah, I think that's fairly true. But again, remember, part of the thing that is always going to be true is that the parsing JSON files is going to be much more CPU intensive than parsing some other format because of the fact that it's basically
no doubt. Mm-hmm.
Yeah, so that always is going to be true. But your comment about the disk is quite true, and I think maybe one of the questions you might look at is that in even if you have a slow disk and you move up to a fast disk, you still are stuck with the parsing problem of the file of the data format itself. And you know, even if you keep everything in memory, you still wind up with that CPU intensive operation.
Yep. That's exactly what I thought, right? So you are stuck with that task. It's just depending on your disk speed, your bottleneck basically shifts from one to the other.
Right. And even if you're using an in-memory disk, you're still stuck with that CPU problem.
Definitely. Definitely.
So, okay. All right, good. So we'll do the 5 minutes and then we'll do it. And just for you to, so you guys know, we're 2/3 of the way through a 3-day course in terms of content. So we've got a little bit of flexibility today in terms of what we're going to be doing. So we'll check in 5 minutes and see how we're doing. Okay.
Okay, good. All right. I was just explaining a moment ago that I may have made a mistake. Well, I didn't explain that part. I was last Thursday and Friday, I was very sick. So I was kind of stumbling through my classes, focusing as best I could. And I went and shut down the virtual machines on Friday. I saw them all changing state. But for some reason, when I came back this morning, they were all still running. It really surprised me. So I thought, oh gosh, this is great. So they probably have been compromised. So I've spun up another set of virtual machines, but they're in that kind of initial state. So I'm going to give you kind of the option here. If you want to just, if you're just working at the command line and you want to play with the previous one, or if you want to pull some stuff off the previous one, I've left them up with the same IPs, but I've also put up some brand new ones this morning for you, and I put up a new spreadsheet which I'll dump into this Slack channel right now. So I do apologize for that. Like I said, I was definitely not completely, shall we say, sane, I guess, when I was doing this. So I'll let you guys make your choice as to what you want to do.
So for me, the VNC, it says too many authentication failures. So I cannot connect VNC.
So I am going to put into the
so far we were okay without VNC, right?
Yeah, but I don't know. I haven't tried the SSIs.
Okay, so I put the new spreadsheet in there. So I'm gonna give you guys the option as for those of you who just want to use the new machines, I will shut down your old ones. But if you want to work on them a little bit, so I do apologize. It was entirely my fault. It was nothing else other than me not ensuring, coming back later and ensuring that they'd been shut down properly. All right.
Gerald speaking. I would also use a new machine, but the password is not there. I mean, the IP is listed twice for me.
Oh, okay. Okay, let me. Which machine was that?
Gerald, the very last entry.
The one ending in 232.
Oh, I didn't put the. I see. Gosh, here I thought I was actually doing better. Okay, let me fix that for you right now. That is Gerald, and so we'll into Gerald here, and we'll grab the instance ID on that. And Gerald, I'll just pop that instance ID into the Slack channel.
Perfect.
So you can grab it from there. My apologies on that. There we go. So there you go. If anybody else has any other issues, let me know. Okay, so.
Gregory speaking here. I'll keep my old VM. Everything works there. I connect. So.
Okay, so your old VM is fine. All right.
Yeah. The 235. Okay. No, wait. Which one? No, wait. Then just me check the IP that I used. Yeah, the IP ends with 235. Yeah, so this one I keep. And
you're going to keep the old one. Okay.
Yeah, exactly.
Okay, so I'll just shut down. I'll just turn off your old one for now, or your new one.
Yeah, the new one. Yeah.
All right.
Roman speaking, it doesn't let me in actually. So I enter the password and it asks me for a password.
Who is that?
Roman.
Roman. This is for the new one?
Yes.
Okay. Let me see. We made a mistake here. We may have. Let me double check this. Roman, you should have 18. So for Roman, hold on here, do it this way. Okay. So for Roman, we should have 188850, and we should have, okay. Looks like the information I sent you is correct.
Let me try another time, but...
Okay.
And the username is still Ubuntu, right?
That's right.
Oh, now it was successful.
Oh, it was. Okay. It just heard us talking.
Yeah. I don't know what happened, but now it's okay.
Yeah, no, that happens a lot with technology, doesn't it?
Yeah.
It's supposed to be our servant, not our master. Okay. All right. Okay, so now, well, we're gonna start with kind of a little sort of review of where we picked up. We've had a lovely weekend, and we all just going to kind of do a little bit of an overview before we jump on to our next section. And we also have some opportunities to play around a bit more with labs. Now, I am obligated by the nature of sort of my obligation to the people paying me. I have to give at least a cursory coverage of the components of the course, but you'll notice that we haven't been spending a lot of time on things like Python. So there are some sections about applications. We're going to go through those really quickly because what I am intending to do is to introduce material, particularly around the interest of you guys on Catalyst and Tungsten. So that is stuff I'm going to be sort of adding, pulling off of some different sources, and we'll talk a little bit about some of the other things like bucketing and some of the procedures that are kind of circulating out there in the world around some of the things we do to avoid certain kinds of shuffling, and how to manage things like large joins and some of the pain points that we often get in there. But we'll kind of add those over the next couple of sessions, and make sure that we cover off a lot of those topics. So hopefully by the end of this session on Wednesday when we leave, you'll have a pretty solid understanding of what's going on with Tungsten and Catalyst and what all of the things are that are happening under the hood, so you can sort of build an experiment from there. All right, so the first thing that I was just going to well, I'll just going up to the one up here to the start here, we had talked about RDDs with the, and I'm not going to go back and pull up the slides on that, but we talked about RDDs as this kind of structured format. Now, RDDs, I've been kind of curious as to the amount of support that they actually have, and generally there are some special use cases for the classical RDDs, but normally they're pretty much deprecated in the certain sense that the kind of data set that has been evolved pretty much does everything that the RDD can do. It offers the same interface, but it operates much more efficiently. So but the underlying concepts there are fundamental in terms of how we interact with them. So the things that we discussed earlier were the important part about how Spark was functioning that we talked about was the directed acyclic graph, and this idea that the transformations are not executed until an action occurs, action being defined as anything that returns something other than an RDD, so that there's an optimization process that can take place. So that is fundamentally where we introduced the basic architectural idea that Spark had up until about, I think it was Spark 1.4, 1.6. Then we implement this data frame concept, which is the idea of RDD plus schema. One of the drawbacks to the RDD was that you couldn't do certain kinds of optimization because the RDD itself was opaque to the optimizer. So you were limited in what we could expect Spark to do for us. The other problem that Spark was running into in the earliest was this notion of being in memory. And again, we have to keep in mind that there's two different things we're talking about memory. One is the memory that we're talking about in our master node where we're running the Spark from, versus the memory in the various worker nodes. And we are given the fact that it's all running in JVMs, we had problems with actually being IO bound. And one of the papers I was looking at a while ago was pointed out that even with memory only, storage, one of the bottlenecks that Spark was running into was the latency between moving data from memory into the CPU. And so one of the things that Tungsten does is utilizes caching memory, the L1, L2, and L3 caches. It actually optimizes the storage in order to cut down on the transfer time between memory and the CPU, which I thought was a really interesting little innovation. So as we come into data frames, we're now putting structure on there, which allows us to be able to start doing optimizations. This is where Catalyst comes in. And then with the introduction of typing, which allows us now to do much better allocation of memory and much better serialization. And again, with this data sets, we're now really looking at two interfaces into an underlying structure, which is being used from either the point of view of a data frame or the point of view of an RDD. Now, the excuse me, the overall approach to Spark is to look for places of optimization, keep as much things in memory, avoid relying on a lot of disk I/O, but also being able to delegate a lot of the actual distribution of the partitions of the data out to the various nodes. So there's a number of places there we want to look at where we can optimize performance. So the idea has been to keep the API fairly consistent, or at least consistent and easy to use from a user's perspective, but at the same time allowing us to have opportunities to optimize under the underlying architecture. So this was the idea of data frames, then data sets coming along to provide the unified interface. I was watching one video at one of the Spark conferences, and somebody was saying that if you ever decide to go back away from data sets, you should be consider retiring and just taking up farming or something. So this apparently has got a lot of this is really sort of the direction in which future optimizations apparently are going to be built. So we discussed the data frames and the ability to be able to start to use SQL type queries and manipulate data based on columns. Everything that I've been seeing suggests that this Parquet data format is increasingly becoming the recommended one for Spark. Now, when I actually started this course, I had not actually used Parquet, and I didn't really know an awful lot about it. So I went and I started looking, reading up some of the technical docs on Parquet, and I was very impressed. This is a data format that has got an awful lot of very impressive design to it, and the way it stores the columns in the data and how the data is serialized and deserialized. So one of the optimizations does certainly seem to suggest itself, and one that I was not fully aware of, is that the choice of and I've been also coming across items where the real gurus in Spark are suggesting that if you want to look for certain kinds of optimizations, that Parquet may be a data format, particularly with regards to serialization. Has much better serialization than some of the other data formats. While all of them work well, Parquet does seem to be one that has certain advantages that can be utilized by Spark. So just keep that in mind as a little tweak. Hold on here, I've got one of my devices is beeping at me. I'm going to have to turn it off. There we go. Better. So. Oops, we're going to get more into the details of tungsten either today or tomorrow, but we'll certainly get into it by tomorrow. And then again, when we look at the performance, again, we've seen that before, so we don't have to worry too much about that. We took a look at basically the data frames, data typing. And then we started talking about some of the optimizations and how we can do optimizations, particularly through Catalyst, that does things. In the example we looked at is predicate pushdown, where instead of reading all the data in, we filtered the data so that we cut down on the amount of data we actually keep stored in memory. And then we actually have when we have running through Catalyst. And we'll just remember, this is a point we're going to come back to, so it's just worth remembering, is that we wind up with an unresolved logical plan, and that unresolved logical plan is just basically your statement. The resolved logical plan is when you go and you add in all the information from the catalog about the structure. That's optimized, and we'll take a look at some of the optimization rules that are used a bit later on. And that produces the physical plans. Each one of them is then run through a costing model to determine how expensive each plan is in terms of execution. And then from there, we wind up with a selected physical plan. And then from that plan, we actually generate the code, which is often done through this Janino compiler. And that produces the appropriate RDDs that result from the query. So the idea here is that we have this other point of optimization. I think we did that one quite nicely. We talked about Spark SQL. Should I use a data frame instead of an RDD? This is not a theoretical thing. This is just a practical issue. And it says yes. Wherever possible. And again, remember that at this point, the data frame is an interface into our underlying data set approach. Here we go. And we talked about creating data sets from various kinds of things. We're not going to get into all of that kind of stuff again. We talked about using the various other data. Talked about using the other or interacting with Hive and its data warehousing SQL type of language. For data formats, we looked at those again, and I'm not going to to go over all of this again, but just remind us where we are when we left off. Now, again, Parquet. This is the one that seems to keep coming up over and over again from at least the kind of technical things that I've looked at that suggest that this is really, if you have a choice, to at least experiment with Parquet and see if you can achieve some optimizations on that. Okay, so it says Parquet and ORC. Now, unfortunately, I don't know an awful lot about ORC, but Parquet, like it seems to come out as being the preferred format. I just didn't realize how much until a little bit of until we got into that. Now, I think we did this lab at yesterday or on Friday, didn't we? I think this is the one where we ended at. I think we kind of concluded our day on Friday with this one. If I'm wrong, please, let me know.
Yes, we did this one, but
so.
you wanted to look into the previous one, the SparkHive class, because that didn't work on our machines.
Yeah, and unfortunately I didn't because I was spending the weekend being sick, but I will certainly take a look into that as well. Okay, thank you. That's something I have to do. So I will take a look at that today. All right. Okay, so now if you wanted to, now these build on the previous lab, so maybe it might be not, since some of you work on new machines, this may not be a good place to go to. So I'm going to suggest that if you want to experiment with this and give this a try, you can, but you may have to go back and do some previous work, which is, again, really sort of my fault again, mea culpa. So we'll have to maybe just leave that for now. All right, so any questions or things that you want to mention about about what we've done so far? Questions, issues unresolved, things that may be still confusing, or things that you need a little bit more information about?
So we do have a question in terms of if Spark is running for quite a while. The previous slide you mentioned something about commit logs. It kind of accumulates quite a lot of logs. Is there a way to automatically get rid of these logs? Because if we have long-running Spark applications, it feels like we always have to manually restart Spark to just get rid of these logs if the underlying resource manager still assumes that it's a running container, so it keeps the logs.
Oh, okay, that's interesting. I'm just gonna make a note of that, and then I'm gonna have to check into that because I don't have an answer off the top of my head. But let me just, okay, so the question, and I'll get back to that one tomorrow. So long-running Spark commit locks.
Not necessarily commit logs, but in general, there are quite some logs that Spark is accumulating as an application running on top of a resource manager like Yarn.
Okay.
And even if the application is not doing too much at the moment, for example, there is no incoming data, then that log is still not cleaned up because the resource manager still sees the container, the Spark container, as a running application. So it still assumes that data is still required. There's some configuration or setting that we can regularly wipe this data, or how can this work?
I will check into that for you. All right.
So this is especially interesting for us as a streaming application, because there we don't necessarily want to shut down the application itself, but want to get rid of old log data.
Okay. Yeah, I can see where that would be a bit of a problem. Okay, well, that is something I will definitely take a look at. Okay.
Okay,
and,
thanks.
I'll get right back to you. Not everything I have on the top is off the top of my head, but so when it comes down to some of the details, but certainly we'll take a look at that. Okay, so pardon me. We're going to go through a bit more theory. That's an interesting question, by the way. Let me see. We were just we did that one. So we are now going to come into data model data frame. So we're going to do a bit about this Spark API. Okay, so now we're looking at the core API. Now, when I was going through these, I noticed that some of the slides are a little bit weird in terms of the titles, but just I think somebody didn't put them in the right orders, but they don't affect the actual flow of the presentation. Okay, so what we're looking at here is the modes of using Spark, and what we've been doing in class is what's called the Spark shell, where we're basically using it in an interactive mode, standalone or connected to a cluster. The idea behind the Spark shell is its role is not to run production jobs, but really to do a lot of experimentation, to develop the particular logic, to do debugging, to run test runs, to see if things are optimizing correctly. And then once that step is done, we wind up actually writing an application in one of the interface APIs, and then compiling it and running it in a production mode. So the runtime components, just again to remind it, with a client driver, which is where we're interfacing with, takes onto the master, which delegates off to the various workers which work on the distributed storage, whatever the underlying model is that we're using. So the cluster master is going to be have most of the tasks delegated to it. The driver program has the various oversight components which it's using to manage the actual task being routed through the cluster manager, which does the appropriate parallelization and distribution out into the various nodes. And where the difference starts to come in is where some of the tasks wind up being allocated to. So the Spark session is the entry point into the application, which does the initialization in the sense of setting up the initial context that we're going to be working out of, establishes the underlying infrastructure connections to the cluster, getting into the data, and it is also creating this a graph of operations. When it connects to the cluster manager, it actually is getting the executors on the worker nodes, and those things that are created are then being delegated, or getting the code delegated to them, where they're then getting the tasks to run. Now, to remember our terminology, a Spark application is when we open a Spark session. When we execute something, we have a Spark job, and our Spark job maybe consist of a number of stages, and each stage is where we don't have to do any data shuffling. When we do a shuffling, we have to do a different stage. We start a different stage in the job. Within each of the stages, you have a chunk of work called a task, which can be executed inside a single executor. So as long as as long as you don't require a reshuffling of data, then each node can perform a series of tasks. So the terminology is tasks are things that are run on the nodes within a stage. So the driver should be close to the worker nodes. So in other words, it should be near in the sense of network distance, but can be basically anywhere.